Hello, and thank you for taking an interest in my Computer Networking 101 course. Now, as always, this is Tyler with TTech, but this time I have a full course for you guys. So, this course is going to run here for 14 sections, and over the course of 14 sections, I'm going to start with the assumption that maybe you don't know anything about networking. That's fine. We're going to start with an introduction of this, but we're also going to go all the way up to more advanced enterprise topics. And between section 1 and 14, we're going to learn quite a bit about networks. So, now this isn't taking away from things like certifications and stuff like this. This course is geared toward the beginner, but it also gets into some intermediate advanced topics. But this does not follow any certification program. This is just a combination of the networking knowledge I've learned over the years and continue to learn just to help you guys. So I do hope you enjoy it, and I will see you in our first lecture. All right, welcome to our introduction. So the first thing you're probably asking yourself is, well, what's the overall purpose of this anyway? I mean, why do we network computers in the first place? I mean, I know I had the question in my head when I first started learning. Well, there's lots of reasons, and they've really expanded over the years versus when this was first invented. So, a few really good ones. The sharing of knowledge. So, just what I'm doing here. I have knowledge, and I want to share it with as many people as possible. So as well, we can communicate internationally. So there's international connections using the internet, and when we network computers together. Now, as well, I'm sure many of you are familiar with the huge amount of services online you can purchase, you can subscribe to. I mean, my goodness, you can buy your groceries online now. So there's many different opportunities for e-commerce. On computer networks today. This is one of the things we're using them for now. World news, always good to get your news over the internet. You can even take older news mediums, like for instance, shortwave radio, and you can rebroadcast that over the internet on things like SoundCloud and TuneIn and things like that. Now, whether those are still around while you're watching this, I mean, I hope they are, but who knows. Real-time chat and video, so these are things like your applications like Microsoft Teams, Skype, Google Meet, Zoom. There's many of them. And again, streaming video, that's what you're watching right now on YouTube. It's a streaming video service, but there's also many other sites that work the same way, and utilize the internet the same way. Streaming music, of course, and just in general entertainment. So these are just a few of the purpose of why we do this. And in the next one, we're going to dive a little deeper into how this started out and evolved into what it is today. So I will see you there. All right, so from humble beginnings to the modern internet. So the first kind of semblance of the internet we know today came from a DARPA research prototype, and that was called the ARPANET. And this was back in the 1960s. So it has been quite a while. But this was kind of the major starting point for this type of technology and starting to learn how to use computers in the way we do now today. So the first kind of proof of concept, so like a trial run of the ARPANET, was October 29th of 1969. And what happened on that date was one node at UCLA sent a test message to another node at Stanford. So this was the first like wow moment, when they actually started to prove that, hey, maybe this could be something in the future. And obviously it turned out to be something very big, didn't it? So even before the ARPANET came around, traces of what is known as email was found back in 1965. So, I mean, obviously, this was around the time of it, but it actually was not integrated into the ARPANET. This wasn't a thought at the time. But what they had done was, because this was separate research going on into email while they were researching the ARPANET, and they saw that research and they started to utilize it, and they were able to see that it was useful. So they took that technology and they put it into the ARPANET, and that was around the 1970s. So at that time, we had a very trivial, you may even say primitive, email system. But I mean, it wasn't anything like today. I mean, you didn't have Gmail back then. You didn't have Hotmail, or anything like Yahoo or anything like that. So you basically had a very simple directory access system from the research I've done. And that's basically all it was. It didn't even span as far as we can today with email. So, another thing that's important to realize. Back then, every hardware vendor made their equipment with their own combination of proprietary and open standard protocols. But to be honest with you, it was mostly proprietary. So the problem is only one vendor's equipment, like Digital Equipment Corporation, so DECnet equipment, they could only communicate with another DEC machine. So similar, Apple could only communicate with Apple. So you can imagine, what if that was still the case today, in 2020? So I mean, what if it was the case that you could still only have Dell computers? You have to have an entire office of Dell computers because, Dell has their own network stack protocols and all of that. And we'll get into what a network stack is later. It would be insane, though, if you still had to abide by this thinking that we used to have. But, so, like I said, DECnet and AppleTalk were examples of this, but the main point is that they were not designed around open standards and interoperability. So that means they were not designed to talk to each other. Because, I mean, they didn't think this would ever need to talk to anything else. I mean, how could they have? So, to standardize things, more research went on, and a lot of this research actually goes to Berkeley, and it has to do with the Berkeley Software Distributions, or BSD. They had a contract with DARPA, and their task was to design an open standard network stack. Well, what happened was TCP/IP came out of that, and they won the contract. So this happened January 1st, 1983. And when that happened, the ARPANET finally standardized on TCP/IP. So at that point, that was a great milestone because they had all this communication. They had the idea, and now not only the proof of concept worked, but now all this equipment that everyone was working on independently of each other unifies and becomes one. So that's the great thing about this milestone in the history of the internet. So after that, though, the ARPANET grew its connectivity, and it interconnected with the NSFnet in 1986. And if you're curious, that's the National Science Foundation network. But again, you got to remember, back in the ARPANET days, these networks were separate entities. We didn't have a countrywide connection, let alone a worldwide connection. So this is what's really cool, because not only are they combining two separate networks together, basically creating the first WAN, they are allowing it to grow and allowing what they're doing to catch on and move somewhere else. So, one of the most visible changes that you and me may have noticed came in the 1990s. So, this is when the World Wide Web was invented. And this used a protocol, so a set of rules, called HTTP. And that's Hypertext Transfer Protocol. Again, we'll speak about it later. And the version number was 0.9 back then. It's improved quite a bit since then, but the idea is the same. So think about the fact pick up my smartphone here. I have a phone here, and on this phone, it can use HTTP and the internet. So if you just grab your phone or your computer, whatever, find an address bar on it, if you look up there, you will still see HTTP. Now, it will use encryption nowadays. It uses HTTPS, but the core of what we're using is still the same as it was in the 1990s. So you got to understand, from the 1960s to the 1990s, a lot of change has happened. And from the 1990s on, a lot of growth in the internet has taken place as well. I mean, the 1990s internet was much different. We didn't have, things like the crazy animations on websites we have now. We didn't have as many interactive experiences. So it was very, very different. And the bandwidth was much lower. Things are improving very rapidly with the internet. And I assume even after the year this course is being made, 2020, it's going to go, even faster and even better. I can only hope and imagine. So, with that though, that is the main history of where we started to how you are here watching this today. So, I will see you in the next section. Alright, welcome to section 2. So in this section, now that we have a little bit of the purpose of why this is, why networking is used, and a little bit of how we got here, we're going to go ahead and start answering a few very important questions. So the first one is, what are all these wires for? So we will see there's more than just, some of it doesn't even use wires, but we will see that. So the main things I want to cover are cable types, connectors, and signals. So let's see about that. So the main cable type you might be familiar with is called UTP, and this is unshielded twisted pair. Now, UTP is a common cable, and if you have a desktop or you have an Ethernet port called an RJ45 port on your computer, you can look down there and see an example of a UTP cable. Now, the cables came in what's called categories, and basically, categories mean that the higher the category, the more bandwidth or information it can carry. So it goes like this. Cat5 is a little bit older, and there's older standards further back than Cat5 as well. But Cat5e was an improvement over Cat5. When you think improvement, think more bandwidth with UTP. And then you add Cat6 and then Cat6a. It's not on these slides I made, but then you have Cat7 and beyond. But the higher the category, the more information that can be carried over the cable. So the UTP cables were originally used for the POTS system, and this is just the plain old telephone system. Now I'm going to stop here. When I say plain old telephone system, I don't mean flip phones. I mean actual landline phones. And if you don't know what those are, that's fine. But it's a phone like on a desk in an office that has one wire going into it, and it's not wireless. So how before cell phones, I mean, you would call and you'd pick up one phone in a single household, and now with cell phones, the plain old telephone system isn't used as much as it used to be. But the cable, though, I want you to understand, the telephone system's technology was retrofitted to support the internet and computers' data, not just our voice. So you'll find this most commonly in homes, small and large businesses and enterprises, and now you can even find it for some internet connections that you can subscribe to. I know there's many services that offer that now. Now, it does have the most flexible installation options. I don't just mean being able to bend the cable, because if you do more research into UTP, you'll find out it's not a good idea to bend them. But I mean that cost-wise and areas it can be installed in and things are very flexible. So the next type is fiber optic. And there's two types of fiber optic. There's MMF, which is multi-mode fiber, and there's SMF, which is single-mode fiber. So multi-mode fiber, it basically, with fiber optics, the data is actually light signal. But multi-mode fiber and single-mode fiber differ because in multi-mode, more than one light signal can enter it at the same time. And what can happen is they get distorted. With single mode, they're designed so that can't happen, but it is more expensive. But we're going to go into that in a little more detail as well, don't worry. So primarily this is used in service provider and data center environments, as well as campus networks. And campus networks can be hospitals, they can be universities, they can be schools, factories, any group of buildings that are in the same vicinity, but they are separate. That's an example of a campus. Any building with multiple floors or separated. So that is our fiber optic. So the next one is RG cable, and this is radio grade cable. So this is what's used in your cable internet connections or for your cable TV. So this provides internet, and it does it using the coax cable television infrastructure. And I want you to understand again, the cable television infrastructure is older than before using the internet itself. Again, this technology was retrofitted to carry computers' data. So that's how we ended up using it for that. So the RG cables are commonly terminated with F-type connectors. And these connectors, you have a cable modem and a TV that use cable. They just screw into the back there. So there's many locations these are used, but you can look at your cable modem if you use one, or your cable TV and see an example of this. Now, interesting, when you're out, traveling around, driving, whatever, well, okay, maybe not if you're the driver, but All right, so the main coax feed, it's commonly, they string it along telephone poles, and that's one of the ways your provider uses coax cable. And they bring it down the pole into the ground and on pedestals, so inside of them. And they also, if you have cable internet, you'll see a plastic patch panel enclosure. They attach that to the side of your building, and then they run that into your building for your internet access. So you have smaller lines that will run into your building, and that's called a handoff. That's a handoff point. So it's an MPO, or a minimum point of entry. So that is where your connection comes in, your cable feed for your TVs or your internet. So the provider also combines this cable type with fiber, and you'll find that they use the fiber because it actually travels further than UTP will, or that RG will either. So it travels further and carries more information. But regardless, cable, fiber, and telephone cables, they all connect back to what's called the provider's head end, and this is your provider. So this is the part of it that takes that old technology, whatever it may be, and converts it into other types of signals to get you out to the internet. So that's the difference. I mean, before the internet, these head ends did not connect out to the internet. They just fed you, a cable broadcast or, your telephone signal. But that's what came from that. So now, you know this next one pretty well, actually, but you can't see it. So radio waves. So radio waves are used in Wi-Fi, satellite, and cellular connections. So all three of these use transmitters they utilize cables and connectors and antennas. And the three parts there together, they turn electrical power, so electricity, they turn that into electromagnetic waves. And these waves travel through the air or propagate. So they propagate through the air is what they do. And it's the only one of them you can't see. So UTP though, going back to our connector types. So we use RJ45s with UTP. You can also use patch panels and RJ11 plugs. You'll see those in legacy landline connections. And also in DSL internet connections. So older telephone systems, they also used to use 66 and 110 punch-down blocks. You used to terminate them in there as well. So that's a little bit of an overview of that. Alright, so now that we talked about UTP connector options, let's go on to fiber. So fiber has a wide variety of termination options, such as LC, ST, SC, and MTRJ. The thing about fiber is you can have equipment on either side of the connection that has one of the pieces could have LC where the other piece may have MTRJ. And you can kind of convert between the two connectors on each end. So, very interesting though, with fiber, at least in most cases, it's expensive to get different lengths and things of that nature. So UTP is also more customizable cost-wise and things of that nature. So, but another important point about a fiber cable, it's half duplex. This means there's only one strand of glass in the cable, where with UTP there's actually 8 wires. So there's 4 pairs in the cable. So you can send and receive using one cable because that cable actually wraps 8 wires up in one jacket. Well, with fiber, that is not the case. There's one strand of glass in the cable. Some have them where the connector combines the two together. But one strand of glass, one cable of one strand of fiber can only send, and then the other strand of fiber would be your receive. So, if I want to connect 2 pieces of equipment, I need 2 pieces of fiber. So it gets expensive as well to manufacture the glass and all of that. But and definitely the SMF type we talked about is actually a manufacturing method where they make it so the glass can't reflect light at different angles. It can literally only use one angle when it's going down the cable. But the MMF is cheaper because you can have light enter at different angles. That's why they distort each other. You could have light 1 and light 2 enter, but light 1 gets ahead of light 2, and then they mix each other up when the other end receives. But regardless, you need 2 strands of fiber for one connection. UTP is 8 wires, so you don't have to worry about that. It's more cost effective. So, speaking of light and electricity, we're going to talk lastly here about signals. So signal is binary bits. So this just means the ones and zeros. So it's ones and zeros, on or off. So think of a flashlight. It can go on or off. All right? So our devices create these bits and send them over a physical path. So the physical paths we talked about with the cabling, okay? And over those connectors and everything. So the data is our message. And that message or data has to be represented somehow. And that's what this signaling does. So the signal is a representation of the data our computer sent. This happens with any device. So, because of this, each type of physical path carries a different type of signal, but of course they can all carry our computer's data. They just have to represent it in a different way. So that the unshielded twisted pair cable, that uses electricity. And what that electricity does is encodes the bits. So what happens is for like a string of bits, like for instance 1110, you may have a situation where that connection sends, 2 volts or 5 volts and then has a positive voltage 3 times in succession to represent 3 ones in a row. And then you could have it where it drops to a lower voltage to represent a 0. But that's how that works with electricity. It changes the voltage to represent different data. A 1 or a 0 relates to a different voltage on the cable. Now, it's not very high voltage, but I mean, you do have to be careful when you're working with any kind of voltage, obviously. So fiber cable, those strands of glass, they carry light, so they carry photons. And the light is what represents the bits. But in this case, it can be either on or off at a different wavelength. Okay? So the wavelength can change to represent different amounts of information. So you could have, wavelength 1 represent ones, whereas wavelength 2 represents zeros. It's very simplified, but that's the idea. And that's how providers keep things separate. Each customer has a different wavelength. But I mean, not all providers use fiber, but the idea is that they're encoding the bits, okay? Wi-Fi, satellite, and cellular, I'm sorry, RG cable, carries radio frequency. Now, in this case, the radio frequency actually oscillates at a certain rate per second. And when you change the oscillation, you represent a 1 or a 0. So you might go faster to, you might oscillate 5 times in a second to represent a 1, for instance, and you might oscillate 10 times in a second to represent a 0. Okay? That's what it's doing to represent them. So again, Wi-Fi, satellite, and cellular, they use radio frequency in the same way. So just like RG cable does, it's the same way with those 3 mediums. But all this encoding that's happening here, with all of those types, every path has its own modulation, so its own method. And what we just spoke about in a little bit of detail is what represents the data. So modulation represents the data. The data is the signal our computer sends. Okay? So that represents what's being carried over it. Now, with any signal, there's a certain amount of distance the signal can travel. So if I, for instance, get further away from my microphone, if I get over here, it's weaker. Now, what that is called attenuation, because if I get closer, the signal attenuates less before it hits my microphone and creates sound. So the attenuation effect just means when I say something, when it gets to your ear, it may have degraded in a way where you can't understand what I said. Same thing with a network. A computer can send a signal, but if it goes too far before it reaches the receiver, that receiver isn't going to be able to make out what was encoded on the physical path, see? So, to avoid this, of course, these signals, when signals go down long distance paths, like miles in some cases with providers, the signal has to be regenerated with special equipment that takes the signal in on one end and makes an exact copy of it. But because it made the copy of it, now if it could only go 100 meters like with UDP, if you regenerate that with a switch, then it can go another 100 meters. So really you have 200 meters. See what I mean? But that's just a simple example of how it gets regenerated. But we can also have it where, how I said, With cable, you can use cable and you can use fiber. Well, you'd use a media converter to do that. So it takes in the radio frequency on one end, and then it has circuits that convert the frequency to the equivalent light on the other end. So that's an example of how you convert one signal type to another signal type. And on the internet, this happens a lot. It's actually very fascinating, where you might start out on a radio frequency signal on your Wi-Fi, but when you actually get to, say, Google or Wikipedia or whatever, it ends up being, light over a fiber cable to get to the server. So that's a very cool thing about that. Lastly, with these signals, you can't have one device use all of the signal, like 100% of the time. So to help with this, there is TDM, that's time division multiplexing. And multiplexing just means we're sharing something, making multiple of it. And FDM means frequency division multiplexing. So they help the devices share bandwidth on any of those paths. And time division multiplexing says, hey, you can speak for 5 seconds, but when you're speaking, no one else is speaking, so you get all of the bandwidth. All right? With FDM, what happens is it says, hey, everybody has to speak at a lower volume here because we have to have multiple people talking. All right? So to do that, though, computers use a different slice of frequency. This is what your RG cable uses on your cable modem. Every cable modem has certain frequency they use. There's other identifiers as well, but it uses with like Wi-Fi and with cable, there is the identifier your device uses and it gets a certain amount of frequency. In that way, we can share the media or that path. But instead of one person getting all of it, everybody is getting an equal division of it with FDM as opposed to TDM. So, with the bandwidth, all right, so with signals, every signal and path it's using, when you combine the two together, there's a maximum bandwidth that it can send. Otherwise, you're not going to be able to use it properly and things will not work. It won't be able to get data over there that's usable. But bandwidth itself is just the amount and rate of bits that you can encode over that path. So it's kind of like this. It's like I can think of a sentence I want to say, and then the rate, the amount could be the amount of words I want to say in the sentence, and the rate is how fast I actually say the sentence. See what I mean? So that's a different way to think about that. But the bandwidth, so the max bandwidth is known as the link capacity, and that's just like the limit of like words that link can handle. So the data is what it relates to here. But latency, and rate, by the way, that's how many bits it can encode per second. So you could have like 100 megabits, so 100 million bits per second, or you could have 1 gigabit per second. That's 1 billion bits per second. That's how much data in a second you can send. So, along with these signals, you have latency or delay. And what this is it's affected by that bandwidth. So when you have more than one person using the network, the available bandwidth will change over time. Excuse me. And that goes higher or lower, and when the bandwidth changes, it changes the delay or latency of the signal. So when you have low bandwidth, like web pages, for instance, will take longer to go through, and that's why. But jitter, on the other hand, is the difference in delay between transmitting signals. So jitter is like, if I say, hello, how are you? My name is Tyler. What's yours? That delay between that, like that, 2 seconds or so, is jitter. So the less jitter you have, of course, the more data you can send per second, because if the jitter increases, well, the bandwidth will go down. Two important factors of calculating network delay are transmission delay and propagation delay. So transmission delay is sometimes called packetization delay. But what transmission delay is how long it takes for you to send an entire signal. All right? So it's the time if you have 100 megabits on your link and you want to send like 500 bytes or 1 megabyte of data. The time you would take the 1 megabyte and times it by 8 to get it into bits, and then you would divide it by the link. All right, the 100 megabits. You would get a result in time, and that's the delay or transmission delay of sending 1 megabyte of data on a 100 megabit per second link. So that's transmission delay. Propagation delay is actually how long it takes for 1 bit of that 1 megabyte to get from the start of the cable to the end of the cable, or the radio wave, or whatever you're using. But that's fixed. Transmission delay is affected by the available bandwidth, and there's many ways in networking to artificially affect the transmission delay. But the signal experiences another type of delay that we really can't control. And this is delay when it's processed by a network device. And I'm sorry, actually we can control this, but at least only to an extent on our equipment. This is known as queuing delay, okay? And most times this is unpredictable, and it always changes depending on how much information is being sent. So you may have experienced 5 o'clock, 5 p.m. or 1700 hours. So when everyone's using your provider's network, everybody on there gets a slower connection. A lot of this is caused by queuing delay because there's more data that the provider has to handle, and you have to wait in line, essentially, in the queue. But that makes it go up or down. But the three types together, so you have transmission delay, propagation delay, and queuing delay. We put those together, and the sum of those is the end-to-end delay. And this is just like if I speak an entire sentence, like, the one I spoke before, the entire time of that, if you were to time it, is the end-to-end delay of a transmission. So this is like when you open up your web browser and do a search on Google. If you hit enter, you see the time that comes up in the side there. That's how long it took to get that page. So that's the end-to-end delay. And ping can tell you this as well, but we'll talk about that later. But all of the factors that make up the end-to-end delay, you can represent them by the RTT, or round trip time. And again, those are in applications such as ping and traceroute and things like that. So now, in this next section here, in this next part, we're going to go through what these devices actually look like in a network. So, brain reset. We're just going to look at some devices now. I know that was quite a bit of information. You may want to rewatch that section. But I will see you in a second, and we'll go through some network devices. Alright, so now talking about these network devices. Now, I do want to say, I took all these pictures myself, and they're from my lab, just to clear any confusion about, where the pictures, copyright and all that. From here, what we're doing is, these signals we just talked about, these are Ethernet ports on this Cisco 2621 router. The signals can come in this port and go out this port, as well as this port here. And there's even signals that can come in and out of these ports, but they're for different purposes. But the idea is this is an enterprise-grade router. It's made for maximum uptime and the highest performance possible, at least in that class of router. I mean, they're very expensive, but they're made in a way that it's really worth the cost. So this is an enterprise grade switch. And here, all these ports are the RJ45 ports, just like on the router. And these ports can take a signal from here. They could send it out this port here, or a signal from this port to this port. And so you can connect up to 24 computers to this switch and have a bigger network like that. This is a managed switch, though, too, so it can do many other features than just a normal unmanaged switch. And yes, we will talk about that later. So from here, though, this is an example as well of a media converter, because these are UTP and they use electricity. These are the RJ45 ports. And these are fiber ports here, and these use MTRJ. So that could take the electrical signal on one of those ports, send it out of the port for fiber as light. So those are like used for connecting the switches at high speeds and stuff like that. But you notice how there's two ports. Now you know why, because one strand is for sending, one is for receiving. But not in this case, remember, with the UTP cable. So this is a wireless access point. This is another media converter, to be honest. It has on inside of it transmitters for the radio frequency for the Wi-Fi. And on the other side here, it takes that signal, the radio frequency, and sends it out as UTP. So, I'm sorry, over UTP, as electricity. And this is a good old dial-up modem. And what was done with these is, of course, these used the plain old telephone system. And you had your phone line here where your normal landline would connect in. And I'm sorry, the phone here would connect in, and then this would connect in as well. And then you would connect this to your computer. And, you know, this would obviously only be used for one computer at a time. And as well, if the phone was being used, the voice signal of the person talking in the phone would interfere with the computer's signal over the same network. So you could only either use the phone or send data on your computer. All right, you weren't doing YouTube on these kinds of modems, let me tell you. Now though, the DSL modem, this is a digital subscriber line modem, and this improved things, and we actually still use these today. So it still uses the plain old telephone network, and that's where an RJ11 goes, connector there, a little smaller than an RJ45, but it still uses UTP cable. And you got your power here, and then this is where you would connect into your computer. The advantage is you can connect into other equipment like a router to share that signal, or like a Wi-Fi router. And so now the voice signal for a landline is separate from your computer's data signal. So they won't interfere with each other anymore. And this is still in use today, and you may even have one watching this video over it. Because, I mean, the bandwidth is more with DSL compared to dial-up. So a cable modem, this is what I have. And what we do here is put the RG cable in here with an F connector. You got your power here, and then this just turns it into an electrical signal. And again, this is still a media converter at its core, and this is too. Just converts that radio frequency to electricity. But again, you connect that into your router and all of that. And this is a consumer Wi-Fi router. This is a WRT 150N version 1. And this is the port you connect to the internet, called the WAN port. These ports are your LAN ports. And then this one also has built-in Wi-Fi, so it also uses radio frequency. So again, these are the ports that use the electricity with RJ45, and then that can send the signals in and out of the device in many different directions and ways. This is a consumer switch. This is like that enterprise switch, but they're just not made as well. They still work well, but they don't have as many features that you need in the enterprise space. So here we just plug our cables in, as you see, and it just sends signals around any of its 8 ports. You can connect up to 8 computers. You can even connect it to another switch. You have to be careful with that, though. So this is an SMB router. This is between enterprise and consumer as far as price goes. You have, again, your LAN ports, you have your WAN, and then you also have a DMZ port. We'll talk about DMZs later, but all you need to know is it's 3 separate groups of computers, okay? That's what you get from using a device like that. So a home connection here, this is where your modem, DSL, hooks into the WAN port. Same thing with a cable modem with a consumer device. And then this is a cable internet connection example, but with an SMB where you connect into the internet port and you could still make a third network with this device, right? And this is how you put it together because the SMB doesn't have Wi-Fi. So you connect to your modem, to your other device, your SMB router, to your switch, and then connect from the switch to the Wi-Fi router, but turn off some of the features to get an access point. So normally you'd use a wireless access point for this. All right, so now we're at the beginning of section 3. So I hope you enjoyed it this far, and I will see you in section 3, and we'll get talking about Ethernet. All right, so what is Ethernet? Well, Ethernet has a standard number of 802.3, and that's just how we identify it when we talk about it, okay? So what Ethernet is it's a set of rules that computers follow in order to talk to each other. So it's just a protocol is all it is. Now it's very important though. Ethernet encapsulates data inside of frames. And what that means is that the data our computers send gets put in a frame by Ethernet. It's part of the rules of communicating. Now, this frame that Ethernet makes, it has MAC addresses in it, and that stands for Media Access Control. All right? These addresses have to do with which computer sent the information, but not only that, they also have to do with what computer has to receive the information as well. So it's just like on an envelope. You have a destination address where the letter is going, and you have a return address where it came from. Now, with Ethernet, an important term is broadcast domain. All this means is that all the computers can hear each other. So it's similar to, everyone being in the same room. Everyone can hear each other. A collision domain, on the other hand, means that all computers have to share bandwidth. So it's like having one hallway that only one person can walk down at a time, or one doorway. You can only use it one at a time. All right, so remember those two terms because they're fundamental to your understanding of Ethernet when you go further. Now, in old Ethernet networks, or legacy, they used a protocol called CSMA-CD because in older Ethernet, every computer was in one broadcast domain and they were in one collision domain. So this protocol helped them share the bandwidth correctly. So this protocol is called Carrier Sense Multiple Access with Collision Detection. What that all means is when a computer had information it wanted to send, it listened to the network, to the wire as it's called. And if the wire was quiet, the computer could send. But as soon as it heard a signal that wasn't supposed to be on the wire, it would stop sending. And then it would send a jamming signal. Now, this is the collision detection part of it. The collision is detected, and the jamming signal tells everyone to stop using the network. And the jamming signal made everyone back off for a random time. And then, when that back off time expired, the computers would try and send again. As you imagine, this is like trying to go through one door without communicating who's going first. It's very slow, it's very error prone, and it's inefficient. So that's how we started with Ethernet, at least. Now, Ethernet also uses a CRC checksum, and this checksum is a value that has to match on either end of the sender and receiver. So this stands for cyclical redundancy check, but all it means is that I put the letter A on my frame before I send it, and if it gets to you, it better still have the letter A on it. Otherwise, it was corrupted. And if that's the case, it has to be resent. It's more complex than that, but that's the idea of what it's doing. Now, we have three ways in Ethernet that frames can be sent. There's unicast, which is a one-to-one communication. So this is like me talking only to you. Now, multicast communication is one to a group. This is like if only, like you're in a lecture hall, for instance, and only the people in that auditorium are hearing you speak. Now, everyone else outside of the room, they're around, they're in the network, but they're not necessarily wanting to hear you speak. So in multicast, you only talk to one group, and that group has to subscribe to wanting that communication. So the broadcast is one to all. One to all means I'm getting everywhere at one time. And this is what the term broadcast domain refers to. It's anywhere a broadcast can get in the network. Now, down here, these three are example MAC addresses. And this is an example unicast address. This is one computer. This is an example multicast address. This is a address actually for STP. But basically, in that case, any computer that wants to run the protocol listens for frames destined to this address automatically. And there's many other protocols that use multicast in the same way. And again, a broadcast, we just spoke. It's all Fs, and it goes everywhere, and everyone will receive it regardless. So again, remember, MAC address, that's Media Access Control Address. All this does is identify one computer signal, and when you're looking at it, it's represented as 12 hexadecimal characters. And hexadecimal is the values it can use are only 0 through 9 and the letters A through F. So it can't go beyond that. But that's how you know you're looking at hexadecimal. And you will also sometimes see a 0x before the hexadecimal. In some documentation, this just means you're about to see a hexadecimal. You're supposed to interpret it as hexadecimal. Now, binary ties into hexadecimal, and of course, binary is just what computers understand. And these MAC addresses actually are 48 binary bits, and that's burned into the ROM, basically. But we have 8 binary bits and we have 1 byte. So what that means is each piece of the hexadecimal address is, because that's 12 hexadecimal characters, like this example MAC here. The 00 is 1 byte, and then the colon separates the bytes. So each hexadecimal character is 4 bytes long, and they have bit values as well. But you'll get into that later. And the first 6 parts, the 6 characters in the MAC, so the 00, 11, 22, are the OUI, or the Organizational Unique Identifier of the MAC address. The last 6 characters are the unique part of the MAC address. So now we're going to talk here about devices and how they utilize the MAC address. Now, this first device is called an Ethernet hub, and this is the very first device that was important in an Ethernet-based network. Now, these didn't use MAC addresses at all. What they just simply did was take one signal from one computer, and then they made a copy of that signal and sent it to all the other computers that were connected to it. So it sent it out every other port. So what occurred was every computer in the hub is in a shared broadcast domain, so they can hear everyone's broadcasts that is part of that network. But because they're in a shared collision domain as well, they had to share bandwidth. And this is where CSMA/CD comes in as well. This is what it was used with. So again, the more computers that used the same hub, you had less bandwidth for each of them. So it was quite the problem. I mean, it was good that this was available to use. It was better than not having it. But I mean, we've improved things quite a bit since the time of Ethernet hubs. So this is the main idea of how they had worked. They didn't use MACs, and they just sent the signal to everyone. Now, this also has security implications as well, because if the signal is not meant for you, maybe you're not supposed to have that data, you know. So an improvement upon that is Ethernet switches. These actually started to use the MAC address. So the original name for a switch is a bridge. So you hear the term bridge used to mean switch when you go on in your studies. So switches take one computer signal, but the cool thing is they only send it to the computer it's addressed to. Now, how they do that is because they have a source and destination MAC address. We'll get into that in a second. But the same applies that every computer on a switch is in one broadcast domain by default. And that's very important because there's things we're going to talk about much later that kind of can improve the situation of having one broadcast domain. But each computer, instead of having to share a collision domain, so share bandwidth, they have their own collision domain. So that's really awesome. And what that means, though, is that every port on a switch is one collision domain. So if you have a 24-port switch, even if it's unmanaged, you have 24 collision domains in one broadcast domain. Or if you have an unmanaged 8-port switch or a 5-port Netgear switch, for instance, you have 5 collision domains on that switch, and you have one broadcast domain. Okay? So this is why it was an advantage. You don't have to share the bandwidth anymore. You get dedicated bandwidth between you and the device you're talking to. So, I mean, that's the really interesting thing about it. Now, switches use special circuits, and it causes them to be faster than bridges. They use ASICs, and that stands for Application Specific Integrated Circuits. Now, these are just very specialized chips on their PCB, so they're circuit boards that all their job is to switch frames all day long, 24/7. That's all they care about. They don't care about anything else. So how do they do this, though, with the ASICs? Well, each computer signal is made separate by that MAC address, remember? What switches do is they use the source MAC address in the frame. When a computer sends a frame to one of the switch's ports. But the switch takes that source address and it puts that address into the MAC address table of itself. So inside of its ASIC, it has a table, so a small amount of memory called a CAM, Content Addressable Memory Table. And this memory, this table, just keeps track of where each computer is on the switch. Now, you can't see this process on unmanaged switches. It's easier to see on managed switches, but I have a lab coming up that I kind of do it in a different way, and you'll be able to see it. It'll be quite interesting. So they perform 3 functions with a frame. So a frame is just a signal with a frame just identifies a signal, so kind of they're one and the same, but they can flood the frame, and that means they send it out to every computer in the broadcast domain. This is very important though. They only send it out every port in the broadcast domain, except the port that the frame was received on. That's very important. So another function that's they do every all day, and what your switch is doing right now in your Wi-Fi router is forwarding, and this is sending the signal or frame to a single computer. But the way it knows that is it looks at the destination MAC address and compares that with its CAM table entries, and then it sends it out. If computer 1 talks to computer 2, it sees the MAC address destined to computer 2 and sends it out that port. Now the third thing is filtering. This prevents sending the signal basically back on itself. So you can't have a situation where a frame comes into port 1 and it sends it back out port 1. That can cause loops and wasted bandwidth and collisions. Sometimes, though, that's very important. And in some networks that use hubs still, it can be something where it would have to be filtered because the hub will send the signal into a port on the switch that it's not meant to go, and that can cause issues. But flooding and forwarding are the main functions of a switch that are used day to day. So when switches are connected directly to one another, they flood broadcast frames, and they'll flood a broadcast frame that's going to all Fs as a destination MAC address. That happens indefinitely, so forever, and it wastes bandwidth of your network and can bring your entire network down. So what they use, and this is only applicable to managed switches. So if you're connecting switches together, unless they're managed, be very careful because you can introduce a broadcast storm, it's called. And that's not a good thing in a network. So STP is spanning tree protocol though. And the switch needs to understand this protocol, of course, but this decides that one switch should be in charge. So it elects it as the root bridge, all right? And what happens is, if you have 3 switches all connected together, and they have redundant paths to each other, other switches that are not elected as the root, they have to make one path to the root, because any frames those non-root switches process have to get back to the root switch in the network. So they make one path to the switch, to the root switch called the root path. All right? And the ports are called root ports when they do that, but you'll learn that later on in your studies. So the whole goal, though, is we shut down paths that reach the same destination. So, wireless access points. So, wireless Ethernet, and now this is known as 802.11, and you've probably seen this with your Wi-Fi router, so it'll be easy to understand what I'm talking about. So, wireless access points are kind of like Ethernet switches, and what they do is they send the signal to the right computer, and they use the destination MAC address to do this. But we're kind of going backwards and having problems that hubs had, because they use radio frequency, like we spoke about in signals. Everyone connected to the same access point shares one collision domain. Now, the computers, when they communicate with one another, they do have to use the access point as a single point of contact for everyone. Now, and there is a method that is called ad hoc Wi-Fi. And that method involves computers talking directly to one another. Now, that is used, but it's not as common as it was. But basically, access points just take that radio frequency and they turn it into an electrical signal. And by doing this, you can extend access to an Ethernet network, but you're using the air to do it because that's what the radio frequency travels through. Now, only one computer can use the air for a period of time, and there's two things that decide this. There's RTS and CTS, which are request to send and clear to send. All this means is that, hey, I have this data to send, it's going to take me 10 seconds. That's your request. And then when you hear a clear to send, they say, okay, this computer number 1 is going to use the air for 10 seconds, nobody else talk. That's what the access point tells anybody connected to itself. And then computer 1 can send for the 10 seconds, and then somebody else will ask for permission. And that's how your Wi-Fi works, but this is a lot of the reason you have lower bandwidth on Wi-Fi compared to an Ethernet network with, UDP cable. Because everyone has to take turns and you're basically using a hub, but it's wireless. So, you still have to avoid collisions, of course, because just like hubs using CSMA CD, the wireless access points have to use CSMA CA, and that's carrier sense multiple access with collision avoidance. And the same applies. They're just watching out, making sure no one's using the air. If they are, they avoid that collision. But the same thing also happens where they need a checksum. The same thing where it is that value has to match. If I put an A on that frame, when you receive that frame, it better have an A on it. Otherwise, it's corrupted and it has to be, resent to them. But the good and bad thing about Wi-Fi is this. The stronger the received signal from a wireless client and access point, you can use more bandwidth in that case. But the lower the signal, the lower the bandwidth. This doesn't happen with Ethernet networks. It's constant, as long as your UTP connection is good and everything, and solid into the machine. But here's a good way to remember it. In general, the received signal strength, so the RSSI, that's the received signal strength indicator, the closer it is to 0 decibels for a measurement, the stronger it is. All right? The closer it is to minus 100 decibels, the weaker it is. Okay? So the weaker it is, the less bandwidth. The stronger it is, the more bandwidth. So basically, to sum it up, the further you're away from the access point, the lower the bandwidth is. Now, any access point uses channel numbers, SSIDs, security settings, and their MAC address. But all those combine to create a connection. Remember, it's wireless. So like if you live in an apartment complex, there's many access points all using the air at one time, and many computers too. The only way to keep that straight is with these values being decided upon between the clients and the access points. And the radio frequencies that are used are 2.4 gigahertz and 5 gigahertz. And the frequency there, it's broken up into channels, and the channel is like our wire that we were encoding bits over. It's the same thing. It's the slice of frequency that we encode bits on. And the channel numbers are 1 through 14, and that's for 2.4 gigahertz. In the US, we can only use 1 through 11, though. In other countries, you can use more. And they're 20 megahertz and 40 megahertz wide. 20 megahertz is one single channel, whereas 40 megahertz is two channels bonded together. That's good and bad, because if you're very congested, using 40 megahertz will actually cause more interference to your neighbors, so you may not want to do that. But the reason is, when you get interference, everyone has lower bandwidth, because everyone's using the air in this case. But the only channels that are safe that don't overlap are 1, 6, and 11. So use those if you get a chance to set that setting on your Wi-Fi router. They can still overlap if you have a lot of access points. So you can have two of them on channel 6 that mess with each other's signals. That still happens. That's why all those other concepts are important that we just spoke about. 5 gigahertz, though, doesn't have as much interference right now, at least. And these use 32 through 165 for their groups of frequencies, their channels. You usually don't have to worry about channels though. It's so wide that you don't have a problem. And these are 20 megahertz to 160 megahertz. And I do want to say something, even with 2.4 gigahertz, the higher the width of the channel, the more bandwidth. All right? So 40 megahertz can send more bandwidth than 20, but 20 can send a lot less than 160, you see? That's why 5 gigahertz is faster. There's more frequency. But also, 5 gigahertz oscillates more, meaning it doesn't go as far, though. That's the drawback. Now, security protocols are included so we know who's connecting and that they are allowed to. We have open, we have WEP, the wired equivalency protocol. You have WPA 1, 2, and 3, that's Wi-Fi protected access. And you have EAP, that's extensible authentication protocol. Now, encryption methods are meant to hide the data from the client and the access point, so only the two parties in that communication know what's being sent. It encrypts data of an attempt to authenticate and a successful authentication, by the way. But our ciphers are RC4, which we don't use that much anymore, Temporal Key Integrity Protocol, which we don't use that much, and CCMP, which we do use quite a bit of. Now, you can also, remember the MAC addresses identify a signal. You can filter on that, and you can use this both in wired Ethernet 802.3 and wireless 802.11. And that restricts access to certain devices. That's a very good setting to have. But that's a little bit about Wi-Fi. Now, the last thing we're going to do here is just an Ethernet switch lab. We're going to look at the learning, the flooding, and the forwarding operation with 3 PCs connected to one switch. So I will see you in the lab. All right, welcome to our Ethernet switch lab. So this is set up especially for this. I've set this up custom to be able to really explain it to you in a detailed way. So up here at the top, we have our switch. Don't concern yourself with the commands. That's besides the point right now. And we are listening for packets basically on all the interfaces. This PC1 is 1111. He's attached to port 1. PC2 is 1112, and he's attached to port 2. And PC3 is attached to port 3 and is 1113. What I want to do is I want to ping PC2 from PC1. So let's ping 1112. All right. So what just happened? Well, it went up port 1, the ARP request here. All right. And the ARP request went from 1112. It's asking who has 1112. I want you to tell 1111 because that's who sent this request. This gets the MAC address. Now you can see the ARP reply went back through as well. But where did the request go to? Well, if we look at PC 3, it went to PC 3. You see how it's destined to all Fs? That's how you know it's a broadcast. That's what goes throughout the entire broadcast domain. And this is the source. The reason he didn't respond is because he doesn't have this address. So he will just drop the broadcast, but he still has to process it. So as far as we know, he didn't have to get anything in his ARP cache. That's not needed, and we'll talk about ARP caches later. But if we look at PC2, he received the broadcast, and then this request here. He has this address, so he sent back an ARP reply to that address at layer 2. And now he has that, the reply with those MAC addresses. And when he did that, this is what went back through the switch here on from port 2 to port 1. And it went back to him. And after all of that is done, if we look, PC1 has PC2's IP address and MAC address mapping, and PC2 has it as well for 1111 because he learned it from the source of the ARP request, the source MAC address here. After all of that, PC1 sent his echo request. But this time, the switch only sent this echo request packet out of port 2. Because if we look, we don't see an echo request here. You see the advantage? A hub would have also sent the echo request out of this port, even though it wasn't destined for PC3 at all. It selectively sent it out of just this port, and then when PC2 replies here from 1112 to 1111 and has the MAC addresses on there, this switch only sends this reply out of port 1 back to PC1. And then this is that reply here. This is the output. So when all that was happening, the switch, if we look at its interface, and again, this isn't how normally a switch works, this is a special configuration. Remember how they learn source MAC addresses? This is an example of that. 02B78A03 on VLAN 1, don't worry too much about that right now, is off of EM1. This is the equivalent of the CAM table, or it's also called either a MAC address table or a bridging table. And then 275762F3, I'm sorry, 0800275762F3, and likewise on the top one there's 080027B78803 is off port 1 and 2. So it didn't learn anything for PC3 because PC3 has not sent any traffic, it's just received traffic. So I hope that made sense of how the switches do those operations for you. So I hope that was helpful. I will see you in section 4, starting next. All right, welcome to section 4. So in this section, we're going to talk about the Internet Protocol and the things that are important to know about it, because there's quite a bit. So, excuse me. Remember how Ethernet has MAC addresses, those media access control addresses? What the Internet Protocol does, or IP for short, it takes the MAC addresses and basically puts them in groups. So all those network interface cards or the cards that in the computer that have MAC addresses, you configure IP on them and they know that they're all in the same group together. That's why there's important values that we have to understand to be able to do this. But a lot of networking and computer networking has to do with managing these IPs, because other parts of networking like security and having like intrusion detection type schemes and things, those all don't matter if we don't know how to manage IP networks, because it's the core of what computer networking is. So, this protocol is used between IP networks and our broadcast domains. And it encapsulates data, but this time, this is a distinction here. The data that it's putting inside of a packet is that frame. And this will make sense much later in the course. It'll finally click and make sense why I keep saying this. But the frames go inside, the packet goes inside. I'm sorry, the data the packet is encapsulating is TCP or UDP. My apologies, said it backwards. But we'll get to those in a little bit. But each protocol encapsulates something. So just like Ethernet, we have source addresses and we have destination addresses. And, again, going back to the envelope, it's the same thing, same reason. Now, the source address is the computer it's coming from, whereas the destination is the one it's going to. A distinction with IP is that it does not make sure the data arrives correctly. So it just sends, it doesn't know if it got there or not. So it's like when you send a package in the mail, at least in the US, and you have a tracking number with it, and you can verify if it got there or not. So the data, of course, is broken up into packets, so there isn't like one large chunk of data. The data is multiple packets being sent. And like Ethernet, we use a checksum. If I write the letter A, when you get it on the other end, it better have A on it. Otherwise, you have to resend that data. So again, the specific part of the Internet Protocol that's very important is IP addresses. IP addresses identify a single computer in one broadcast domain. All right, so that group of computers, or basically, you can think of it as a group of MAC addresses, essentially. And it identifies one of those. And the IP addresses are also used to know how to send packets through routers, which we're going to talk about in this section. But it also has different things where it can control what path the data will take as well. So you can already see IP has a lot more features than Ethernet. Ethernet only has a source and destination, and there's no real way to control where it goes besides switches. But routers can control it in much greater detail of specifics of its path. Now we have two versions of this protocol, but they both, in essence, they achieve the same thing. We have IPv4 and we have IPv6. Now IPv6 is newer than IPv4, but they are both still used very much in computer networks today. So this IP address in IPv4 has a format. Just like how MAC addresses were 48 binary bits, well, IPv4 is 32 binary bits. But instead of just writing out the 32 bits all as one string, like the example below, we actually represent those bits as decimal. So these 32 bits, we break them up into sections called octets. And there is 8 sections in one IPv4 address. So these down below, the 192.168.1.1 and 208.131.1.45 are examples of IPv4 addresses. Every section with the period or dot as the separator is an octet. And each of these sections contains 8 bits. All right? And the 8 bits can be turned on or off to represent different decimal values. Now, just like Ethernet has different ways to send frames, IP has different ways as well. With this, we have unicast, which is one-to-one, and multicast, which is one to a group, and broadcast, which is one to all. Now, these do map directly to Ethernet, except they're not represented in hexadecimal like before. They're represented in decimal. So like 192.168.1.2 is a unicast address. So what does this mean? Well, it means one NIC will be assigned that address, one computer. So that IP address maps to one and only one MAC address in the broadcast domain. Multicast can actually map to many different MAC addresses at once because, remember, they subscribe to that multicast group. Okay? So it can be like a switch will make multiple copies of a multicast frame, because when it's multicast, this address will be a multicast version, not that exact one. But if you want to use multicast, you need a multicast IP address and you need a multicast MAC address, because they're both for different purposes. You need both of them for communication, though. the one is just for a broadcast domain, a single one. The other is for going across broadcast domains. And again, broadcast is just like if you're yelling and it gets everywhere in that broadcast domain. And also, that is all ones. That's 32 ones all on, so they're all ones. Now, to make managing IPv4 easier, they are actually broken up into what's called class ranges. And what class ranges do is each range has a maximum number of computers. So each range can group together a certain amount of MAC addresses or computers. So we have A, B, C, D, and E. And those are the IPv4 classes. And these are just for the IPv4 protocol. It's different in IPv6. So A, B, C, and D are the most commonly used classes you're going to see on most any computers and any network equipment. Now, you may not use class D as much on computers themselves, but you use all of them for different reasons. The reason is D is for the multicasting addresses, so only specific tasks on devices in a network will need multicasting addresses. That's why it's not as common as A, B, and C, because A, B, and C are used for unicast communication. Now, E is a class you really don't have to worry as much about, because that's reserved. We can't assign them to a computer or a network device. It won't allow you to do that. It's just been told in its program not to. So the class of address, this is very important because when I first learned about all of this, this was a source of a lot of confusion and frustration for me. So the class is determined by that first octet. It's determined by the first octet's value, not the mask, and that will make sense when we go forward into this section. So in A class, you want this to be, it has to be 1 through 126 for the first value of that address, so the first section. Now the entire range is written out here. We have 1000 through 126, 255, 255, 255. And again, if you want, you can pause and look at all the ranges. It's so you know the entire range that is valid. And if you look at the pattern, all that has to not change is the first octet. The first octet can change within these values as it's, part that can change, but the other sections can't. I'm sorry, the other sections can. I apologize. So the other sections can change. But again, a class B is 128 through 191. A class C is 192 through 223. A class D is 224 through 239. And E is 240 through 254. Now, only A, B, and C have a default classful mask. And we're going to see why that's important in a few minutes. Now, out of those ranges, A and B specifically, we have reserved addresses that can't be used on any computer, that are used for something else, rather. So you have 127, 000 through 127, 255, 255, 255. And this is part of the Class A range, but the whole purpose of this range of IPv4 address is to test your network stack. So you want to make sure with this, you're making sure your entire computer can use a network, essentially. So this is what's called the loopback address. Now, traditionally, you only ping when you're testing to 127.0.0.1. but you can use the entire range. But 127.0.0.1 is the accepted address in that range to test. Okay? Another one that's important from the B class is 169.254.0.0 through 169.254.255.255. Now, this is a function that is called a PIPA, and that is automatic private IP addressing. And the importance of this reserved class will become important once we move on to assigning these addresses. But essentially, this is a fallback method that will be assigned if everything else fails to assign an address. So, public and private addresses. What is this about? Well, IPv4 is, remember how it's 32 bits. So, how you know the amount of addresses you can have there are 2, the equation 2 to the 32nd power. You can express it as that. And that comes out to 4,294,967,296. And that's the entire IPv4 range from class A to class E. So we can't actually use all those by a long shot because we can only assign addresses from the A, B, and C classes to computers. And remember, D is for multicasting. Multicasting isn't assigned to a computer, it's subscribed to as a destination address. Okay? So, we need more unique addresses than we have in IPv4. So, some of them were made public, whereas some of them were made private. Just like we reserved the loopback address range, and just like we reserved the APIPA range, you just took that concept and split it up even more. So we have 7.5 billion people in the world as of 2018 at least. And this is more than the unique address space of IPv4. So what happened was, this is the private and public ranges. The private A range of addresses, and you see why we call it an A range now, right? Because that falls through 1 and 126. So this range is 10.0.0.0 through 10.255.255, and this is the reserved range for using on your network when you're using IPv4. Now, way back when, this wasn't the case, and you were assigned a public address, and you would use that for every single computer on the network. This is not the case now. If you create a network of computers with IPv4 in 2020, you have to use these ranges. Otherwise, it won't communicate correctly with the rest of the internet. A B range, likewise, is 172.16.0.0 through 172.31.255.255. And C is 192.168.0.0 through 192.168.255.255. And again, that is because this 172 is between 128 and 191. Likewise, the 192 is between 192 and 223. Alright, moving on to IPv4 subnetting. Now, subnetting is the very crucial topic in IPv4. This is what creates the groups, essentially. This is the whole concept of having groups. If we couldn't subnet in IPv4, we would be back to having one big broadcast domain. That would not be good. It would not be efficient. It would not be secure, and many other things would go wrong because of that. But essentially, the large number of networks and computers on them, we want to break them into smaller portions. That's essentially what we're doing with subnetting. We're taking a bigger network and breaking it into smaller pieces. And what you do is you take the A, B, and C classes and we're making those smaller chunks of themselves. Instead of having the entire A range, we would have smaller chunks that make up the entire A range. If you put all these chunks back together, you would have the entire A range, but we're chopping them up into smaller pieces. Now, subnetting runs through IP routing, routing protocols, network design, routing protocol configuration, firewall rule configuration. What I'm saying is you cannot get away from you can't ignore learning subnetting. You can't put it off. You can for a while, but if you do, you're going to hit a wall in networking where you're not going to understand something because you need to know this, period. Okay? So rewatch this section a few times if you need to. It took me a while to get subnetting. The concept makes sense when you think about it in your head, but when we talk about all of the interesting things about it, it's not as straightforward as you would think. So every bit, remember, in the octets, they have their own value here, and we subnet using binary to actually understand where the networks divide and separate at. Now, here's an example of the bit values here. And if you look at that pattern, they double by powers of 2 is what we're essentially doing. So we have 1, 2, 4, 8, 16, 32, 64, and 128. And that is the bit values for one octet, or one section of that IPv4 address. Here, we're going to go over examples of how they go together. In this first example, I have 8 bits, but the rightmost bit I have turned on, so it's a 1. It can only be 1 or 0 because we're working in base 2, which is binary. Now, if only one of them is on, I only have to add that respective bit value. So I look up at my chart, and remember, this was reversed, so really the 1 starts over here. Now, what happens is, because remember, this is right to left, so 1 is here. So you only add 1, and you don't have to add anything else. So your value is you come out with a 1. If you have 2 on, the bit values that are on are 128, because now we're all the way to the left, the leftmost bits. We add 128 plus 64 in this case, in this octet, and we get 192. So what we're doing is converting the binary to decimal is what we're doing. And this is important to understand. If you have all zeros, you don't have to add anything, so it's 0. If you have all 1s, you have 256. Now wait a second, I said that when you see broadcast, it's all 1s on. Well, it is. But there is some of the non-intuitive things about subnetting are about to show themselves because this is 256. And if you've done programming before, this is what that really adds up to. But in networking, how we use binary in the networking field is a little bit different than how programmers use binary. So again, though, you just add all those values up and you get 256. So the binary, and now that we know the binary, we have to put it together with a subnet mask. In IPv4, we have a default subnet mask, and this is only the first step of the confusion. So in a public range of an IPv4 address, you have class A, and that is 255.0.0.0. Now, this can address a maximum number of computers or MAC addresses, so it can make a broadcast domain consisting of 16,777,216 hosts. Okay? And a class B is 255.0.0, and that can make a network of 65,500 536 hosts. And then a C has 255, 255, 255.0, and that can address 256 hosts. Now, how we come to these values here are, remember, that is 8 ones on in the Class A subnet mask. So what happens is we have a network portion. So some of the bits are network in the subnet mask, whereas the other bits are host bits. And very simply, if we add up the 8, 16, and 24 bits that these next 3 sections have, you take that and say 2 to the power of 24. Or, just count by 2 24 times and double as you go. But, 2 to the power 24 is the accepted formula for that. But that's the maximum number of hosts. And this is one network. If you see this mask on your computer and it falls in the A range, you have one big network with that many hosts. But with the B as an example, you have 16 host bits. The ones that are on all ones can't change, okay? So you have 16 host bits. So we say 2 to the power of 16, or 2 and count 16 and double as you go. You have 65,536 hosts. If you have a C, you have 255, 255, 250, so you have 8 host bits. And that is 2 to the power of 8, which is 256. So that's the default mask of a public IPv4 address. And this is private. I'm sorry. The private is the little bit different masks, but the reason, like, the Class A is the same, but the Class B is a little bit different. And in this case, if you add up, this is 8 bits in the first octet, and then we have 4 bits in the second, so that adds up to 240 in decimal. And then you have another 4 bits, and then another section of 8 and 8. So we have 16 plus 4 host bits, so we have 20 host bits in a private Class B default mask. So you say 2 to the power of 20, and you get 1,048,576 hosts. And this is only if you're using a private address and mask. But this mask can still apply to a public address. That's where it gets confusing and where you have to pay attention. So a private Class C is 255, 255.0.0, and this is 16 host bits, so 2 to the power of 16 is 65,536. So that's the difference between public and privates. All right? So that is some of the base of subnetting. So go back through, memorize these numbers if you want, memorize the masks and the classes of public and private, because it will help you understand the subnetting to come as we move forward in the course. So now that we have a foundation of subnetting, we can now look at the subnet mask and learn how we can figure out different aspects of an address of the IP network. So like how many hosts a subnet mask gives us, and how many networks that the network is broken up into. So for instance, to find out how many hosts a subnet mask will provide, all you have to do is, like we'd said before, you count each host bit starting from the right to left. Or you can just take the number of host bits, and if it was 8 host bits, you just do 2 to the power of 8, then you get 256. Now, to count for networks, on the other hand, you count left to right, or again, same thing, just take the number of network bits. If it was 4, for instance, and you're using a public Class C, you have 2 to the power of 4, so you have 16 networks. or just count those 4 network bits from left to right as 2, 4, 8, 16, doubled by power of 2. That's 2 ways of doing it. They're both valid, but both examples we're going to explore are public Class C networks. So our counting for hosts example, we have 24 network bits in our example mask, and then the bits that are highlighted are host bits. So we have 8 host bits in this case, and this is also known as a /24. That's called the CIDR. That's the classless interdomain routing. The difference is we just say that we have a 24-bit mask to mean 24 network bits are on. So you just take 32 and then subtract it with whatever your bit is, the bits you have, and that would give you the network, the host bits you have. In this case, we have 8, or you can just count them. So we have 8, so 256 hosts in this network, but 2 are reserved for the network ID and the broadcast ID. Now, because of those reserved addresses, we take the 256 and subtract 2 from it for the network ID and broadcast ID respectively, and then that gives us 254 usable addresses. In this example where we're counting for networks, remember that if it is a public Class C, for instance, if it is still a 255, 255, 255, 0 mask, or /24, it hasn't been subnetted as long as that class is in the first octet that we spoke about a little bit further back, and that it's a /24 mask. This is where it really kind of gets confusing to remember, because it makes a big difference the class of address and the mask you're using. So in this case, this has been subnetted. So keep the 256 in your head. All we're doing is breaking up the 256 in smaller pieces. So for this, we have 4 network bits. So we borrowed 4 bits past the classful boundary, as it's called. So now it's a /28. So we have 28 network bits. We can count those 4 and just say 2 to the power of 4, and that's 16. Or just do 2, 4, 8, 16 from left to right. And we have 16 networks out of that. So we took 256, chopped it up into 16 groups. In this case, we have 16 hosts on each of the subnets we just made. Now, we still have reserved parts of each subnet, though. So each of those 16 subnets we made, 2 of the hosts on each one aren't going to be able to be used. So it's really 16 minus 2, and then we have 14 usable hosts on each subnet. Because in this case, we have 16 separate network IDs and broadcast IDs when we subnet. It's not just one like up here. There's 16 of them. Because each chunk that we just took out of the 256, we still have to know how to identify it, to know what computers are in what group. And that's what we're trying to understand how to do with this. So, classful subnetting will kind of bring it together for us. Again, we have that default network portion and host portion, like a public Class C, and we change the amount of host portion that is in that address to chop it up differently. So all we're doing is borrowing existing bits from the host portion, starting from the default mask. So we have 24 bits here. That's one network with 254 hosts. So in this case, we're not subnetted. It's one network. So here we have 198.51.100.0. That's the network ID, the beginning, from 198.51.100.255. That's all the way to the broadcast ID. And breaking it down, 198.51.100.0 is the network ID. 198.51.100.255 is the broadcast ID. And remember, the network ID, anytime you're looking at a subnet mask, if you take that subnet mask, whatever the network ID applied to the IP address is, put in with the IP address, it has to be 0 with the mask to make up the network ID. It should be all zeros in the host portion. To make up the broadcast ID, it should be all ones in the host portion of the address of the subnet mask. So between those two, though, we have 198.51.101 through 198.51.100.254. That range is the usable address. So that's the usable range for that subnet. So like in the example where we chopped it up into 16 subnets, each of those subnets has these three values: a network ID, a broadcast ID, and a usable range. But they're all separate groups if the computers are talking to a computer that doesn't fall within its own group or subnet. So we're going to take a pause, rewatch that. I know that was a lot of information coming at you. Rewatch the Classless part because you want to have a good understanding of that before we go into the next few parts of subnetting. Yes, there's more, but I will see you in a second. Alright, so now we're going to talk about a different kind of subnetting. Now the kind we just covered was classful subnetting. And what classful means is you're always going to end up with a subnet mask, regardless of if you're using a class A, B, or C. You're always going to end up with a subnet mask that either is 8, 16, or 24 bits. It's going to be in that size of mask. It can't go in between 8 and 16, or 16 and 24, or 24, over to the rest of 32. But the reason is, the reason classless is important is when you need a mask that supports a different amount of hosts and networks that you can't achieve with an A, B, or C default mask. With 8, 16, or 24 network bits, I mean. So here we're going to do the same thing. We're still borrowing host bits, but, so for instance, this is going to be a public class C, we're going to say. So we have a classful boundary at the 24 bit. There's a mark there. And if we borrow 1 bit from that, we then have 2 networks with 126 hosts on each network. The idea in our counting example is the same. We took the 256 that we would normally get with 24 network bits, 256 hosts, and we broke those hosts up into 2 separate networks with 126 hosts on each. And then from there, it's still the same kind of subnetting concepts. So from here, instead of having the 198.51.100 through 198.51.100.255, as we had with 24 network bits, with 25 network bits as we have here, we now have 2. So we have 198.51.100, that's the first subnet's network ID. And then the range of that first subnet is 198.51.101 through 198.51.100.126. This is the first subnet's usable range. And then, remember, the broadcast ID is the end, so all ones are on in that subnet mask. We have 198.51.100.127. That's the end of the first subnet. The second subnet's beginning, all host bits off to 0, is 198.51.100.128. This is the second network ID of the second subnet's network ID. The range of the second one is 198.51.100.129 through 198.51.100.254. That's the second subnet's usable range, and the computers in this subnet cannot talk to the computers on the computers in the first subnet won't be able to talk to the computers in the second subnet unless we use a router, and that's why we're going to go over routers later. But this is the core of what we're doing when we're making these groups. This is what they are. They're just groups of computers that are in subnets. So we can write these two subnets in what's called CIDR notation. And this is quicker than doing it the other way, where we're using dotted decimal notation. In this case, we can summarize all of these values in these two representations. 198.51.100/25 and 198.51.100/128/25. What this does is just uses the network ID value and then gives you a CIDR representation of how many network bits. Same thing on this one, 128/25 at the end. And with that, what you do is why the first subnet's network ID and the second network ID increment like that. This is called the interesting octet. It's the one you count in that can change. How you find it is you have to go back to those bit values. And if we do it here, we see the last bit on its value in our example is 128. That's why the subnets in the interesting octet, the fourth one, increment by 128. This is also called the block size. And this is a source of a lot of confusion as well with subnetting. So that's why it goes from 100.0 in the first network ID to 128 in the second, because this counts by 128 here in this with this mask, okay? So that's this is why subnetting is one of those things that you really have to just do a lot of research. Me explaining it in this course is not going to get it for you. I can tell you from experience. It took me a while to understand this fully, because it's not intuitive. Me just describing this, it's like, okay, I get what you're saying, but you know, it's not very intuitive. So, but this is classless, and remember, this is so we can break the subnets up into smaller pieces and get tighter control over how many hosts and networks we have with the subnet mask. Okay? Again, same thing. Rewatch this section, and I will see you in the next one. Okay, so now, what we're going to do now is pretend we're going to start with those classless subnets we just made. Now, well, different ones in this example, but the concept is the same. We're starting now with classless subnets. And what we're going to do is further subnet those into smaller pieces. So this is VLSM, variable length subnet masking. And a good way to think about it is you're subnetting the subnet. All right? So the subnet has already been subnetted. It gets kind of confusing. But all we're doing here is we're slicing up an existing subnet into even smaller ones. So 3 steps. We're going to start with 192.168.10.0/25. Go back to the class list if you didn't already to jog your memory on it. But remember, this holds 126 hosts. What we're doing is we're going to start at the next network ID. 0 to 128 is the next network ID of this subnet, the first one. And now we're in the second subnet. You can't start in this network ID because then they would conflict with each other for routing and such. But we're doing 192.168.10.128. And now we're using a CIDR of /30. So we have 30 network bits. All right. And this is, we're going to pretend as a public. Well, for this, we're just going from a 25 to a 30. So we're taking this and we're slicing it now into 2 hosts. So this gives us 2 hosts in the subnet. And now our block size, or our increment, is we have 2 host bits left with a /30 mask. So it's 2 to the power of 2, which is 4. So then we take 128 plus 4. And now we get to our next network ID of our third subnet, which is 192.168.10.132. And now we're going to slash that into another subnet with 2 hosts. So now we have 3 subnets out of the 1 subnet we just were doing. All right. So we can have the subnets written as 192.168.10.0/25, 192.168.10.128/30, and 192.168.10.132/30. Now, the whole idea is you're starting from an existing subnet and then making another subnet out of it and then making another subnet out of it. All right? That's the whole idea, and that's why we started with Classful, went to Classless, and now to VLSM. We have one more important thing to talk about with subnetting. Essentially, we're going to put them all back together into one subnet. So I will see you in a second. Alright, so now we have all these subnets, or these chunks and networks and stuff. Now, what if we want to put them back together? Now, I will say the reason this is done is for routing protocols specifically. You're not going to see subnets like this assigned to your computer. All right? This is not made for that. This is made when you have many networks that you have to advertise. I'm getting ahead of myself a little bit, but that you have to advertise and you want to make them one advertisement that encompasses all of them. Instead of having 10 advertisements, you may have one advertisement that encompasses all 10 subnets. That's what we're doing here. We're doing the reverse. We're putting everything back together. So, essentially, we're just combining a bunch of small subnets into larger ones. So in this case, we have 192.168.10.132/29. We have 6 hosts in that subnet. And we have 192.168.10.140/30, and that holds 2 hosts. What we want to do in binary is take the 29 and 30, and we want to make a mask with enough network bits, with enough host bits rather, to actually hold the network bits of the original 2 subnets. So what I mean is a /28 subnet, a /28 mask holds the 30 and 29 masks in it. As far as the bits go, there's not actually 3 masks. We're making a new mask that will encompass these 2. The network bits of the 29 mask and 30 mask will become host bits in this new /28 mask. You see that these, if you look down, are now in the zeros position, the host bits position of the summarized address. So what happens is the summarized subnet's network ID is 192.168.10.132/28, which is the first network ID of this /29 subnet. And the summarized subnet's broadcast address is 192.168.10.147/28. And again, we're counting by 16 on that because that's the bit value of the last bit that's on in the mask. The 28th bit is the 4th bit in the 8th octet, so that's 16. So 132 through 147 holds the range of subnets here. All right, it holds all of those hosts in a new subnet. You see? And again, this is just for routing protocols, but it's a good thing to know because it's one of those things you're going to bump into if you go further into certifications and things of that nature. So, I will see you in the next one where we're going to talk about routing tables. Alright, now with all that subnetting in the network bits and host bits in our heads, now we can actually understand an IP routing table. So this is the process that a router uses to decide how to route a packet. And we're going to go into a little bit more depth on routing tables, but it makes sense here because we just talked about subnetting, and that's the core of how a routing table works, is subnets and network bits. So a routing table just holds directions for each packet, and an entry in a routing table matches a destination IP address and a packet. That's the goal. So when it routes a single packet, the destination address is compared against the entries in the routing table, okay? So the LPM is what we're looking for here. That's the longest prefix match. All that means, in simple terms, is it's just the entry that has the most network bits that match. All right? It just matches. So if that match is found, then that is the route in the routing table that the packet will be routed over. That's the matching route, or LPM route, the longest prefix match. So an example, if we have a packet with a destination address of 192.168.10.130, in this case, it's going to end up being routed by our mock routing table down here of 192.168.10.128/25. That's the route it's going to choose, or path. This is unless the metrics of the routes are changed, but that isn't as common unless, at least for a basic understanding of the routing table, this is how they operate. You can bypass it to make packets go ways they wouldn't normally, but that's later on. You will learn about that. And a default route here is the catch-all route. It happens to be used when no other routes exist that better match the destination address. So it looks like a 000/0. If you open up a command prompt for on Windows, if you do route space print, you will see a default route that's going to point to your default gateway on your computer. But it's a last resort, essentially, and it just matches every destination IP address. Most networks in place have a route like this. So in this case now, the next route in our table is 192.168.00/16. So 16 bits matches the least network bits of our destination address. All right, so we have one that matches all of them, and then we have one that matches a few more than the default, but it's not as good as it could be. See, because that one would match 192.168 of our destination, whereas 0 would match all of it. But we have a more specific one, and that is 192.168.10.128/25. All right, so this matches 25 bits of our 192.168.10.130 address. And that means that is our most specific route. So that packet is going to be routed out of that interface on this router, okay? And that's how the routing process works. The router has a routing table. It compares IP addresses that are destinations with the entries of the subnets it has, the routes, and it's able to route the packet. And it uses network IDs of the subnets to decide this. And remember, you can change the metrics as well. Rewatch this section. Again, you have to understand subnetting before you're really going to understand how IP routing works. And then you need to understand all that to understand how a routing table works. So with that, I will see you in the next one. Alright, so now that we talked about a little of subnetting and a little bit about IP addressing, we need to talk about how do we assign those. Well, there's many ways actually. We have DHCP, static, DHCP v6 for version 6, Slack, and dual stack. So the interesting thing is, DHCP and DHCP v6 automatically assign our IP address and net mask, whereas static with either IPv4 or IPv6, we have to put everything in manually in our computers, what's called their network settings. Now, IPv6 has two ways to assign itself automatically. You have the DHCP v6, of course, and you have the Slack. Slack is stateless address auto configuration. Okay? Now, the other scenario you will have when you're using both addresses together is a dual stack. And this dual stack is when you assign an IPv4 address and network mask and an IPv6 address and its prefix length together in the same network settings on one computer. So again, static is completely manual, but DHCP, DHCP v6, and Slack are automatic. So that's how we assign them. But once we assign them, remember how we have the MAC addresses? How do we figure those out? Well, in IPv4, because IPv4 is a logical address, it can move around from computer to computer. So you might not have the same IP address you had a week ago, even on your own home network, because of things like DHCP. So we keep track of that movement with ARP. That's Address Resolution Protocol. And this just uses requests and replies. And that helps you ask a computer on your network, hey, who knows what MAC address is at this IP address? So in other words, who has this IP address? I don't know how to talk to them. Well, you send that as a request. And the computer that ends up having that address in the broadcast domain, but now we know that's an IP subnet as well, sends back the reply. That reply says, hey, I'm at that IP address, and here's my MAC address. So if you want to talk to me, use those two addresses. It's as simple as that. So once the computer gets that information, it puts the replies information in its cache, the one that requested it. But something very cool and clever that ARP does is the computer that's being asked for its MAC address also puts the computer's, the requesting computer's MAC address in its ARP cache at the same time. So there's like less traffic. It's in one request, but you're actually, the other computer will save that preemptively, at least for a small amount of time, but it may still have to request it. The cache only keeps the information for about 5 minutes. So it does continue in our networks on an ongoing basis. So that was the main stuff about IPv4, but now we have to talk about its successor, IPv6. Now, we're gonna start with the format of this. An IPv6 address, instead of being made up of decimal, being represented by decimal, it is actually represented by 8 hexadecimal sections. So remember, this is exactly the same as a MAC address. So this is a 0 through 9, A through F range. And there is 8 sections of that, and they are 16 binary bits each. So if you do 16 times 8, that's 128 bits. Now, the amount of bits is very important because this is why IPv6 has more unique IP addresses, because there's more unique combinations of 128 bits that you can make versus IPv4's 32 bits. But this is the main driving force of IPv6, is that we need more addresses. So this is one of the main reasons it's being adopted. But essentially, it's kind of just supplementing IPv4 at this point in time, at least in 2020. Now, it's easy to remember because the first 64 bits of the address, or first half, are the network portion, period. When you look at that, the first half, if it's at least default, that's the network portion. The second portion, or the second 64 bits, are the interface ID portion. All right? So the 64 bits, the second part of it identifies the computer itself. This is like the host portion of IPv4 in our subnet mask. The network portion is, the name is the recipe. That's the network part of the address in IPv6. All right? Now, this is an IPv6 address. It's 2001:2600:4000:1000, and then a group of 4 zeros, group of 4 zeros, group of 4 zeros, and 0001/64. That /64 at the end And by the way, this is how you look at this address. We have the first section, second, third, and fourth. This between the 1000 and the first group of 4 zeros is the network portion. This next portion is the interface ID. So the interface ID in this interface, in this IPv6 address, is all zeros and then a 1. And that identifies one computer. All right? Now, the /64 is the prefix length. Just like a CIDR in IPv4, this is how many bits are assigned to the network. The ones that are left over are interface. So they're their host. The same way. So the prefix length with IPv6 is just like the subnet mask in IPv4. So don't get tripped up about that. That's what it is used for. The main difference is we can represent more computers in IPv6. That's why we have to have a different format, because we have to have more values. But if you don't set the prefix length, this is the equivalent of not subnetting in IPv6. The default is a /64. This is like the classful subnet mask, or the default classful mask, remember? From those public and private ranges. If you don't subnet your network, that's the default mask. Now, it's not as important as it is in IPv4 to subnet in IPv6, at least for it's important for different reasons. It's important for things like security and scaling of your networks. For now, at least, it isn't as important for address utilization. All right, and that's one of the big reasons we used VLSM and things like that, and CIDR and everything in IPv4. You should always subnet your networks if you can, because when you subnet, it gives you better performance in a network and it gives you better security in a network. So, all right. So first off, pop quiz. Do you remember the IPv4 address type that went everywhere? You got it? Did you say broadcast? Good. If you said broadcast, you're right. Because guess what? The good news is there's no more broadcast in IPv6. There's only unicast and multicast. Now, there is one more, but we will get to that. So, we only have two primary ways to send packets in IPv6. So there is unicast, which is that one-to-one. It's just like me talking to you in this video. There's multicast, which is one to a group. Remember, the groups subscribe and or join a group of computers that want to receive the information. Otherwise, they ignore IPv6 or 4 packets, v4 or 6, that are destined to that multicast address. That's how they subscribe. They either listen to that or drop that packet and ignore it. So, the IPv6 does have many address types. This is similar to how they were reserved in IPv4. You remember the loopback and you remember the APIPA? Those were reserved addresses. This is similar to that, but because there's no broadcast in IPv6, groups of multicast addresses are assigned for many important functions in IPv6, such as DHCP and Slack and other things like that. You just can't magically send to broadcast and get a function to work. You have to send to the specific multicast address for that to work. So the first address that's very important is called a global unicast address. And these always start with 2001. Well, technically they start with 2000, but there's an entire range for this type of address. And here is an example. And again, you can remember, you got the first, second, third, and fourth section. What was that? The network portion, that's right. And you have the last four, remember what those were? Interface ID, right? So the interface ID identifies the one computer on the network ID, the network portion, rather, identifies that IPv6 network specifically. that group of what? Group of MAC addresses. It's the same thing. It's just a different representation. Now, that's a long address, isn't it? Well, it would be hard if we had to type that out all the time. Luckily, we don't, because when they created IPv6 back in 1998, they thought that, hey, maybe administrators and engineers and end users at their homes and people in labs and stuff don't want to type all that. So we have a compression rules. There's two rules. One is if a section has what's called leading zeros, you can remove them. So it's like this section here in the middle of the global unicast address. You have 0011. Those two zeros are leading zeros. So, well, the first zero, I'm sorry. So we can get rid of both of those zeros. So both of those zeros are leading zeros in that section. You can remove them to shorten the address. There's another thing too. If you have consecutive sections of all zeros, so like 8 zeros in a row, you can go ahead and concatenate them or make them one, like shorter, truncate them with a double colon. All right? So this is actually how it looks. So the highlighted sections down below the full address are parts I have compressed by just looking at the address and applying the compression rules to it. This is a good thing to practice because you can see, you'll see over time different representations of it. You're not always going to see the full thing, and you're not always going to see the full compressed one. You're not even going to see the same like methodology for compressing them, because you don't have to compress if you're writing it in documentation or typing it. You don't have to compress it all in the same way that you might expect. So you got to be prepared to see all kinds of representation. So from here, though, the first highlighted section, the third one in the network portion, I've taken off the leading zero. That's what I did there. And then it's 100. 1200, I can't really do anything. There's no leading zeros. It's not a consecutive group of zeros. So you're kind of stuck. But at least we have some things we can do to help. So the two highlighted ones are all that's left over from the leading zeros here in the fifth section there. And I took those out. And then the 6th and 7th sections were zeros. So I truncated them. I made them smaller with a double colon. And the last section there, the 00A1, those are leading zeros. So I take them off. Just drop them off the end. And then you get A1 at the end. So we get a shortened address because of this. So to reverse a compressed address and make it the full representation again, what you have to do is remember there's supposed to be 8 sections, okay, with a full address. You look at every section. Any section that does not have 4 hexadecimal characters in there, assume that it has a leading zero compression. All right, so in this 100, the third section, I'm going to look there. I'm going to be like, I know there's supposed to be a 0 there. So I put the 0 back. And then 1200's fine. I look at the 1, 1. That's 2, not 4 in that section. So I know there's got to be 2 zeros. So I put the 2 zeros back on. And I look at A1. That's 2, isn't it? There should be 4. So I put the 2 zeros back on. So then I reverse the leading zero compression. After I reverse it, I count all my sections that have 4 hexadecimal characters in them. All right, let's do that. So we have 1, 2, and I'm reading the compressed line, by the way. We have 1, 2, 3, because we put the 0 back in, 4, 5, we put the zeros back in there, and we have 6. Well, I know there's supposed to be 8 sections, and I can't put any more zeros back. There's no more leading zero compression. That tells me a very important thing. It tells me there was 2 sections of 4 zeros each. So I add back in 2 additional sections of the zeros to get my final two sections. So then I would just take the double colon, put the 8 zeros it's missing, so the two sections, and then I get my full uncompressed IPv6 address. Now that's one of those things like subnetting. You just gotta keep looking at it, keep practicing it, and it will become second nature for you. Now, these reserved multicast addresses, I put here some of the most common ones you're gonna interact with. And you may already be interacting with them if you have dual stack on your internet connection. Just didn't know what they looked like. So we have FE80::1. And this range is the link local address. And link local means it can't be routed by a router. It stays in its broadcast domain or subnet, okay? It's a group. And all you can do with a link local is reach devices on your same broadcast domain or link. All right? That's all you can do. So you use this for only that purpose. You can't get to Google using this address. So, the next one, excuse me, is in FF02::1. This is the all nodes multicast address. And the all nodes multicast address has to do with resolving things like the MAC addresses in IPv6. It's very fundamental in that. Same thing with FF02::2, but this is to communicate with a router in IPv6. So the all nodes multicast address is when you want to communicate to do things like get the MAC address of another computer. This is one of the reserved groups in multicast with IPv6. If you want to communicate with an all routers multicast address specifically, you do FF02::2. And where these addresses, where you will see them, is in the destination address field of an IPv6 header. All right? So this is where you will see them at. And it uses a combination of the link local address and the all nodes multicast address or the all routers multicast address, depending on what it's doing. So the link local and the multicast address ranges work together in IPv6 for various services. Now the last address type is an anycast address type. Anycast is very different compared to what we've talked about before. Multicast is for the group, as we said. Unicast is one-to-one. The interesting thing with multicast is it's like a unicast and it's like a multicast address at the same time. What happens is you can assign these anycast addresses to a computer. This is normally not a home computer. This is normally a special one called a server, which we'll get to those in a little bit. But what happens is when you request that resource on the internet, you only go to the one address. That's the only thing you have to type in is the one address, but it gets the server that responds is the address, the server that is closest to you. So you don't have to worry about any of that. It automatically finds the closest server and will send that reply from that server. But it figures that out without having to change the address. It just kind of shares it across all of those devices. So that's a very interesting thing with IPv6 that we didn't have in IPv4. The closest thing in IPv4 is CDNs and things like load balancing for that. But it's completely different in IPv6. Now, the meaning of the network portion. So each of those four sections does have a specific meaning. So what we do is take the whole address here, and we're going to tackle all four of them. The first section first. So the 16 bits, 2001, because remember, that's hexadecimal. So that's really 4 bits, all right? So that identifies the registry, and the registry assigns IPv4 and IPv6 addresses all over the world, all right? There's different registries for all parts of the world in its different countries. Now the second part is 2600, and this group of 16 covers the ISP. That identifies the internet service provider, and that internet service provider, excuse me, got that address from a registry. So the third section, 4000, identifies the company, and this can identify many different service providers, for instance, or websites you're accessing, things of that nature, but it helps you by identifying the company that's connected to the ISP. Now, the fourth one has to do with the prefix, but this is the subnet part. So this is the part you and me can break up into smaller chunks, just like with IPv4. It's a little bit different, but it's very similar. You still basically have kind of like network IDs and ranges in there, but you have many more ranges when you break IPv6 into subnets. But that is what identifies it. So what you would say, if you were trying to represent this, is you would say, hey, I am on the 2001, 2600, 4000, 1000 network. My address on that network is 0000, etc., 1/64. And that tells you everything you need to know about what network you're on. All right? So that's how you say that. It's a lot harder to say than IPv4, but I mean, there's more values in it to have to say. But that's how it's laid out. So remember how ARP gave us the MAC addresses? In IPv6, it doesn't use ARP because they reinvented it to use multicast. So they had to make something different to take advantage of that instead of broadcast like ARP uses. Now, NDP, the Neighbor Discovery Protocol, is actually a set of protocols. It uses things like ICMP v6 inside of it, which we'll get to much later. But NDP is the common discussion term to refer to that. But understand there's other protocols. There's no NDP protocol. It's just a name for other protocols that allow it to happen. But this is really the same concept. It uses requests and replies, and with those it maps the two addresses together, meaning the IPv6 address to the MAC address in that broadcast domain. So the IPv6 and MAC address, the IPv6 address and MAC address, that reply gets put in the requesting computer's NDP table this time. Same thing, the person that received the request for that IP address MAC address mapping can put the source MAC address in their NDP table as well. They still time out over time. But remember, with the NDP, we're using this address, FFO2::1, and we're utilizing this address. There's more to it than that, but it is quite complex. It's confusing when you're first learning about the finer details, but just for now, know that it's the link local that's used and the all nodes multicast address. Okay? So, that's how that works to get the MAC addresses. So next, we're going to go into DNS, or the domain name system. All right, so after we've covered the IPv4 addresses and IPv6 addresses, you're probably wondering why your browser says something like www.example.com. Well, this is because of DNS, or the domain name system. And similarly to how ARP and NDP work, this uses a process of requests and replies. But instead of mapping an IP to a MAC address, this maps domain names to IP addresses. So we already know the domain name we want to reach. We just have to get the IP address in order to send packets to it. So, like before, the reply is placed in your DNS cache when you request. And how this is organized is it's a hierarchy. it goes root name server at the top here, root name servers. Then you have top level domain servers. Then you have second level domain servers. And then you have upstream servers. And finally, you actually have the servers at your network. So like on your Wi-Fi router. So it's a hierarchy of TLDs and subdomains, and all that together manages the domain name records on the internet. Originally, this was one host file on one server that everybody had to make sure they had the latest copy of. So it wasn't as scalable as it is today. But these TLDs, they're things like .com, .org, .net, and there's many others today now. But the subdomains are to the left of the top-level domain. So you have example.com, you have example.org, example.net. Then you can even add a portion called the CNAME, which is www.example.com, things like that. But all of this is just mapping to an IPv4 or IPv6 address. That's all it is. So the records hold different information in DNS. So there you can have multiple records for the same domain, depending on what they're used for. So an A record holds an IPv4 address that maps to an IPv4 address. A quad A record holds an IPv6 address. An MX record is a mail exchanger record, and that holds information about the mail server for a domain. There's others, like a text record, and that holds different things like SPF, that's Sender Policy Framework. That's something used by mail servers, but there's many reasons that the records are useful. But the main idea about DNS is it just makes it easy to access IP addresses. We can just remember the domain names instead of remembering the IP addresses directly. Now, especially with IPv6, we saw how long that address is, so DNS is very helpful. So all that happens to find this IP address is that you send a DNS request on your computer right now in your network. Well, you're asking, if it's IPv4, for the A record of like example.com. This goes to your LAN's local DNS server, and that's on your Wi-Fi router. So after that, that local DNS server asks upstream DNS servers what that query is, because it may not know. It might not have it in its cache. So the upstream DNS server, if it doesn't know already, will ask the root name server about the part of example.com, and this is a full query. We're assuming there's no caches being used to speed the process up. It will ask the root name server about the .com top level domain. So all the root server is going to tell it is where the top level domain server is for com. Okay? Now, from that response, then they know, hey, the upstream will ask, the upstream knows who to ask about example.com. So then it asks the server for example.com what the A record is. So this is the second level domain server, the SLD. So after it gets that entire answer of example.com, it caches it. So if someone else requests it later, it can bypass that whole lookup process and just give the answer immediately. But after that, it sends the reply back down to the LAN's DNS server over the internet. And when the LAN gets it, it caches it just like the upstream server does. And then it sends it back to your computer because you started the request. When your computer gets it, it then takes the A record for example.com, in our case an IPv4 address of 93.184.216.34, and it caches it. So the next time your computer wants to access that domain name, it knows immediately without asking DNS again. All right? So now we're just going to set up a quick lab and talk about how and see how this looks in practice. I'll see you in the lab. All right, welcome to our DNS lab. So all we're going to demo here is that we can resolve DNS and what that looks like. So let's do an ipconfig. And here in my lab network, I have an IPv4 address, and I have everything set up for our lab. So we're going to do ns lookup. And what I'm going to do is search for Google. I'm going to ask the DNS server I'm connected to what the IP of Google is. So as I query it, we see the server 192.168.1.1, and again, this is speaking the DNS protocol. I'm the DNS client, and the server is the server part of the equation. And when I ask for google.com, that's a DNS query I sent, and the server sends a DNS reply. Now the IP address down below there is a 1.1.1.1. That's the A record for google.com. The other is 1:::1, and I'm going to leave that as homework for you to expand that IPv6 address into its full equivalent, which I'm sure you can now. But from here, if we resolve example.com, you see that has IPv4 and an A record and a quad A record. Same thing with wikipedia.org. All right. Now, I will say, if you resolve these on your network, you're going to get different responses. The reason I'm getting responses like this that go 1, 2, and 3, and then the IPv6 equivalents, is because this is a lab network, and I've specifically put in DNS records to map to those domain names like that, just for the purposes of this lab. So for the subdomain part, the CNAME, if we do info.example.com or media.wikipedia.org, see? And then if we do like smtp, gmail.com, we get the same answers, but it's just a different query that we're sending over DNS. So this is what DNS does. It just maps IPv4 and IPv6 addresses from friendly domain names to their IP addresses. So then we can use IPv4 and IPv6 to send our packets to them. All right? So I will see you outside of the lab. All right, so now that we talked about resolving the domain names to IP addresses, now we're going to talk about how we assign them. Now, specifically, we're going to first talk about DHCP, that's the Dynamic Host Configuration Protocol. And this, again, uses requests and replies, but now it's using them to give a device network addressing information. Now, there's required information and there's optional information that a DHCP server can hand out. The required information is the IP address for your computer, the subnet mask, the default gateway, and the DNS servers. So the IP address, of course, is that logical address that you're going to be assigned one of. The subnet mask is going to help you figure out what group you're in, or IP network, and we talked about that before. But the default gateway is if you want to talk outside of your group, essentially, or your IP subnet. And the DNS servers, now we know, they resolve those domain names to IP addresses. So that's the required information that any DHCP server gives you, at least for IPv4. In IPv6, it's slightly different, but it's not a big deal. It'll be easy to figure out. And the optional information is things like an NTP server or a TFTP server, reserved addresses. This is known as DHCP reservations. This is when you want a certain device to get the same IP over and over, but still have it be dynamic. So you don't have to go to each device and statically put something in. That's why we use DHCP. It's a lot more scalable, especially in a bigger network, but also in home networks. We have a lot of devices in home networks nowadays that all use DHCP to get addresses. So the process goes like this. You can remember it by the acronym DORA. That's Discover, Offer, Request, Acknowledgement. And it goes like this. A new device is plugged into the network in step 1. All right? So this first thing it does after that is sends a discover message. In IPv4, this is a broadcast. So it's going to, at layer 2, with MAC addresses, it's going to all Fs. At layer 3 with IP addresses, it's going to 255, 255, 255, 255. Now the layers are going to make sense later. I'm going to approach that toward the 3/4 about into the course, just as a little different because it'll make more sense after we cover all this. So after that, the first DHCP server to hear the discover message sends back an offer. So we've already done discover and offer with the first 2 steps after we plug it in. And if we like the information we're being offered, we send a request message back to the DHCP server. All right? So what that says is, hey, can you assign me that information? So after this, the DHCP server acknowledges, so sends an acknowledgement message, and then it creates a lease. And that lease just allows us to use the information for a limited amount of time, so it's dynamic. And then if we don't renew it, obviously it expires. Or we just can request a new one. Now with IPv6, this is only one of the methods for getting an IPv6 address automatically, and this is SLAC, stateless address auto configuration. Same concept, we plug a device into the network, but this time this device sends a router solicitation message. That just means it's saying, hey, does any routers that can hear me, what network portion are we using here? So what's the network portion of the segment? You remember what that is, right? The first 64 bits of the IPv6 address. So if a router is there to hear it, it responds with a router acknowledgement message. So this includes the IPv6 network portion, so the first 64 bits, and it sends that back on the interface that received it. All right, so that's where it sends it back from. Now your device uses the network portion of that reply, and then it creates the 64-bit interface ID in addition to using the network portion in combination with it. So it assigns it to the interface normally that it requested that it sent the solicitation message out of. But it creates the interface ID portion. Now, normally you use the interface's MAC address as part of the criteria, as part of what you put inside of the address. But you use EUI64 to do this. It's extended unique identifier. And it's 64-bit, hence the 64. Now you can use that automatically, or you can statically assign an interface ID, just like the DNS addresses the IP addresses that were 1::1. I statically assigned that IPv6 address. So this didn't use EUI64 in that case. But before you can use this new address you made, you have to send a duplicate address detection message. And that make sure no one else is using the address, because otherwise it wouldn't know with NDP which MAC address actually belongs to the IP address. It does that with IPv4 as well. You can have a duplicate where ARP wouldn't know what IP and MAC belong together. But Slack does assign a default gateway and a default route, but not DNS servers. Now I'm going to pause here because it depends on the implementation if that's true or not. It used to be, but some implementations actually assign name servers. They've improved things over the years, and this isn't always as true as it once was. Now, DHCP v6 does assign DNS servers. The difference is it creates the lease in the same way, but it also uses Slack to assign the address, so it kind of uses both to do this process, but it just keeps track of it better. All right? So then you can request the same address easier because you have state for that address. But any router that has IPv6 running, they will send these advertisement messages out that have the network prefix in them already. So anyone on the broadcast domain or subnet will hear this advertisement and be able to automatically use the Slack process to configure themselves. So it'll get the network portion, it'll use EUI64, and then it will have itself an IPv6 address, specifically a global unicast IPv6 address, by the way. That's a very important distinction. So now we're going to talk about DHCP. and I will see you in the lab. Alright, so now in our DHCP lab here, we're going to run, what we want to do essentially is get our dynamic address. So we have IPv4 at this point, and we're going to do ipconfig/release because I already had one. So this is that lease. We can actually tell the DHCP server if we want to get rid of the lease or not. And if I clear the screen and then do ipconfig/renew, we can get a new lease. That's discover offer request acknowledgement that just happened. So now I have the IPv4 address 192.168.1.100 automatically assigned. I have the subnet mask of a /24, and I have a default gateway. Now, I'm going to tie this in right now. The reason I have... oh, by the way, let's do this as well. ipconfig/all. Here we go. Now, the reason you see DHCP is enabled and auto configuration is enabled, that means Slack, okay? So, I have my IPv4 address in my lease. I have my mask. It tells me when my lease was obtained over DHCP, when it expires, which is configurable on the server, but we're not talking about the server today. And we have our default gateway. Now, I had a lease before, that's why I have two. You won't have that in your network. And then we have our DNS servers that we assigned, and you can choose those. Now, the reason we have IPv6 information as well is because of Slack. I've set something up on the server so it assigns the network portion, and this is what I mean. It was not a DHCP v6 server I used, it was a router advertisement software, and it still gives you network prefix, default gateway, and name servers. So it depends on the software you're using, okay? So that's why that's like that. But what happened? We sent a router solicitation message, got a router advertisement, and this got us the 2001 portion of the address. In our case, I've assigned 2001::, as the network portion. That's it, and then the rest of it was generated. In this case, not with the UI64, but in a different way that Windows uses. And it's able to get that address. That's why it says temporary, because it's not static. This is automatically assigned. The link local address is our address to communicate again in our segment, and this is called the %16 here is called the scope of that address. So that's basically what interface this address is a part of. And that's how we have it all set up here. But this is how we can dynamically get an IPv4 address and its information, and an IPv6 address and its information. So I will see you outside the lab. Alright, so now we've talked about how to map MAC addresses to IP addresses with IPv4 and IPv6, and how to resolve domain names to IPv4 and v6 addresses. Now we need to talk about how do we use those addresses to get the information somewhere else. So what we're talking about here is routers, and how routers help us connect our groups of computers together. So they connect the subnets together in those broadcast domains. So what they do is they simply connect different broadcast domains together, period. That is the main job of a router. Now, to do this, they break up broadcast domains, which I know doesn't sound intuitive, but the reason they do it is because a router has different networks on each interface it has. So every interface it has is in a different network or broadcast domain. So we configure different IP networks on either side. Now, when it's set up like this, and every router is, it divides computer networks just like walls in a building divide rooms, see? So that's what it's doing. But, I mean, if we didn't have routers to do this, basically every computer in the entire world could all hear each other at once. So, I mean, routers play a very important role in routing traffic, but also keeping that traffic separate in a way as well. Because routers don't route traffic where it's not needed, only where that packet is best routed to, like how we talked about the routing table earlier in subnetting. But that's what routers help us do. Now, they use routing tables, and what a routing table does, and your computer has one too, it's just a more basic one, is it keeps track of directly and indirectly connected networks. A directly connected network is when the router has an interface that has an IP in that network that is directly connected. Indirectly connected means that the router can reach that network, but it has to use other routers to do it. That's where routing on the internet becomes more complicated. Even in enterprises too, this happens. So that's how they keep track of those two different types of networks, though. They put them in their routing tables and their entries in there. So because of it, it's basically their big map of the world, but it's just a small little subset of it. But each routing table entry, all it is an IPv4 subnet or IPv6 subnet. Or if you want to think of it, it could be an IPv4 subnet and an IPv6 prefix. But remember, they're the same thing. It's going back, fundamentals. It's just that group of MAC addresses. That is all the entries in a routing table are essentially, are just groups of computers that the routing table knows how to route to. Now, this also includes how many routers away that subnet is, because if it's indirectly connected, it needs to know how many routers do I have to use to get to this network. That's what indirectly connected means, that other routers in its path know about that network. So that's what we mean by how many routers away that subnet or network is. Now, there's also a metric, and that means how preferable the route is. This could be in terms of hop count. This could be in terms of bandwidth of that connection, and other things like that. It can also be in terms of something called administrative distance, where you as the administrator can even choose what routes you prefer, and that changes the metric. There's many ways that you can do that and reasons. But the subnet in the entry, as we said, if it's directly attached, you're right there already. You don't have to use other routers to reach it. But if it's a remote subnet, the entry will just point to the next best router or hop to get to that network. It doesn't get it to its final destination IP address, but it gets it to another IP address of another router that can get it closer to that network. So that's the amazing thing about how routing is working. But the subnets can also have multiple ways to get to it. You could have one subnet with 3 different paths that are all ways to reach it. The internet as a whole, around the entire world, has many different paths to get from point A to point B. They have directly connected, indirectly connected routes, and other things like that. So there's all of this is just on a bigger scale with all the routers that make up the internet. Now, you can also put routes in a routing table manually. And when you do it, it's called static routing. And this has advantages. You control hop by hop where your packets go, at least from the routers you maintain and administer. But you also have to keep track of every network you have, whether it be IPv4 or IPv6. If you want to reach it, you have to put it in a routing table. You use static routing if the network is indirectly connected. If it's directly connected, the subnet will automatically be put in the routing table. Okay? If it's indirectly connected, you either have to use static routing to reach it, or you can get them by advertising your connected routes and exchanging their connected routes for your connected routes through a routing protocol, which means that routing table information from router A can be advertised automatically to router B, and then router B will put that routing table information inside of its own. So then dynamically it can populate its routing table. So that's another way to scale this up So, because otherwise we'd have to go to every router on the internet and statically put in routes. That would not be fun or scalable. The internet would be broke all the time if it was ever fully finished, especially today's internet. In the beginning, it was done statically. There was no routing protocols to speak of, but nowadays there is, and I'm glad there is. So, how do ARP and NDP fit into this? Well, Ethernet can only be in one broadcast domain, okay? It doesn't go to another broadcast domain. So, it has to... The reason that is we can only talk to computers we can hear in our own group, in our own subnet. So, if it turns out that the computer's in another broadcast domain, we can't use ARP or NDP to get to it. We have to use our broadcast domain's router, which is also called a default gateway in our network. So what we do to make this decision is you use your computer automatically uses the assigned subnet mask from its network settings. It turns that mask into binary, like we did before, and then it takes the destination IP address you want to reach and turns that into binary as well. And then it puts them over top of each other. And if the destination address has enough bits that match the mask, and it fully matches the mask correctly, basically it figures out, hey, does this IP address fall within, you remember these terms, the network ID and the broadcast ID? That's what it's checking. And if the destination IP address doesn't fall within its subnet, by the usable range of its subnet, it sends out to its default gateway. So it knows it has to send to the default gateway for that. So that means it's remote. So we use ARP, an ARP request, or an NDP request to get our routers or default gateway's MAC address, because that is the only computer that knows how to reach other networks in our broadcast domain. So it's the only one we can hear. So we get its MAC address and then send a frame to it with its destination MAC address. But if it's local, in other words, though, if it's part of our own network, we just use ARP or NDP to get the MAC address we want to talk to directly, just like before with ARP and NDP, how we spoke. Alright, so now, how does the router actually operate once we've decided we have to send traffic to it? Well, a router uses the destination IP address, and it uses that with its routing table. It compares the routes in order to find the best route. So remember, that longest prefix match. That's what it's looking for when it's trying to route the packet. So when a router forwards a packet, though, it takes the packet in on one interface, like on your LAN, on your home network, and your Wi-Fi router sends it out your WAN interface, a second interface. All right? Any router does this. It's just that some routers are a lot bigger and more powerful and have different types of interfaces on them and things of that nature. So what happens is sometimes there's other protocols than Ethernet. And I know we haven't talked about it this far, but I'm going to drop it in here. That there's protocols like Ethernet, there's protocols like DOCSIS for cable modems, and other protocols like that. And sometimes the routers have to switch the protocol in use. So the packet stays the same, because that protocol like Ethernet, it carries that packet, remember? And DOCSIS can carry that IP packet. So sometimes the routers have to switch that protocol that's carrying the IP packet, essentially, that envelope, basically. If it comes in a red envelope, it may send it out in a blue envelope. That's essentially what we're talking about here. That means it makes a new layer 2 frame for whatever that interface's connection type is. Okay? That's called the layer 2 rewrite. It's very important to remember in any type of networking you're doing. And now, in addition to the rewriting of the packet, so we're changing, hey, this packet was in a red envelope, it's in a blue envelope now, that's the rewrite, we send it out. Well, you also have to keep track of how many times the packet has been routed. The reason is preventing loops in your network. Because otherwise a packet could be routed forever and never get to its destination. That takes up a lot of resources and bandwidth on the internet if that happens, which is why it can't happen because of time to live fields. So we route the packet, but we take one away from the time to live field. It can go from 0 to 255. But when it gets to 0, though, it can't be routed any further. Same thing with IPv6. It has a hop limit field. It gets 1 subtracted from its value when we route the packet. And if it's 0, you're out of luck. You can't be routed anymore. So if no routes exist, here's another thing that can happen. Sometimes the routing table just does not have any routes, not even a default route like we spoke about before. And when that's the case, the router has to tell the sender that it can't reach the destination, okay, that packet's going to. So the router sends back a destination unreachable message to the sender. And I mean, that's not good, but at least it informed you it couldn't get there. Now again, a time exceeded message is another message that routers send. And that is sent back when the time to live of a packet, or the hop limit in IPv6, the time to live in IPv4, is 0. But if the router processes it, and like if it comes in with 1, but then it tries to route the packet, time exceeded, and then it drops the packet and it sends this message back. So these are not inherently bad things. These are what routers are supposed to do. It's part of what's called ICMP, the Internet Control Message Protocol, and we're going to get into that in a little more depth later, and you'll understand why routers do these things a lot better once we get into that. So to round this section out, we're going to have a router lab this time. So we have two computers here on two separate networks, and they're going to route. The router is going to route their packets between each other. We're going to look at the routing table lookup. We're going to look at that TTL hop limit subtraction, the decrement. We're going to look at the IPv4 and v6 forwarding operation. And in doing this, we're going to see that the frame changes. We're going to see the ARP request and reply process and the NDP reply process. So we got one PC on the 110/24 network. PC2 is on the 222/0/24 network. And R1 has an IP address on each of its interfaces that belongs to each of those broadcast domains. And then once we turn on routing, which will already be turned on, it will forward the packets based on the destination IP address. Really simple routing table to look at and a really simple network. But this is how every router on the internet works. This is all it is. Looking at that destination address, sending it over. There's more advanced things, yes. There's things like MPLS, but it's still in essence routing too. But it's awesome. You can go on forever in computer networking. There's so much to learn. But this is your core. Focus on IP routing and the switching and everything else. So I will see you inside the lab, okay? All right, welcome to our router lab. So the first thing to know is that we have one device here, and this is the 1112, and he's on a /24 subnet mask he's configured with. And this guy's on the opposite network. They can't talk to each other. This is why we have a router involved. So this router has one interface of itself on the network of PC1. Another interface is on PC2's network. So if we look at ARP right now, the only addresses it knows are the two connected interfaces. It hasn't had to communicate yet with anything. Now if we look at TCP dump on the first port, which you don't gotta worry about that if you don't want to. If you do, you can follow along. So then we're gonna ping 22222. All right. No route to host. What does that mean? Well, it means that we don't have a route to get to that network. See, do you see a default gateway, remember? The 0000/0? I don't see that. I just see a connected route. So let's go and put that route in real quick. just like that. And we'll restart our routing. And now we'll try to ping again. Okay. Still not getting through. Now, the reason it's not getting through is the router, we already see our ARP process. And now the router looked at its routing table, and it found a route for the 2220/24 out of EM1. It sent it over there just fine. The reason it didn't come back through is because PC2 over here doesn't know about the 1110/24 network. So if we put in a default route for that network and then restart, now we're going to monitor the packets on this interface. If we go over here now, oh, that looks more interesting now, doesn't it? So now we get packets, and if we switch our interface to look at the other network, now it's routing on both sides. So what is happening is the router's bringing this, we're doing an ARP request and reply for the router's MAC address right here. Okay? That's the only thing we can hear in our broadcast domain. And then the router is maintaining the MAC address for 1112, but he looks at layer 3 at the destination IP address 2222, compares it to his routing table, and then sends it out that port that is connected to PC2 on the other network, this other group or IP subnet. Now PC2, when he routes it back to us, he's looking at his routing table, sees that this IP address doesn't fall in his subnet, and then he sends that out of his up to his default gateway, and then the process repeats. So while that's repeating, you see that the router took off 1 from the time to live and made it 63. And then if we look at the router's ARP cache right now, we can see it has its own addresses, but it also has the 2 MAC addresses of the clients it's connected to. 1 for each broadcast domain. And then it's looking at its routing table to be able to find what routes. All right. Now, we'll do one more real quick with IPv6. I'll see you there. All right, welcome back to the router lab. So now we're working with IPv6. So to get acquainted, we're going to open this interface here, and we have one interface on our router that's 2001:/64. That's the network it's a part of, and it's 2001:1. So it's all zeros and then a 1 in the interface ID portion. On the other interface, it's connected to the 2002:/64. So this is going to route between, if we look at the IPv6 routing table, because you can have both with a router, we have this network here, 2002/64, that's EM1, and we have 2001:/64 in the routing table that goes to EM0. So what we're going to do is listen for some traffic on EM0, and then we'll go over to our client. So what we want to do is ping 2002:2 from the PC that has 2001:1, because they're on different broadcast domains or groups. So we're going to go ahead and, so I started a capture here on PC2. We're going to do ping 6 2002:2. No route to host. Well, let's examine the routing table on this machine. Alright, there's no default route, I notice, but there's also only one connected network in this table for EM0. Remember, it does the same thing. It takes the network prefix and compares it to the prefix length this time to find out if it's on the same network. It's not in this case, because when you compare that to a /64, they end up on different networks. So what we're going to do is go into our configuration, and all you need to know is that I'm giving it a default route, and I'm going to restart that part of my system. Then I'm going to check again. Now I have a default route for everything that's not on my IPv6 network, on that subnet. So now if I ping 6, 2002::2, and then it almost goes all the way through, I get very important things that happen. It went through the router, but it went down here, and you can see I had to get the gateway address, and once it got down to the other segment, PC2 had to ask for the address of its gateway, because it doesn't know the gateway, the MAC address of it. But if we look at the NDP table on our router, it has not only its own MAC addresses for the interfaces it has, it also has the MAC addresses of its neighbors on that link. So it has 2001::2 and 2002::2 on the other interface. So because of that, though, we can open that capture back up. And what's happening here is you can see that the clients on the outside have their gateway MAC address, stays there for a certain amount of time, just like ARP does, but it does the same, serves the same purpose. Same thing over here. But we don't have a route on this guy, and he can't get back. Doesn't have a default route. He only has that connected route, just like on PC1 to begin with. So we're going to add this route in. This is the importance of routing, why I'm showing this. And then we're going to restart. And now let's check it. Now we have a default route to 2002::1, our IPv6 gateway, out of EM0. So now if we run that capture, and if we just do that ping again to 2002::1, we get replies. And you notice how the hop limit is decreased by 1? It's the same concept. Because our router up here routed it, even though it was IPv6, it works the same. And if we look over here, you see 2001::2. I didn't show you this for IPv4, but it is the same. We're going to turn on to show the MAC addresses. So on this side, what I want you to see is that the source 2001::2 going to 2002::2, the source MAC address, it ends in 62F3, okay? But what I want you to see is when we look over on this side of it, if I use the right command, the MAC address here, the same packet after it's routed out the interface that is closer to this network, that matches the route that was selected for the packet, for that destination, the MAC address has changed. This is the layer 2 rewrite. What it changed to was the MAC address of the router's second interface. And this happens constantly. This doesn't have to be the destination network. It rewrites it either way, even in IPv4. So that interface, it rewrites, sends it out the other segments. Because remember, the clients on each side can only talk to their router in their broadcast domain. So that's why that has to happen. But now that was the end of our router lab, and I will see you in section 5. All right, congratulations so far, because now we made a LAN. So now we know about switching, we know about MAC addresses, routing, DNS, ARP and NDP, and IPv4 and 6 and subnetting, and how we route packets. So now we know quite a bit about a LAN and a little bit about how we use the internet from that LAN. Next, though, we need to talk about other things that our computers and their applications use to actually take advantage of that routing and the domain resolution and MAC addresses and all of that. So I will see you in section 6. All right, welcome to section 6. So you remember so far how we've talked about switches and frames and how they use MAC addresses. And we've also talked about how routers use packets and they have IP addresses in there that they use. Well, now what we're going to talk about is what we use to carry our application's information. All right? So this is basically what things like your apps on your phone, your web browser, things like that use to carry useful information. So, like things like a web page or images or text, anything your device sends over the network that becomes a signal, as we had talked about in the beginning, has to be encapsulated in one of these protocols. And it's needed, and we'll see why as we delve in. So, you remember the IP, so Internet Protocol. That doesn't make sure data arrives. So this helps IP out to make sure the data is organized. So there's 2 different protocols for this. And again, they help the data from getting lost and mixed up. One of them does, but I don't want to get ahead of myself. So we have TCP for this, that's Transmission Control Protocol, and we have UDP, User Datagram Protocol. So TCP encapsulates data, which in this case is the application's data. So these are things like HTTP. This is that HTTP data is being stored inside of either a TCP segment or UDP datagram. We'll know that there's a difference coming up, but this is where it's stored. So TCP encapsulates whatever your application's data is into segments. Segments, remember that. We're not dealing with packets or frames here, we're dealing with segments. UDP, on the other hand, puts the application's data in datagrams. And I didn't mention this before, but IP packets can also be called IP datagrams. They're very similar, they just use IP addresses. Now, TCP, its whole job is to send the application's data in a reliable fashion. Now, it does this by having state before the 2 endpoints of the connection on the network send this data back and forth to each other. So they have a state. The state is established. All right? That happens before sending any of their important data. So TCP may really make sure the data doesn't get lost or mixed up. Now, this connection that is established is called a 3-way handshake. Remember that because it's very important in TCP. None of our other protocols have any type of handshake. They just send their information. IP, Ethernet just sends information. All right? But this has state, and that has repercussions for routers and other devices we'll talk about later, and even our computers. So the 3-way handshake is called a SYN, ACK, ACK. Now, these refer to the TCP header, and the header of TCP has flags in there. These flags are just kind of like, think of a flagman for construction. He has a flag that tells you to stop, he has a flag that tells you to go. You look at that flag and do what it says. It's the same thing with the TCP header and the flags. So SYN means synchronize, and acknowledgement means I acknowledge this information. So this sets this connection up. The first SYN is saying, hey, I'm sending you what's called an initial sequence number, or ISN, and I want to synchronize with you. So I'm going to send you a SYN, SYN, and the SYN ACK comes back from the other endpoint, the person on the other end of the connection. they have to want to synchronize with the other side as well. They have to agree on this. So this is where the ISN comes from, the remote end of the connection. But every TCP segment, we'll see in a second, has a sequence number. It is like a tracking number. It has to be kept track of, and when it is received, it has to be acknowledged. So I don't know how many of you guys that are watching this use eBay, but anytime you get a package online, you look at the tracking number. When you get you're looking at it to see where it's in transit. When it arrives, you go online sometimes, send the seller a message, say, hey, I got the item, thanks. Now, yes, you don't usually say, hey, send me more items. It doesn't work. That's as far as the analogy will go. But it essentially says, hey, here's the tracking number, I got it. The seller is like the person that sent the SYN. The SYN-ACK is the message you send to the seller to tell them that you got it. The sequence number is the tracking number. So that last ACK, though, is acknowledging the SYN the receiver, the remote end sent. Okay? So SYN, SYN-ACK, ACK, and now we have a connection set up. We have to do that before we send important data. Now, the first SYN, like I said, is sent by the sender. It's the ISN. It has the initial sequence number in it. The second SYN-ACK is sent from the receiver. It says, hey, I got your SYN. I want to start a connection with you. I'm acknowledging it, and here's my ISN, so we can get on the same page with our sequence numbers, so we don't lose any data. Now, the last step is we need to acknowledge the ISN, the initial sequence number, of the receiver, so the sender acts that. And after all that's done, then we can start sending images over the connection, text over the connection, web pages. Our apps can start to communicate on our phones. It's the same thing. They all use it. This is the amazing thing about these protocols. So every segment from a sender or receiver, I just alluded to this, has to be acknowledged. You got to know you got it before you can send it. Send it the next one, or send a response for that segment. So TCP will not send any more data in the connection until the data that it has sent has been acknowledged. It will not send it won't send like if we had segments 1 and 2, it won't send those it won't send 2 until you acknowledge 1. So if I send 1, I got 1, I acknowledge 1. The sender sends 2, the receiver gets 2, I acknowledge 2. The sender then sends 3, the receiver acknowledges 3, and so on. You'll see there's things we can do to help this and send more data, but it's a little bit different. But you have to acknowledge it, remember that. Any data, TCP connection, acknowledge it before you send more. Now, if we lose any information in the connection, whether a router routes the packet wrong, because that can happen, or a switch fails, or a switch port fails, or a cable in your network fails, or a wireless access point fails somewhere. There's many failures, but this is why TCP operates this way. If any part of a network fails for any reason, the receiver can let the sender know that if he didn't get the information he was expecting. So the missing data can be acknowledged again, the previous data. If I send 2 and then the receiver keeps acknowledging 1 over and over and over, it means he didn't receive 1. So I have to resend 1. I don't just assume he got the second one if he hasn't acknowledged the first one yet. It's a very cool flow, how it operates. But how you do this, though, is when you send the acknowledgement back, we use another TCP field called the sequence number. This sequence number is like, just like I said on my finger sheet, you didn't see it, but if it's 1, my sequence number comes back as 1. So that's able to say, hey, I need 1 again. So that's how we ask for information to be sent again, another copy of it. Now, TCP uses both sequence numbers and acknowledgement numbers, and they both keep track of what has been sent and received. The sequence number is what has been sent. The acknowledgement number says, hey, I've received. It implies that I have received the previous sequence number or group of sequence numbers, and we'll see that in a second, and that I want to receive this next sequence number. This is what I am expecting, all right, or group. But again, hang on. So when both sides are done with this reliable connection, we need to tear it down. So it's torn down. And the proper way of this happening is a fin, an ACK being sent. The fin flag, it could be flag, bit, or a flag or a bit, it's called. The fin means finish in the TCP protocol. So if I want to send one, I send fin from my sender, and when the receiver gets it, he sends a fin to say he wants to finish the connection as well, and he acknowledges my segment that had my fin bit in it. So then, lastly, I receive that fin, and then I ACK his participation of wanting to close the connection. This is how it happens, how it should happen. Sometimes it doesn't happen like that. I didn't cover it in this course, but this is why we have things like TCP reset messages, where something goes wrong in TCP, and another flag to use is the RST flag, which means reset. You can either reset a connection or time out a connection if something completely goes wrong and we can't set up the connection properly or tear it down. So that is the basics of how TCP operates. We're going to go into a little bit more detail in a second. Alright, so a little bit more about how TCP operates. UDP will be easier. So TCP also can send faster or slower. That just means how much data is being sent in the connection. So when TCP does this, it's called windowing, or a TCP sliding window. And the window field is another field in a TCP header. What we are saying is how many bytes of information can we send in this connection before I have to stop sending and I need to hear you acknowledge to me that you've got that whole window of bytes. This is what I meant about groups of sequence numbers and groups of acknowledgement numbers. So, this window has a max size, but the size isn't constant, so it can change. It won't stay the same during a TCP connection. And it increases or decreases. Now, the way it understands which way to go, larger or smaller, is by how many ACKs the sender and receiver hear. So we can send, say, I can send 1, 2, 3, 4, 5, 6 TCP segments. Back to back to back to back to back to back to back. All right? Now, what the receiver does with that is sends one acknowledgement that says, hey, I'm expecting to receive 7. But what he will do is take his window value. So if he has a window value of 7 they've agreed on, and he will acknowledge that he's received 7, up to 7, by saying he is expecting 14. Because for 7, the next 7 plus 7 is 14, so when you add the window field into the acknowledgement number, you get the next window of bytes. See? So by that, he's implying he's received the entire window. If he didn't, he would just... If I missed 5, I would just keep acknowledging 5. What I would do as the sender, if I had a window size of 7, is send all 7 TCP segments again, because I'm implying that the receiver's implying he's lost one. There's other things like SACK, so SAC, that is an acknowledgement number that is selective. It's a selective acknowledgement number where I can just pick out 5 out of that window of 7. So I don't have to waste all the time and bandwidth of sending all 7 again. So this is that group, though. This is what the window does. The bigger the window, the more bandwidth I can send, the more throughput I can have in bandwidth I can use per second. This goes all the way back to our signaling, to our Wi-Fi channels, to our UTP cable, to our fiber. higher the window, the more signal I can send per second through that path. All right? So what happens is the receiving end can also control. So if he's getting overwhelmed, like if I cannot store 16 segments, let's say, at one time, and I can only store 8, I can go ahead and send that window adjustment, and a window update it's called. I can send, hey, I need to send you this packet and tell you I can only have 8. So he tries to change that window actively. And the sender, if he is operating correctly, will agree. And he will change it to 8. And then, so they'll back off on the window size, decrease it, and send 8 instead of 16. So the receiver does not get overwhelmed. But this goes into if things break in the network. That would decrease acknowledgments being sent because IP packets carry TCP segments and they wouldn't be being routed if something went wrong in the network or there was more delay. Remember that end-to-end delay? It all goes together. It all affects things like this window field. How fast our acknowledgments get through affect how fast our window field can grow and how much we can send in our connection. So that's as far as we're going to go about windowing, but you have a very good base about how that operates. TCP, going back to our checksum, it's the same concept. Technically, it is a 16-bit checksum and it's created with a hash. But all you really have to remember, you don't have to necessarily remember how the hash is made. All you have to know conceptually is that, hey, when I send, I'm going to put an A on that TCP segment. When you get it, there better be an A on it. If there isn't, it's being corrupted, and I need to resend it. So that's another thing that can happen in a TCP connection. You remember our checksums, hopefully, from our frames, from our packets, from now our TCP segments. It's all the same. So UDP will be a lot easier. There's a lot less moving parts, but there is disadvantages. Oh, before we move on to this, I do want to say there's something called multipath TCP that has been around for about 7 years. It's still in the experimental stages. But if you hear that, don't get confused. Everything I have said about TCP holds with multipath TCP as well. It's just a way to use more bandwidth, essentially. It's like 2 simultaneous TCP connections doing what we just said, but they can take multiple paths. That's all it is. If you want to read more about that, just use the internet, essentially, and look that up. It's a very good tool. Well, because when you're learning about the internet, you can use the internet also to search anything I'm saying that you might not understand and need more clarification on it. That's the beautiful thing about the internet. You can use it to learn about it. It's amazing. So, all right, UDP operation. So UDP is User Datagram Protocol, but this is a lot like the Internet Protocol. It just sends data. It doesn't know if it was received. It only knows that it sent it correctly. It doesn't even necessarily know if it got out of the network. It's, that network. But it has less overhead. There's no connection setup, no windowing, no anything. But it is more error prone. This is used for things like YouTube and streaming and video calls, where with a video call, if you lose a picture of someone you're talking to and they make, like they're saying, hey, I was going to say it, and then it makes something weird, and then they start to speak, but then you hear it again because it resent that segment of audio in a TCP segment. You wouldn't want that. That's why UDP is used for streaming applications. And it will all click in, I promise. We are getting close to where it will all click in together. So this doesn't perform any connection setup at all. It's an optional checksum that can be used. It only covers the UDP datagram, not your application's data inside of the UDP datagram. So not like the contents of youtube.com or wikipedia.com. It doesn't cover the checksum of that. It only covers that its fields are correct. All right? TCP covers the application as well, all that data. So, port numbers. They both use port numbers, TCP and UDP. And pop quiz, the total number of port numbers we have is 2 to the power of 16. You remember what that is? 65,535. That's right, because it starts at 0, by the way. So the port number just tells TCP and UDP which program on your computer should receive the data. So it's an identifier for that data. Ports can be thought of like this. They're a doorway to your computer's programs. Essentially, can either be open, can either be shut, can be somewhere like cracked, so it can be in between. But a source port is the program the data came from. A destination port is the program the data is going to. So you need both of them, just like in IP, you need source and destination addresses. Now we know why. Just like in switches, you need source MAC addresses and destination MAC addresses in those frames. But both the sender and receiver use those port numbers, and the entire range of them is 0 through 65,535. Now, in the range, remember these two distinctions. There's reserved ports. That's 0 through 1024. And these can only be used by server programs, at least by default. If you get playing around with servers later on in your, in your journey of studying this, you'll be able to mess around with that and really have a lot of fun. Changing, port numbers your servers are using and things. But it also means if you're a server administrator or just a hobbyist, you have to be root to listen on those ports. So if you're doing any programming, you have to make sure your program has root permissions to do that. But the ephemeral ports, ephemeral is just means temporary, basically. So they're used for a short amount of time. These are 1025 through 65,535, and they're only used by client programs by default. Again, you can mess around and use these for server programs and other things, and we'll see that in just a second. But these are the port numbers. They just identify what program sent the data, what program should receive it. All right? This is what our computers deal with directly. So IP addresses and MAC addresses only, all the computer had to care about was, hey, I have a MAC address that identifies my network card on this broadcast domain. I have an IP address that puts me in this group of MAC addresses in this subnet, whether it's IPv4 or 6. And now we're dealing with identifying port numbers. Now we really have to pay attention because our computers have to manage this directly. Now, again, with the port numbers, this concept of multiplexing is very important. All it is it's how client and server programs create and manage multiple connections. That's it. So I could have 5 connections at once or, 20,000 connections at once instead of just one. If I didn't have multiplexing, I could only use one port number at a time. And that would be horribly inefficient, especially for the scale of the internet today. Many clients are connecting to servers many, thousands of times a second, all over the world. But source and destination ports, along with source and destination IP addresses, work together, and those identify one connection or flow. And again, this part, your computer keeps track of this. There's other things in the network that keep track of it as well, but we haven't got there yet. So multiplexing is just like having multiple doors in a building. Many people or processes on your computer can use any of them at the same time. So if they have to send or receive, they can use a port number or a door for that. So that's a good way to think about it. All right, when I come back, we're going to start section 7. We're going to talk about these application protocols and find out what TCP and UDP carry and how those port numbers come into play in combination with that. I will see you there. All right, so application protocols. Now, remember how TCP and we have TCP, UDP, IP, and Ethernet. So just like those protocols, applications, they have to use protocols as well, and they use the protocols to access the network. So all of it, hopefully, you're starting to understand how it all is relying on each other. All right? It all relies on each other. It can't do the whole thing by itself. All right? So it's just like in in the world. There is many different tasks that have to be done, and as as people, we can't just rely on ourselves to do everything. We need to rely on other people as well. It's structured in that way. Now, that's similar to how computer networks are. Excuse me. Now, each protocol has a set of steps, and that's the same for any protocol we've talked about all the way from Ethernet to now. All right? Even the signal at the physical stuff has protocols, but they're just harder to understand and see because they're built into our network cards. It's something called an ASIC, just like how we talked about switches having ASICs. That's basically a miniature computer little chip that does that very fast. I mean, you can't run like Windows, Linux, or BSD on it, obviously, but all it knows is that simple task of like looking at a destination address or forwarding a packet very fast. But every protocol is just a set of steps. You have to follow them. So the steps have to happen in the right order between a client and a server. If that doesn't happen, the connection times out and is torn down. Now, it can also be terminated on purpose or reset on purpose or by mistake or a network failure, but that's how it has to operate. And most protocols that are on your computer that your applications are using use TCP for sending their data. Remember why? Because it's very reliable. Think about this. If you're doing something like a purchase online, would you want that to make sure it got to the server? Or would you want to use UDP and, well, maybe it got there. Maybe the price of the item was right that I was paying for. Maybe it has the right address on it. Maybe it's the right item. I don't know. See what I mean? You need reliability with your application protocols too. So that's why TCP is in networks. That's the point of it. But some of these protocols that are they tolerate errors better and they can resend. It's not as critical that they do not it's not critical that they lose information. You never want to, but some things you can be not as worried about. So that's what UDP is for. We know why now. But if UDP is used by the application, it is the application's job to make sure the data it's sent, or it's called the payload, is received correctly and is error-free. So with UDP, the application protocol becomes more complex. With TCP, you have less of a complex application protocol if you program it to create, and you can rely more on TCP's functions to do all of the error checking for you. Now, this is where application protocols tie in with TCP and UDP and port numbers. Web browsing uses HTTP and HTTPS, and they utilize TCP and ports 80 and 443. All right, 443 is normally HTTPS, whereas 80 is HTTP. Now, any web servers use this. DNS, the domain name system, you remember, uses TCP and UDP, depending on what it is doing, and it can use ports 53 and 853. And 853 is for DNS sec with security extensions, and when we use encryption with DNS. 53 is the more common one, but with DNS, like if it's transferring information, it uses TCP to be reliable. But when you're just asking, remember, for the domain name to IP address mapping, UDP is okay. Because if you miss the first response, it doesn't respond, just wait a second and send again. It's not a big deal. So you have DHCP, Dynamic Host Configuration Protocol, that uses UDP, 67 and 68. 67 is for the DHCP server. 68 is for the DHCP clients. Remember, yes, we need our network information, but if we miss the first request, we'll just send again. That's why UDP is used for DHCP. DHCP v6 for IPv6 uses UDP and ports 546, and 547 for the ports there. SSH, or Secure Shell, which is a protocol for administering systems over the network and also for proxying, uses TCP and port 22. FTP, the file transfer protocol, uses TCP and ports 21 and 20. Cool thing about FTP, 21 is the control port, 20 is the data port. So if you're trying to use FTP in your network and you try to get a file, but it fails, it's actually because it's trying to open port 20 before we started a connection on port 20. So it just drops it. It does not know, and we'll understand why that is in a little bit. Telnet uses TCP and port 23. It is the older version of SSH. It wasn't encrypted. SSH is encrypted, meaning everything is secure. Just like HTTP is plain text, unencrypted, HTTPS is encrypted. That is secure. SMTP is a simple mail transfer protocol. That's TCP. Uses ports 25, 465, and 587. 25 is for email being sent and received. 465 is for secure sending of that. 587 is for something for submission of that email. IMAP is the Internet Message Access Protocol. We have TCP and ports 143 and 993. And again, that's for receiving mail. SMTP is for sending it. POP is again for receiving mail and those ports. Now, 993 on IMAP is for secure, for TLS. 143 is for plain text. 25 can be used secure or insecure for SMTP. 465 is for secure. 587 is secure. Now, POP can use 110 for plain text, 995 for secure version, so TLS, or SSL otherwise known as. IRC is Internet Relay Chat. I'm sure a lot of you watching have heard about it. Maybe some of you haven't. This even was before instant messaging, and it's a cool decentralized chatting mechanism, application protocol where you have a server and you have a client. Clients connect to the server, and you can send messages and files and have private chats and things. It is awesome. There was things before Discord. I know it's hard to believe, but IRC is still alive and kicking. But anyway, it's cool. So it uses TCP, uses ports 194, 6667 is the default, I believe, if I remember. It's been a long time. And 6669, you can use TLS and SSL to encrypt it again, like always. These application protocols and TCP and UDP bind to a socket, and that socket is just a function used by a programmer. It's a set of rules that know how to make a socket basically in a program, and the socket is between the application and the rest of the network protocols, so everything below the application protocol itself. The only protocol the application has to know is its own. It either has to know HTTP and a TCP or socket call, or a UDP socket call, like a DNS server. All that has to know is DNS and a TCP socket call or a UDP socket call. Same thing with a web server or a web client, like Firefox for browsing. All we gotta know is HTTP and that we have a socket call to make and how to do it. Don't have to know anything about IP, don't have to know anything about routing or switching, anything like that. It depends on the other lower layers to do it for it. So WinSock is the Windows Socket API. It's Advanced Programmer Interface. And it is how you code this. It's the Windows Socket function, and otherwise called library, that gives you access to the network stack in Windows in its kernel. Berkeley sockets are the Linux and BSD socket function, and it's just a library that gives you access to the Linux or BSD's kernel's network stack. Alright, so now on to processes. So a process is what's going to be using that port number or the protocol, either TCP or UDP. And the process also has instructions for whatever application protocol it has. So these could be HTTP, they could be SSH, FTP, whatever have you. So How this is done, though, is a process is dependent on a kernel, which is part of an OS or operating system. And what the kernel does is just creates a process when it's told to execute a program. So when Firefox starts, it requests resources, and that creates a process. And then the kernel gives that process certain resources. So, a certain amount of resources on the computer. These are things like RAM, disk input and output, CPU time, sockets, etc. And remember, the sockets are what connect into the rest of the kernel and, in turn, the network. So after the process is finished using those resources, or the process scheduler says, hey, you're out of time here and we have to use and get another process access to these resources, it frees the resources. So it only can use them for a certain amount of time, and then it frees them, and then any other program that wants to use resources can. So an operating system has what's called a network protocol stack. And this is what sockets give us access to. So a process gets executed, it requests a socket resource as part of its resources, and then through that socket, either TCP or a UDP based one, it accesses the network protocol stack. And the first part of that stack is TCP and UDP. And then, as we're going to see really soon, the other parts of the stack are all the other protocols we've talked about already. So, again, everything that we've talked about, Ethernet, IP, TCP and UDP, and the application protocols, they're all code. So they're ones and zeros. And there's more to it than that, but I'm going to save that for another video. So basically, they're code. So all the other protocols, such as HTTP, IRC, SMTP, TCP and UDP, Ethernet, DOCSIS, whatever protocols you want, that's all code, and that code is in a network stack that's part of the kernel's code. So this is also called a TCP IP stack, and it just means that it's a bundle of all this software together. And this stack performs all the network functions a computer needs in a step-by-step manner. And computers, like your Windows or Linux machine, aren't the only things that have network stacks. Routers have network stacks. Switches, to some extent, have network stacks, but again, they have the ASICs, so they don't have as a good of a view of the network stack as other devices. But they utilize some of the stack, or even all of the stack in some cases, depending on, again, the implementation of the device. And there's some switches that you can't access higher layers on. There's other switches that you can. And yes, I'm about to clear all that up. What a layer is in all of this. So it's a step-by-step process down that stack, and a network stack is made up of these multiple layers. So here we go. The OSI model. This is the Open Systems Interconnect model. And like the long and short of this model is it just logically helps us understand the pieces of a network. That is it. That's all it is. It's a design reference model, essentially. So it helps us understand how they fit together and how they depend on each other. So before, when I said how TCP has to be routed by IP, that is why they are layered together. And that's why a network stack has been designed based off of these models here, the OSI model. So this model here has 7 layers. This is the older of the two we're going to talk about. Depends who you ask if it's still relevant or not, and you're going to hear all kinds of stuff that it's not relevant anymore, and things of that nature. I still use it. This is what I learned. It's pretty much what you will learn on any certification program about networking, even today. the two we're going to talk about. So regardless of any of that, it's made up of 7 layers, and each layer is one responsibility of a network. Whether it's the application layer protocol, whether it's the signaling and the connectors and the wiring, or whether it's routing or switching, each layer in a network is represented by one of those layers. Most times, everything we can describe and design in a network is derived from the OSI model layers, and it will be able to fit in there when we discuss it and talk about it with other people. So the higher numbered layers in the stack depend on the lower numbered layers to operate correctly. This is why our network stacks are designed in this manner. So this is our layers. I'm going to bring my mouse over here so you can see. So this is layer 7. And this is the application protocols. This is everything, things like Firefox, SSH clients, DNS servers and clients, DHCP, client and servers. These are what application protocols are. All right, these are what the processes have in them that request a socket. All right, so this is HTTP, FTP, all that runs up here at layer 7. Layer 6 takes the instructions in the application, whatever those byte layout is and of it and things, and instead of having a different format for every protocol, because more are invented every day, the presentation layer standardizes all of the information or data coming from application layer protocols. So it makes it so they are all ASCII, that they're all standardized code, basically. That's every device agrees on, that is designed based on this model. So this is the American Standard Code for Information Interchange, I believe. It's that's what ASCII is, though. Now, under this, once we've standardized it, we have the session layer, layer 5, and presentation was layer 6. And the session layer here is things like session initialization protocol for our phones, and sometimes encoding schemes and things. But not every protocol or piece of a network is going to fit neatly into one layer. That's why it's a design reference model. Don't freak out if something you're dealing with that you can't really map it to this model. That's not necessarily what it's meant for. When this model was made, this is when AppleTalk was still used. This is when DECnet was still used. Things of that nature. This was an attempt to standardize. And it worked, obviously. But through the session layer, then we go to the transport layer. And this is layer 4. This is where we find TCP and UDP. And this is our segments and datagrams. So that's, when you think transport, think those TCP and UDP, think port numbers, things of that nature. When you think layers 5 through 7, think data. So it's still just data, but there's no real identifiers on it yet. That's what the transport layer puts on there. It puts identifiers on. Source port and destination port, essentially, is what we're dealing with there. And we're still, identifying it on our computer. And then when we go to layer 3, our computer is putting it in an IP packet. So think routing, think routers, IP addresses, source and destination addresses. And this is where our packets live. Things like that. Our data link is layer 2. And we have media access control addresses. We have our frames. We have our switches that operate at layer 2. Our bridges also. And this is where those live. And we also have a sublayer of the data link layer, the 2 sublayers. MAC, which is the media access control sublayer. And you have the logical link control layer, LLC and MAC. So that's what I want you to think about when you think of layer 2. And the physical layer, of course, is all the pads, the signals, the wiring, the connectors, the modulation we talked about, the radio frequency. All that stuff lives at the physical layer. Now, the reason I didn't start with this is because when you first learn this model and you don't know anything about networking, it doesn't make sense. It really does not. So that was, in my opinion, that's my approach. That's how I chose to do this. And that's the great thing about the internet. There's so much more content out there to see. And again, if you need clarification, use the internet and learn more about it. But anyway, with these layers, we have PDUs, and that's the protocol data units. And this is how we have data up here at the first 5 from our application protocol here and down below. This is where we get port numbers put on. This is where we get IP addresses and routing happening. The data link is where we have frames, and the physical is bits. All right. Now remember, this whole thing happens as a design reference. This is why your network stack works this way. And basically, it's just all the parts of it. See what I mean, though? When you get into these models, it makes it seem a lot more confusing than it really is in practice. But anyway, the second model of the two is a TCP IP model. This is the more modern one we use. The TCP IP, so this is Transmission Control Protocol / Internet Protocol model. Same thing. It's a design reference model. Same applies there. There's many valid versions of this model. Some have 5 layers, some have 3. If you want, you can have discussions for days about that. That does not matter to me. That does not matter in the context of networking. But again, each layer deals with one part of a network when we're designing one. And the higher layers depend on the lower layers to operate correctly. So again, even if we look at the OSI, the TCP and UDP segments don't know how to route packets. They just know how to identify port numbers and make sure data gets there. Okay? Same thing with session, presentation, and application. See? Network only knows how to route packets. They only deal with IP addresses there and routing. They don't care about port numbers whatsoever. There's cases we can, but we haven't gotten there yet. The data link layer is frames. MAC addresses, that's it. Don't care about subnets or anything. So we wouldn't have multiple broadcast domains if we didn't have designs on the network layer like routers. See? So you need all of them, and this is why it all comes together. Same thing with bits. All that cares about is ones and zeros in your signals. It doesn't have any idea of what a packet is, just how to encode it. That's it. And there's also many different people in groups in networking that work on each of these layers specifically. All right. So anyway, same thing with that though. And the layers are I use the 4-layer model. This is the 1989 internet model. This is the one I had learned on when I first encountered the TCP/IP model. That's why I chose it. There's others, as I said. This is from RFC 1122, and that's the request for comment document. They're very good reads, and I suggest you look up RFCs if you're curious. Same deal, though. We have application. Those are all our application protocols. Transports, where port numbers. Internets, where routing and packets come into. And the link in this case is where frames and signals and switching all become one in the design. Application here has presentation and session rolled into it. So you got to keep that in mind. Where they understand it's 2 different models, essentially, okay? But they mean the same thing. They're just 2 different design models. The TCP/IP model is more modern. Same thing, they have the data for the protocol data units, data, segments and datagrams, packets and frames, just like so. And you'd add signals there as well because the link deals with that. Now, application is just how data gets sent. We send data from layer 7 to 1 through a model, and this is how it gets sent down a network stack from a process through a socket down the rest of the network stack. And each layer adds its own header information. Some layers also add a trailer as well. De-encapsulation is how we receive it. So this is when it comes into over the signal path. So like when when electricity comes over the UTP cable, comes through the RJ45 connector, hits your Ethernet NIC, the NIC decodes that information from whatever voltages it's detecting. Remember, the modulation scheme finds the ones and zeros out of that signal and sends it up layers 1 through 7 all the way up to the application on the host. But something very important, if we're dealing, I'll go back to this model. If we're dealing with a router, They usually only de-encapsulate this packet to here. Take the frame off, look at the IP, and then make a new frame. Remember that rewrite, layer 2 rewrite that happens? Sends it out. Now, something called firewalls will look at layer 4 and sometimes all the way to layer 7. And hosts, of course, will look all the way to layer 7, okay? Now, switches will only look at layer 2 and then just modulate it again out whatever path. Same thing. Routers look at layer 3 and then we'll create a new frame and modulate it again, making a new signal. Alright, so that is how it's received though. And this is essentially what happens. We have our application data. That's our formatting data. That gets put, the formatting data encapsulates the application data. The session data then gets added and encapsulates the format and HTTP data. A TCP segment gets added in this case and encapsulates the other 3 layers, so session format and HTTP. And then IP gets put on there, and as a header, this is where we're putting on the headers, and then it puts in the addresses, and it encapsulates TCP, session, format, and HTTP. You can encapsulate any protocol, by the way. And the data link adds a frame around it. That's why it's called a frame. It frames the packet. This is the header of the packet with source and destination addresses, among other things, those MAC addresses. This frame, this part of it here is called the trailer. This includes the CRC 32-bit checksum. Ethernet frames they add a trailer. That's why some protocols add a trailer, some don't. After all this is done, the physical layer gets it. So this is from the driver of your operating system to your NIC. And then once the NIC gets it, that ASIC in the NIC will modulate it in whatever media type it has. So whatever signal path, whether it's electricity, light, radio waves, etc. And then that makes the ones and zeros into encoded and modulated on whatever that may be. But what you need to know is the lower layer that encapsulates it, the higher layer's data is the payload of the lower layer. So like TCP. TCP is the payload of IP. And then the frames. The frames payload is IP. IP is still encapsulating the other information, but every layer below only cares about the layer's protocols directly above it. That's the cool thing about these layers and why it kind of gets complicated to think about. But yeah. Alright, so that's the end of section 8, and I will see you in section 9. Alright, so now that we know how routers and switches are supposed to look when they operate, so basically their baseline behavior, what we need to know now is what do we do when that doesn't occur? When something happens that's unexpected, or essentially the question that always comes up, and even in home networks, is the internet broken? I can't get online. You hear that all the time. Or the internet's slow. Many things like that. So, here is how we can narrow down if it's the network or if it's the computer on that network. That's a very important distinction because sometimes computer problems can mimic a slow network when in reality it's the computer causing the slow experience, not the network itself. But that is something to watch for, and with these topics, we're going to be able to know for sure what is going on. So we're going to diagnose network problems, and that's what we're covering in this section. Now, the first thing we need to know is there's 3 important steps for diagnosing a computer problem in general or diagnosing a network problem. First of all, we got to identify the symptoms of the problem. All right, so we got to gather facts, essentially. And with those facts, it's a good thing with the facts to verify the problem. So repeat the steps that's happening to know if it's happening when you repeat them. A good place to do this as well is on your own computer, because you'll know right away, is it something on that computer only? Because if it's only on that computer, all right, go search that computer only. If it's on your computer, that may mean it's affecting everyone. And if it's affecting everyone in the same way, that is a telltale, a sign that it's the network itself. All right? So really keep that in mind. It's very important. So what you do though is just use those facts, and once you verify it's happening, like let's say I cannot get to google.com. Well, we now know quite a bit about how that happens. So we can look at all the kinds of things that would mess up our ability to get to google.com. Well, the first thing that comes to mind to me is DNS. DNS could be an issue. Routing could be an issue on our gateway. Our routing table on our computer, the routing table in our router, the CAM table in our switch. Now, in that case, we would probably try a different switch because there's only so much you can do in the case of switches. But those are the places you may want to look. And don't ignore as well the layer 1 stuff, the physical things, making sure your cables are plugged in, making sure they're not damaged, and all of those things. They're very important. So you would do this, you would go through, check everything on the LAN, then you would go through as far as you can on the WAN, the wide area network, and look at your modem. And you have to make the decision, well, when is it a problem in my network or just with one PC, and when does it become a problem that my ISP needs to help me solve? That's a distinction we're going to get into in a little bit. But essentially, you just test theories of what could be causing the problem, and you test and verify resolutions to those problems. Maybe it's putting a missing route in a routing table. Maybe it's renewing your DHCP lease, or with Slack, getting a new IPv6 address, or IPv4 with DHCP, or DHCP v6. Those types of things. You can look at MAC addresses. You can look at your ARP cache and things. There's many reasons, but all you're trying to do with all of this is isolate whatever the problem is and discover the root cause of it. Whether it's routing, whether it's a cable that's bad, whether it's a switch that's bad in the network, you want to isolate that. Even if it's a PC itself that's causing it. Like maybe a virus on the PC or something like that. So you got to isolate that, period. That's step 2. Step 3. You got to verify it's resolved. You can't just say, okay, it's fixed, whatever. I'm going home. And be done with it. That's not a good solution. That's not a good way to deal with an issue. So you want to verify it's resolved, but you want to follow up a little bit later and verify it's still working. Because some issues, like if it's a switch issue with a CAM tail, it may straighten itself around, but then if you have two switches connected to each other, that the device on that other switch maybe sends that broadcast that was causing CAM table corruption. Well, maybe that is intermittent, and it doesn't happen all the time. So an hour later, you get a call, I got the same problem. What's going on? So it's important to follow up. Don't think because you did one thing and it fixed it, the problem's done. You may have other aspects in the network that are coming together at the right time to cause the problem. So always be aware of that. But once you have figured out all the aspects of whatever's causing it, and you've come to a resolution of that problem, you want to document it. That is so important. You can waste so much time if you don't document what fixed an issue, and then you're sitting there trying to remember what you did to fix it, but you're essentially starting from, from square one again. So, you always got to document. And I know you don't like to document. It's like, my goodness, I've solved the problem. I don't want to waste time documenting it. It pays off later, is what happens. So don't ignore that. But those are the 3 steps of any computer problem and network problem. So you can apply these concepts here to both. Now, what tools do we use to investigate network problems? Well, we have 2 main protocols that help us do this. They help solve problems. We have ICMP, the Internet Control Message Protocol, and we have ICMP version 6, the Internet Control Message Protocol version 6. Now, ICMP v6, by the way, has a big part in Slack. It isn't just like an IPv4, how DHCP was there. ICMP v6 does neighbor advertisements and solicitations, as well as echo replies and echo requests, trace routes. It does lots of different things. so like router solicitations and router advertisement messages, ICMP v6 is the protocol underneath. That's why I said NDP is an umbrella term. But regardless, though, these protocols are utilized in some of these programs, and they help us solve these problems. So, ping, it just sends ICMP echo messages, and it waits to receive ICMP echo replies. This can test DNS as well if we use a domain name in the ping command. And it can test layer 2 to make sure our switches are working, and it can test layer 3 to make sure our routers are working correctly. So you can knock out a lot of your issues and verify a lot at once with one command. If you realize why the command is working, see? That's why you got to put it all together. That's why networking is all one big thing, separate pieces that all come together and operate together. So ifconfig and ipconfig, when we're looking at these commands, we're verifying one PC or sometimes a router, but we're verifying the IP address on the interface, the subnet mask, and those two things that are assigned there. Remember, if we get the wrong subnet mask even on one PC in the network, it will think it's on a different broadcast domain or subnet. So that can cause routing problems with that one PC, and if that mistake happens on a router, that can cause routing problems as well. Maybe all the PCs are right, but the router's route is wrong because you configured the interface wrong, or just a static route. That can cause all kinds of problems in a network. Now, netstat-rn and route print, I do want to say the newer one in Linux is IP space route for this information, but it verifies that the correct routes are there, so they're in the routing table and they're being used. You do want to check that. That's very important that they're being used correctly. And traceroute and tracecert in Windows, traceroute in Linux and Cisco iOS. But these just send packets with a time to deliver hop limit field because it works for v4 and v6 that gets one hop closer each time and causes a time exceeded message to be generated by that next hop. So then it knows that each hop along the path to the destination is operating correctly. This is really good to narrow down routing problems and things. But speaking of DNS, dig and NS lookup are a good way to help us verify resolution is working. Those are good tools. iPerf is good for bandwidth capacity testing and things of that nature. And telnet. Telnet is actually used for administering a Unix system over a shell, but you can actually verify it to check on specific servers. So if you've done server administration for any length of time, you may have found out by messing around that you can connect to the port of a service on a server with telnet and give commands manually. Like you could connect to an HTTP server and give a GET request manually to make an error happen on purpose or to make sure it serves you the file. So those are some things that Telnet can help you do. So now that we have an idea of some of the tools that help us do this, let's talk about the important places that we should look that the tools basically inform us about. So they give us a hint, hey, you know, when I send to this switch, it's not working. Well, it could be something with MAC addresses, you know, or if I can't send to my gateway, it may be something with that configured IP address or netmask, those kinds of things. And that's, we gather clues about the problems with those tools, and then these places are where we may correct the problems. So the ARP cache, of course, we've already talked about. This is that IP address and MAC address mapping in the table there. This is only for IPv4, but you need to use the ARP cache's information to verify MAC addresses are being resolved correctly. This can also help you narrow down duplicate IP address problems, and that can cause both routing issues and problems with MAC addresses. And that can even go further and affect your switch, the CAM table of it and everything. When you have two two MAC addresses mapped to the same IP, that messes up the CAM table. So that's a possibility. The NDP table is another good place for IPv6, remember. It maps MAC addresses to IPv6 addresses in that table. Again, you're verifying those MAC addresses are resolved correctly. Same concept applies. If you have duplicate IPv6 addresses map into the same to two different MAC addresses, it messes up your sending of your information, your packets or frames, and it messes up the switch or even the router in some cases. Now, the routing table, again, we know that. We need to verify the correct routes. We got to make sure they're in there. Not only are they in there, but when you have, like with routers, when you have more than one route and you do something called load balancing, you want to make sure the right route is being used. So that would be a great way to narrow that down as well. NetStats output. This helps verify our applications. Remember the application protocols, that they use a socket and they use either TCP or UDP, how we covered this. Well, on your operating system like Windows or Linux and BSD, you can check your processes are using the sockets correctly. So you can make sure the kernel gave a process a socket in the right way, that it's creating and using the socket right. A good example would be if you're administering a web server, let's say, and you want to make sure that Apache, for instance, the web server software, is listening on port 80. Well, remember, that port number maps to a socket and it identifies the socket. When I do netstat -ANPUT there, it shows me the TCP applications and the sockets they are creating and using. So if I can't connect to my web server and I find out Apache is not listening on port 80, so that he hasn't made that socket, I know it's a socket issue and I need to check the server software, maybe make sure it's running. I need to check things like firewalls, which we're about to get into in a few more sections. But that's your tip off there for that problem. Now, another great thing is network packet analyzers, and I love these things. I use them all the time. They're great in many different parts of your network to diagnose many problems and just verify things. So TCP dump, T-Shark, and Wireshark, at least of 2020, are the tools we use. TCP dump, I think, will be around for a long time. I think I'm safe in saying that. Probably the other two as well, I would think. But what they do is they capture all or just specific packets that a network interface is processing. There's two ways it can do this. It can do it in real time or from a past capture from a capture file. These are when you see .cap at the end of a file name or .pcap. These store all of, remember the OSI model? All those layers, all the headers and everything and all the different information. These analyzers capture a packet, thousands of times a second on an interface, whatever it's doing, and will zoom in and show you the details of every layer of that packet, every header that's attached to it. It's a really awesome way to learn even more about networking. And you can install Wireshark right on your Windows PC or whatever you have and fire it up on your, Wi-Fi card or on your Ethernet connection, and you can just see so much network traffic. And you can really learn about all these things even better. But anyway, there's another interesting thing to do besides a file. Analyzers can also send over a network socket. So I could have TCP dump run, send its output over a network socket with something like SSH, or natively by piping it into another command like netcat or something like that. And you can monitor a remote system locally. That's a really good thing to do in some networks and in some cases. But that's some about how network packet analyzers work. I encourage you, download Wireshark, fire it up, and see what you see, because you are going to be amazed. You are really going to it's going to click in, and you will see how the OSI model relates, how the TCP/IP model goes into it, the routing, the switching, all of that. It's going to make a lot more sense. and like layer 4 with the port numbers, you're going to see a lot. It's going to be awesome. But yeah, they allow deep and detailed inspection of every aspect in a packet. That is what they do. And it can be overwhelming, but there's lots of things you can do with those once you learn more about them. I mean, things like this are a body of knowledge in themselves, getting efficient with just filtering tools like that, packet capturing tools. They're very extensible tools. Now, we're going to wrap this section up with a network troubleshooting lab. We're going to have 2 computers and 3 routers. They're going to have multiple networks between those routers, and they're going to use those to talk to each other. We're going to examine what the ping command looks like to test connectivity in it. We're going to use the traceroute command to see the packet's path, and we're also going to see what happens when a router does not have a route in that path. And then we're going to troubleshoot and fix those issues. Now, I know I have IPv4 addresses here, and you should know, go through and see if you know the usable range of those addresses, broadcast and network IDs. I'm sure you do. But this is the reality of knowing subnetting as well. This is how you would see it, like how I wrote it in the diagram here. It's easier than writing out the entire subnet. But when I do IPv4, I'm going to do IPv6. All right, so I will see you inside the lab. All right, welcome to our troubleshooting lab. So here we have 3 routers, and we want PC1, which is connected to the network of router 1, so the LAN, to talk to PC2 in the second LAN that is connected to R3. So we're going to go through here. First thing we're going to try to do right away is, because PC2's address is 4442, let's just try to ping that and see what happens. 4442. We get a no route to host message. So the important thing to realize is this message is coming right from our own computer. It's not coming from our router R1. It's coming right from our own computer. So that's where we should start to look first. So we're going to do netstat rn and f for the family, and then we're going to do a init for IPv4. This tells me here, by looking, I have one connected route out of VM0. Okay, but I don't have any default routes, do I? So that's going to be a problem for our PC because he doesn't know how to get anywhere. He needs a gateway to help him. So let's go in to our file here and enable the gateway and see what our routing table looks like now. Now we have a default route. Remember, that's the last resort. It matches everything that isn't on the one subnet we have that we're a part of. So let's try to ping again. Oh, look at that. So now we can ping, and we're PC2 on the other LAN through these 3 routers is getting our packets and sending us replies. So why does that happen? Well, there's actually a lot of reasons. But the reason mainly is because here on this router we have these 2 interfaces. One is a part of PC1's network, and another interface is part of a second network. But if we look at the routing table on this router, you see it has connected networks. The ones that say link number 1 and link number 2 are connected, and these are the ones that are assigned to its interfaces, EM0 and EM1. The other 2 networks, the 330 and the 440, /30 and /24 masks, so they're CIDRs, have a gateway for them. That means R1 here isn't directly connected to them, and he needs to send those packets to the router that has 2221 if they're destined for those subnets. So let's go up to router 2. If we look here, okay, he's got those addresses. He's got the 2221. So this is the router that R1 is sending packets to. And he's got another network as well. So if we go to the routing table, these are again the connected ones, EM0 and EM1 for the 2220/30 and the 333/30. But the thing is, He doesn't know about the 1110/24 or the 4440/24. So he has a gateway of 2222 to reach the ones network and the 4440/24 to reach the 3332 network. Now the difference is that it's the same thing. He has to route to either of those networks. But from here, basically, what we can do is going down. I mean, you see the pattern, right? This R3 has an interface on the 3330/24 and has one on the 4440/24. So each router has a bigger picture of how to get that packet to the network. R1 and R2 by themselves don't know how to get to the 4440/24 network. And R3 by himself does not know how to get to the 1110/24. That's why they have to use their next hop address to get the packet one hop closer to its destination. Now I'm going to pause this, and we're going to go ahead and tweak a few more settings and show you other failures that can happen and the reasons why that is. So I'll see you in a second. Alright, so now we're going to try to ping that again now that we understand a little bit more about how that packet gets between the PCs through the routers. So we're going to run a ping. Oh, wait, I know what's wrong. So remember, we got to check that routing table, right? It's got to have that default route. It does have the default route. So have you figured out why it's not getting there yet? Well, this is that destination host unreachable message. And if we look at the reply, it says it's coming from 1111. And if we look at our default route, that's our own gateway. So let's go up to that R1 here and find out why it's telling us this. All right, so let's look at its routing table. And do you see a 4440/24 route? I don't see one either. So, the reason it can't route the packet any further is because it doesn't have a route, just like in the beginning, how we didn't have a default route off of our LAN. So, you can have failures in multiple places. That's why those messages happen from routers and why they're important. So, all right, I'm going to go ahead and pause it, and we're going to do one more exercise with this. Now, actually, to repair that problem, we have to put that route back in there and restart our routing real quick, just to make sure that we know how to solve the problem here. And then if we examine the routing table, we have the 4440 route in there again. And now if we ping, it's successful, because that router has the route for that network. I also want you to look, the time to live field is now 61, even though it started at 64, because it's because 3 routers have forwarded the packet, and every time the time to live gets 1 subtracted from its value. And that's so the packet doesn't cause a routing loop and route around forever. All right, so I'm going to go ahead and do that one other thing for you, and I'll be right back. All right, now we're going to try to ping again to that host. There's no timeouts this time, but there's no received packets either. And it says 100% packet loss. Well, we're going to debug it a different way this time, because we know we have our default route, but sometimes we aren't going to be able to access every router in the path, and this is actually, more often than not. In this case, you would have to call your ISP if you had a routing problem with them, and they would have to help you troubleshoot and, prove the problem might not be there on their end as well. A way you can isolate this, though, without being able to see the routing tables of your routers in the path, is do trace route, and we're going to trace that route. This uses those ICMP messages, and the time to live field. So let's trace the route and see what happens. It's not a very big route, is it? We're getting timeouts on the second hop after our gateway. Now, that tells you something very important. That tells you the problem isn't the first gateway. The problem is right after the gateway. All right? So what I'm actually going to do now is, because from before, well, let's go and look over on, in this case, like if this was our ISP, we would have to call them and say, hey, I can't get past your router. There's something going on. Something like that. But let's go up to R1. Let's start to double check everything. Okay, do we see an entry for 4441, for 4440? I do. Do I see a 1110? There is one. All right. So that looks okay. Now, if I look up here, do I see route here? There's something odd about this routing table, but I can't put my finger on it. I have the 4440/24. Well, that's the network I want to get to, right? So it should work. You see any reason why it wouldn't work? Remember, we have source and destination addresses. It has to go there, but it also has to come back from there. You got it? All right. So if you said we're missing the 1110/24 network, you're correct. If you didn't catch on to that, that's okay. You would have caught on in time because you would have kept troubleshooting and, figuring it out. Now, the reason this happens is because when the packet comes back through, it is sourced from the 444 network going to the 111 network. So if we ping again, now you see where the ICMP unreachable is going? This router does not know how to get, it's getting the echo request as a reply from 4442. That part is working, but when it tries to route this destination address, it doesn't have a route for it in its routing table. So it sends back to 3331, the next hop for the 444 network, the person that sent this packet, that, hey, I don't know how to reach this host, this destination. And then the router here gets that message and forwards it back onto the PC that sent it. And then he's informed that, hey, that a router along the path doesn't know how to get there. And if we do a trace route from the perspective of this guy, he gets a little further along the path than we did, but you only see that he's getting to 333 and then getting sent back. So the reason it is because this hop has the problem, not our gateway. Our gateway is forwarding it on to 3331, but then 3331 is having the issue. So how do we fix it? All we have to do is put the route back in for this network. And then from there, we just restart our routing. So now, if we run that capture again, like this, and then do a trace route from here, we get all the way through and get a time exceeded message from the host we're looking for, 1112. And if we do it likewise to 4442, we get through as well. And even though I didn't have a capture running on this, it still is routing the packets. Let's bring the windows up so you can see a little better. So it is routing them, and then if I ping, my pings succeed. So this is an example of a routing problem where it's not obvious. And the reason it's not obvious is because you're not seeing an error message directly on your end, so if you didn't have access to the endpoint and their equipment, it would be hard to figure out. So that's why in some scenarios, like if it's your provider that has the problem, you have to call them because otherwise you wouldn't really know. And with things such as firewalls, sometimes administrators block these debug messages. So it is very difficult to know where a packet is being dropped. But it's also for security because I can learn the topology of the network all from one point in the network without having to have access to those routers. So that's why a lot of places disable this feature. But it is a debugging feature. This is the Internet Control Message Protocol. And, any traffic, even web traffic or anything, would go over this path the same as well. Because it only looks at the destination IP address to route it, not port numbers. And we'll talk about that in a little bit. All right. So that is how we do some basic troubleshooting with ping and traceroute, and how routing works. All right. Now we have the same lab as before, but now we're dealing with IPv6. So we have the three routers and we have PC1 and PC2. We want PC1 to be able to ping PC2. Remember, if he can ping, he can send any other type of traffic over to PC2, unless there's a firewall, but that's besides the point for this example. So we're going to do ping 6, and I'm on the 2001:/64 network, and the PC2 is on the 2004:2, and that's part of the 2004:/64 IPv6 network. If we ping that, no route to host. So do you remember from IPv4 what this means? Where would you check? Check in the routing table, that's right. So we would check the IPv6 routing table. So looking through here, hopefully you've already spotted there is no default route. All I have is the route for the 2001:/64, and that's my connected network. That meaning it's configured on my interface. So, of course, I'm part of that subnet or group. So, let's go ahead and put the gateway in. And let's restart that. And hopefully we get a little bit better results. All right, now let's try that same ping. 2004:2. And now we can ping. Now there's a lot of great things to examine here. One, we were able to ping. But the reason is because remember, just like with V4, remember, just like ARP2, we used NDP, the ICMPv6. This was my computer here saying, hey, I need this, the MAC address to send to you. And then that solicitation came up, and then the advertisement came back saying, hey, this is my MAC address. So then I could send to the gateway, I could use the proper Ethernet MAC address to get there, because I can only hear in my broadcast domain, that default router. So after this router gets it though, he looks in his routing table with the destination of 2004:/64. If we go through here, we see 2004:/64. It goes to a gateway of 2002:1, and that's out of EM1. Now, this is part, EM1 is part of that network or broadcast domain the next hop is on. So he's going to do the neighbor solicitation, 2002:1. The next hop is going to do the neighbor advertisement back to him, and then that process repeats to get the MAC address in this lab scenario. But after that, he then sends the packet to R2. R2, that's the same advertisement from 2002:2, you see, to his next gateway, just like the client did. It's just that the routers have more specific routes than just a default route that catches every network. So if we look at his routing table now, IPv6 routing table, we see 2004/64. The next hop is 2003::2 out of EM1. So again, he has a route to get to the network. If we look at the interface it's going out of, this IP address is part of that broadcast domain. Yes, there's no broadcast in IPv6, but you still call them broadcast domains for the subnet. So he gets from 2000, from here, 2000, let's see here, 2003::1, that's the solicitation from 2003::1 to 2003::, I'm sorry, from ::2 to ::1, the solicitation comes back. So he has to ask again for that MAC address of R3. And these entries get put in the NDP table this time. So like this is the entry for that next hop. The ones that have expire and they have a timer, this is the entries for those next hops. But that's what neighbor advertisements and neighbor solicitations, that's how we get MAC addresses in IPv6. It's not ARP replies and requests anymore. So that's how you do it in IPv6. But once it gets to this router, that same packet, it has a connected network for 2004::/64. It's linked to. It doesn't have a next hop this time because R3 is directly connected to the network. So finally, R3 sends out a neighbor solicitation. Hey, I need your MAC address. And he sends back an advertisement, a neighbor advertisement, 2004::2, back to the gateway, because here he asked for the MAC address who has 2004::2, see? And then he got the reply with the advertisement coming from 2004::2. And then he put that in his table here. If we look 2002::2, that's the MAC address it maps to at layer 2. And this is the layer 3 address. Again, we'll talk about that in a little bit. And EM1, this is how long before it expires. Now, we're going to break a few more things in different ways and show you how you will troubleshoot them. I'll see you in a second. Alright, so now I've intentionally broken a few things. And let's go to ping 6 again, but use a V this time so we get more verbose output. You'll see why it's important in a second. So let's ping that guy again on PC2. Now, do you notice a difference in this failure? It says no route to destination, and it's coming from for 2001::2 to 2004::2. But it's coming from 2001::1. Well, if we look with a routing table, it's coming from our default gateway. So let's use traceroute as well, because it's a very important thing to be able to troubleshoot. So if I try to traceroute again, now this confirms one of the points of the problem, because it tells me there's an issue at my default gateway. It's not getting further than my default gateway. So let's go investigate that default gateway. So let's go to R1. You can see the packet's coming back as well. That's what packet capture is doing. All right. Now, what I'm actually going to do this time is try to ping the same way from 2004::2, a little bit different this time. Hey, that's weird, isn't it? That's the same error we just got on our host before. The reason is, I think you know by now, is that the routing table doesn't have a route for that network. If we look through here, do we have a route for 2004::/64 or a default route, which you're not going to see on a router like this? You will in some cases, but on bigger routers, it's not as common to just have one default route. So, I don't see a route for that network or a default route. This explains our error message when we try to route. If we do a traceroute from here, traceroute 6, 2004::2, no route to host, same thing. So we have to put that route back in. So let's go down here. Restart our routing. Now let's do a ping 6 2004 : 2. Okay, now this router can ping it. You see the hop limit is 2, 64 minus, taking 2 off of 64, so it's 62. And the reason it can ping now is because we have a route, so now we can trace route as well to that host and get through the other gateways, the other routers. So now if we go back to our clients, let's try those two again. 2004 : 2. And there we go. We're getting our packets through now. Now you see what the problem was, right? It was because our default gateway this time did not have a route. You can see all the routers are getting there, and we're reaching our destination, and they're sending back an ICMP unreachable message. I'm sorry, time exceeded message. And that's how we know we got to where we want to go. So that is how we're going to debug that. I'm going to break it in one more way and see if we can solve it. We'll see you in a second. Alright, I went and broke it one more way. So we're going to do that ping 6 again, -v, 2004 : 2. Alright. 6 packets that we've sent here, but all of them are lost. Okay, we need to investigate this further, so let's look at the routing table of our client first, because, well, I wonder if something went on. He's got his default route. Let's make sure we can ping our gateway. Alright, good. We can reach our gateway, so that tells me NDP is working good, and our gateway is online. Let's do a trace route. Let me try that again. It's only getting to the first gateway. Alright. Well, I remember that the IP of that one gateway, the next one, was 2002, : 2002. Okay, it's not, whoops, that was ping itself. Okay, we can get to that side of it. We can't get further past it. What about 2003? Can't get to any of those either. So let's go up to our gateway, because I think there's a problem in our gateway. So let's try to ping that client, 2004. Okay, can ping him from there. What's going on here? We can ping him from here, but we cannot ping from here. And if we do a trace route, we cannot get past our gateway. Well, I'm going to investigate the next router up, R2. So let's try to ping that network. Okay, we can ping that network. Can we ping ourselves back from this network? The 2001 : 2. No route to host. Hey, let's look at the routing table of this router. Let's look for 2001 : /64 here. 2002 : /64. 2003 : /64. 2004:/64. I don't see a 2001:/64. So do you see now why the problem happened? We have a source address and a destination address, but when it comes back, they're reversed. So every router in the path has to know how to route the packet back the other way as a destination. That's why we were having the failures we were having. So let's go ahead and put that back in. And look at our routing table. Now we have a 2004. Now let's see from here if we can ping the two endpoints of the connection. And this isn't common. You wouldn't usually have access to the routers in the path like this, but I do in this lab. Now we can ping both sides. So let's go back to our original client here. Let me just rearrange these windows real quick. Now, let me try to ping the clients. 2004::2. There we go. Now we have connectivity. So this is trying to show you the importance of why you need routes in both directions on every router in the path, and why just because one end can send doesn't mean you can send from another position in the network. So here we have all of our routers working. They're sending back and forth. So this is how we do it in IPv6. It's the same concept. The same things apply. It's just a different address format. You still have subnets. They still do the same thing as an IPv4 and things of that nature. And NDP still does the same thing as ARP. So that is this lab, and I'll see you outside the lab. All right, so now that we've talked about troubleshooting in general, we're going to go ahead and talk about how something else can throw a wrench in our networks. So we're going to do the same thing from PC 1 to PC 2. So we're going to ping 2004::2. And we're going to go ahead and ping. We're not getting no replies though. So what we're going to do is the same thing as we did before. We're going to check our routing table. Not the IPv4 routing table. Sorry about that. The IPv6 one. We have a default route, which is good. So let's ping that default route. Good. We can ping our default route. That's what we want to see. So let's start now again with a trace route to where we want to go. Okay, it's stopping there at our gateway. So, let's go up to the gateway. Now, let's go and do a netstat on this gateway here and look for the IPv6 information. Well, we have the network we want to reach. It has a next hop there, so we're good as far as that is concerned. So let's see. We have a next hop and everything. Can we ping our next hop? That's a good thing to ask. Let's see if we can ping that. So 2002::1. Okay, we're not able to ping it. It does not look like that. Let's do a trace route from here to where we want to ping. Hey, there's an error on 2002::2. All right, this is starting to make more sense. That the problem is here. So let's look at the routing table. Well, good. We have all of our routes. Good. We have everything we're expecting. Now let's try to ping our destination. with the right command. Permission denied. Wonder what that means. Let's try to ping. Let's do 2002 : 1. So that's R1's address. We can ping that. Make sure we have our addresses on here. We do. Now we can't ping R1. I accidentally pinged R2 that time, but we can't ping R1 here, and we get permission denied. But we have all of our routes. Routing is on and everything. Our interfaces have their IPs. What's causing this to happen? It doesn't make no sense because to R3, he has all his routes here. And we can ping the endpoint. Can we ping the see if we have our addresses. Okay, can we ping the other side? Hey, we can't ping the other side either, but everyone has their routes. I think it's something with R2. So let's go back up here. And what's actually wrong with R2 is a firewall. So what I've done here is enable the packet filter firewall. And I've written simple rules that we have EM0 and EM1. These are the two interfaces for R2 to route packets through. All I've done is blocked ICMP v4 and v6 going in and out of those interfaces. And I'm passing everything else, so like TCP would have worked and stuff like that. But that is why firewalls can add a very big obstacle in troubleshooting, but it's also why we need them as well, because they keep traffic out of places we don't want traffic to go and stop information from getting into hands it shouldn't. Because remember, with traceroute, I can see the topology of the network without being present on those routers or having access to them. This is why, on the internet especially, they block things like ICMP and traceroute from working, so that doesn't leak information. But, so just to show you that firewalls, while they're very good and very needed in today's networks, they can make troubleshooting that much harder. And there's something you should work into your troubleshooting methodology. So, there we go. I will see you outside the lab. Alright, now we're going to talk about client and server models. So, what a client and server model is another basic type of reference model, basically. What we're focusing on here is not how the entirety of the network operates together. What we're focusing on is that the way a client and a server are going to have a communication with each other, otherwise known as a transaction. So we're focusing on when this client sends a request to the server, what is the server going to respond? All right? So we're focusing on different ways that this can be done. There's only two main ways, so there's not as much to have to worry about with these models, but they're still very important to understand how our application protocols are using the network, because there can be many different methods that these protocols use, and this is how we basically categorize application protocols. All right? So there are two main types. We have two main types of client and server models. There is simply the client to server model, so that's client server communication, and there's peer-to-peer, the peer-to-peer communication method. Now, client and server is when a client sends a request message, and then the server sends a response message with the data that the server has. When you have a client and server, Normally, the client is always requesting some type of information from that server. Whether it's a web server, that's, the web page information. Whether it's a database server, it may be, information from about a certain category, like a model of device. Like if you go on linksys.com or something and you pull out the help document that searches, a database and pulls it out for you. Things of that nature, essentially. But that's the idea with client to server. Peer-to-peer is different. Now, peer-to-peer is when an application can be a client and server at the same time. So, this is actually very important because normally in a network, when you have one server, you may have 10,000 clients connecting into the one server. Well, those 10,000 clients put a big load and stress on that server sometimes. Not to mention the bandwidth in the routers and switches along the path to get to that server, and sometimes it can overload it and cause slower bandwidth, loss of packets, and the methods of like TCP and things we talked about will start to take effect. Well, peer-to-peer takes the load off one central server. You can have 10,000 clients. Instead of connecting to one endpoint, those 10,000 clients can all connect to each other to get pieces of the same information. Now, peer-to-peer client model, the peer-to-peer model, is a design reference. I'm not talking about things like the BitTorrent protocol. That is something different. Look into that if you will. But the BitTorrent protocol is a combination, is an implementation of peer-to-peer. All the data you're getting on the protocol is spread out across multiple clients. Steam is another example. Video game streaming, it uses multiple clients to download updates faster. It's not a specific protocol. It is the method it's using to connect to servers and clients. All right. So the client and server process is very straightforward. We have a client on the left. He sends a request to the server on the right. Then the server on the right just sends a response back. And this process goes on and on and on. And what happens underneath this process to carry it is TCP. So the TCP connection, when we talked about setup, through a handshake would happen before this, and now the client and server send requests and responses over certain source and destination IP addresses, sockets, and those source and destination IP addresses as well. All this makes a connection to a server. All right? So a server has to make a new socket every time a new client connects to it with that client's unique information. So that's why a server can be overloaded if 10,000 clients are connected to it. Peer-to-peer again, we can do that process at the same time. So we actually have less socket connections to keep track of between each client and server, because not every client and server is going to be connected to each other or even have to be. They can kind of relay information for each other. But yes, this TCP still can take effect here. You can even use UDP as well. Remember, if it's UDP, it just sends and then it creates a socket if the server decides to accept the connection. Even though it's kind of like connectionless, with UDP, it still makes a connection. Same thing, but TCP is connection oriented. Has to make that connection first. So, like with HTTP, like when you go in Firefox or the browser on your smartphone, you send a GET request, that's HTTP version 1.1, and then it sends a response 200 OK if it's connected, and then it will send you back whatever HTML document you were looking for. All right? Same thing with DNS. We know now that a record like example.com goes there as a request. The server then responds with the IP address in that domain, the zone in that mapping. They have an ID to keep track of each other at layer 7, by the way. This isn't a port number, this is an ID in DNS. And then it sends a response back. All right, now we're going to start on section 11. And I will see you in a second. All right, so now that we've talked about the client and server models, we're going to talk about network topology models. So here we're discussing different network layouts. that are possible in all different types of networks. So the idea is that these models can represent either the physical or the logical layout of a network. So we have three of them. The most majorly used ones, the most commonly used ones, we have a star, bus, and a mesh. So a star topology. I've labeled the nodes or hosts on this graph, and we have 1, 2, 3, 4, and 5. So what I want you to do, even with your home network, you can do this as an exercise. Take number 1 here, node 1, and make that your Wi-Fi router. So draw out these 5 circles here, and in there, go in your Wi-Fi router, find its IP address and net mask, and convert that into an IP address / CIDR notation, and go ahead and, if you have 5 PCs or even just like 1 or 2, go to each one, do an IP config if it's Windows, do an ifconfig or IP adder if it's Linux, find its IP address and CIDR value, put that on this graph. Draw this on a piece of paper though, or like in any kind of drawing application on your computer. But by doing that, you're going to learn how to make a logical topology with your own network, because that's what these models apply to. It's not one topology that fits every network. It's multiple networks have different needs, so your topologies may be different in different parts of your network. So you need to understand that. And this is the logical topology. If we were doing the physical topology, we would talk about things like what server rack a piece of equipment is in, or what building, or what type of cabling node 1 and node 2 are connected with. That would be more of a physical topology. A logical topology is more of how they are addressed and what subnet they're in, and maybe what IP addresses they have, things of that nature. And like other things, like what servers you have, like what protocols they're running, things like that. So that's a star topology, but the idea is this is just like with your Wi-Fi router, how every node on a wireless network has to talk through the access point to talk to another node. So 4 has to go through 1 to talk to 2. That is a star, even though you would think wireless is kind of like a mesh type of idea. It's not, at least not with our infrastructure type Wi-Fi networks, where you have to go through a Wi-Fi router to talk to anyone else that is connected to that Wi-Fi router. A bus topology is where we would have used CSMACD. This topology isn't as common as it once was. It's still used in some places, but essentially everyone's sharing. This is that shared collision domain and shared broadcast domain. So if 4 wants to send, he has to stop and listen, and if no one else here is sending, he sends his signal. But if 2 sends right when 4 is sending, whoa, everyone back off. And then they start to send again after that back off. They send that jamming signal. But this is what's good about moving away from bus topologies. We don't have to have contention for sharing the link and delay there. We can just automatically send, like with a star topology, because you could put a switch in here, and then you could send frames right through the switch, just like our Wi-Fi access point does. So a mesh topology. Now, this is more common in enterprise networks and service provider networks. And what we're doing here is we're having redundancy. So 1 can get to 6 through going through 2 to 6, 1 to 5 to 6, or even, 5, 9, 10, and 6. We could have another link between 9 and 6 there. But we can also even get to 6 by going through 2, 3, 7, and 6, and so on. So if failures happen, we can route information different ways. Now, you can imagine there is actually more cost involved in this because we need more connections between each node in this network. But it's a good redundant design. It's a very good design to have. Now, a mesh topology. This topology here is we're showing that we can have redundant links directly between nodes. So we have less delay or latency to get to each node and multiple paths. So we can get to 1 to 2, we can go 1 to 6. If this path between 1 to 2 fails, we can still get to 2 by going through 6 and 2. Or if that failed between 1 and 6, you can go 5 to this extra path to 6 and then go to 2. You see the advantage of having a mesh topology. This is the idea of it. One more thing with mesh topologies. There's two types. There's partial meshes and full meshes. So full meshes is when every device is connected to every other device. So you would have 8 here, and then 1 would be connected to 8, 1 would be connected to 4, 1 would be connected to 7, 1 would be connected to 3, and so on, and then you repeat the process for 2. You need a lot of cabling. It's the best as far as routing is concerned in your network, because every node is directly connected to every other node. You don't got to route through anyone else. But it's expensive. And if a link breaks, you still have suboptimal paths, but you can still get around the same way we just had said with the other two topologies. The bad thing about a star topology or a bus topology, if one of them breaks, you can't get to the ones past it. So if 2 breaks, you can't get to 4 with a bus topology. On a star, if the center breaks, nobody can get to anybody. So this is the same thing as having a switch or a Wi-Fi router in your network. So there's disadvantages too. That's why we have multiple layouts of our network topologies. So the last one is a point-to-point, from one node to another node. When I mentioned ad hoc Wi-Fi earlier, this is what ad hoc Wi-Fi is, but it uses a Wi-Fi channel, a radio channel, of radio frequency. So 1 to 2. You could have a piece of UTP cable as your little lab experiment. You could make a piece of cable and connect PC1 directly to PC2 without a switch or a router or anything, and you have a point-to-point network. You've made a point-to-point topology. It's good because you got direct connectivity, and it's bad because obviously you can only talk to one other node, and if either of you fail or the link in the middle fails, well, nothing exciting is going to happen. There's no redundancy in a topology like this. But we're going to talk about redundancy a little later and how other ways to achieve it as well. But with that, we're going to go into section 12, where we're going to start talking about a few things about security in a network, including firewalls and other things like that. So I will see you in section 12. Alright, so now we're going to talk about the fact that some data in our networks isn't always good data. And sometimes we don't want the data in our networks at all, or if it is, we want to keep a close eye on what that data is a part of, and things of that nature in this section. So we're going to start first with the need for firewalls. So firewalls basically are like a stop sign or like a roadblock. They can stop information from going to one computer. They can stop one network from talking to another network, just like a big barricade in the middle of the road would stop 2 sides of the road from getting to one side of the road to the other. That's basically what they do, but they do that with our packets in our network. So a firewall's purpose is just to deny or allow data. And it makes the decision based on the rules that it's configured with. And this is its rule set configuration. So we have 2 types of firewalls that follow this concept of having rules. They're software firewalls and hardware firewalls. Now, these 2 types can be divided a little bit further into host and network types. So all of those kinds, though, all of them can use information from every layer of the OSI or TCP/IP models. So all the protocols in the model we talked about, those two models, it can make a filtering decision based on that, depending on the type of firewall it is, because there's many different types. There's kinds that can filter on IP addresses, the source and destination, where the packet's going to and where it's coming from. It can filter on the port number. We know now that that really means we can say, hey, we don't want this application from this source port to talk to this type of service on our network with this destination port. But you can also have firewalls that look at layer 7, and they look at the payload, so the application protocol. Remember how it used the socket and got into the network stack from there? It can actually prevent that data from crossing over the network depending on the type of firewall in use. And we use both kinds, but we'll get into that in just a second. Now, either of host or network firewalls have two common rule set configurations. So this is like the mindset when you're creating the rule set. You have inclusive and exclusive. Well, in exclusive, all it does is allows all packets, so all data regardless. But the difference is it denies and drops packets that match a rule in its rule set. All right? It allows everything by default, except the traffic that has a rule for it. So an example would be like, I want to allow everything but port 80. So I want to deny the HTTP service. Remember, that's just the default port numbers. That's why it's important to understand these are the defaults. They can be changed to work around things like this. But if I want to do that, if I put a rule in there for 80, TCP port 80 traffic inside of a exclusive rule set, it would block 80, TCP port 80, and allow all other types of traffic. With an inclusive rule set, it's the opposite. These are actually more secure. These deny all packets by default, all types of traffic regardless. But it does allow and accept packets that match a rule in the rule set. So with this type of rule set, you have to understand a lot about your network and what traffic you actually need. Because it starts out, everything is dropped, no matter what. Don't care where it's going to. I don't care what port number it has, and even what protocol it has. What we do is you would have to poke, you'd have to basically make rules in the rule set. You'd say TCP port 80, UDP port 53, SMTP, so TCP port 25, TCP port 443. You'd have to put rules in for every port. And not just that, but you, at that point, want to start concerning yourself with the source address of the packet, so what networks the packets are from, carrying the TCP or UDP traffic, and where they're going to, their destinations. And you have to put rules in there, and everything else that doesn't match the criteria in those rules, it just gets dropped. It will not be allowed, either on a host or a network firewall. So, a software firewall. This is a software-based type. This is just like Windows Firewall in, Windows, IP tables, and technically it's NetFilter in Linux, but the IP tables is the tool you administer it with, but it's NetFilter. BSD has PF. They have PF for packet filter. They have IPFW. That's IP firewall, and they have IPF. That's IP filter. So depending on your system, you have many different software-based firewalls, but this applies to all of them. So the concept of a software-based one is that the job of it is to stop a host from having its network sockets be connected to. All right? So if it's running a server or if it's like a client on a network, we don't necessarily want sockets that aren't being used to be connected to. Or if we don't want a server accessible to a certain group of computers this is what we put in the firewall of just that server, for instance. But how it does it with TCP or UDP is it TCP would send like a TCP send message to the through handshake to start up the connection. Port 80 on the receiving host, that firewall on there, the software firewall, will prevent a connection from being performed. We can do this in two ways. We can drop or reject. Now, I want to pause here because it's very important. There's three distinctions we have to make. Drop is not going to tell you it was dropped, and it's also not going to let TCP reject the connection properly. That's important. Reject is going to not only drop the packet, but it's also going to tell the sender of the packet that was dropped why that happened. It's going to tell you, and it's going to, with reject as a firewall policy, whether it's a host or a network firewall, it's going to tell you, hey, ICMP administratively prohibited. It's going to send back a packet just to inform you your packet was blocked. And that's not good for information gathering and reconnaissance. You don't want that on servers or your network. So, beside those two methods, if you do not have a software firewall or network firewall in place at all, if you don't have anything listening on a socket on your computer and a host tries to connect to it, it is going to naturally send back a TCP reset acknowledgement message to that SYN TCP segment. It's going to say, hey, something went wrong here, there's nothing listening here, reset the connection. That's another reason. It doesn't say there's a firewall in place, but it confirms. It confirms to someone looking that nothing is listening on that socket or port number. All right? So that's the distinction. And if it's UDP and you try to connect without anything listening, it sends back an ICMP port unreachable. So that's the difference. If you want to have a silent firewall, basically, use a drop. If you don't, use reject. And if you don't use one at all, you still have to realize TCP and UDP are still going to operate. So there's a lot. That was a big distinction there for you, but keep that in mind going forward when you're working with firewalls. But what drop essentially does is it just forces the remote protocol, the remote host protocol, to time out its attempted connection. So this is like if you try to connect to a website and it waits, like 3 minutes, and then finally says, hey, I can't connect to this website. That is called a timeout. All right? When it automatically jumps out and says, hey, can't connect, like 2 seconds later, that is either that a TCP reset message was received from that IP address, or that a firewall was blocking the connection and sent a reject message, an ICMP admin prohibited message back. Those are the only two times that protocols can automatically time out quicker. All right? Otherwise, you have to wait for them to do that. Now, reject does tell that the remote host doesn't have the socket you're trying to connect to, that it doesn't have a program that's able to respond to the connection attempt. So that's why we want to be careful using reject with a firewall policy. Okay, so now on to network-based firewalls. So what a network firewall does is it stops data being sent from one network to another. That's its whole purpose. Now, this firewall is combined with a router. Okay, so the function of stopping packets and looking at that rule set to decide if they should be sent or not takes place on with a network-based one, and it really means it decides first, should I route this packet or not? It doesn't just route it based on the routing table lookup automatically. If you just have a router, so a layer 3 router, it's going to route any packet it has a valid route for in its routing table. It's not going to be picky about what it sends, which in today's networks is not the best thing. Especially, especially for segmenting our networks off and wanting to have more security for our devices. So again, when you hear people say a network firewall or just firewall, they usually mean kind of like this scenario. You actually need to understand it's a router at its core. The firewall is actually deciding on top of it if the packet should be routed or not. There's more they do, but we will see as we unfold this slide. So, again, it's added to the router, and in higher security networks, they can be placed at many important points. So, you could have a bigger network where you have 5 different LANs. Maybe you have a guest, you have an office LAN, and you have like a DMZ, which we're going to talk about in a little bit. But you could have 5 separate firewalls that are network based, and then like inside of the DMZ, that you can then have another firewall that's network based. So 2 network based firewalls. The one inside the DMZ has an even stricter configuration, and then on the server that maybe is hosting a website or something, it has a software firewall with a strict configuration for its sockets to being connected to. But on the way there, 2 network firewalls filter out and weed out the packets that are getting to the server. And then even after all of those layers of security, the server filters out with its software firewall to really make sure it should have that transaction with that client. So that's what you're doing with network firewalls in higher security networks. You're implementing them as layers of security, because firewalls are all about security. Originally in the internet, they weren't even needed because, you trusted, it was more of a research-based thing. You trusted everyone on the network for the most part. Nowadays, it is not like that at all. Obviously, we've seen, you see and hear about hacks all the time. That's why we have firewalls, as part of a defense of that. But, so generally though, the closer the firewall is, whether it's network or software based, is the closer it is to mission critical data, the stricter its configuration is. So the less it lets in and out. Okay? So it kind of goes like a big funnel, and then it gets such a small funnel that it's almost like a small little stream by the time you get to the service that you actually want to access. But what this does with network is it controls what packets are sent in and out of interfaces. So it can control either direction of traffic flows. All right? So firewalls can see data, though, like this in 2 ways: per packet and per session. Per packet is a stateless firewall, so it doesn't remember anything about prior packets and how they go together in a connection. Like if you have a TCP 3-way handshake, a stateless firewall would only see the send go through, make a filtering decision, and then route the packet if it's on a router, if it's a network based. And then when that packet came back through, if there wasn't a rule to allow SYN-ACK packets for TCP specifically, it would drop the packet because it doesn't have state. Its decision is per packet. It does not correlate them together, or in other words, glue that information together in the connection. A per session firewall does, and this is what is most commonly used today, whether it's on our PCs or whether it's on our Wi-Fi routers and things like that. But this is a stateful firewall. So if you send a TCP SYN packet to start a connection, it's going to make a state of that source address, source port, and destination IP address, the 4 criteria there, and protocol, by the way, the 5, for that state in the firewall state table, only in stateful firewalls. But then when the SYN-ACK comes back from the, with everything flipped as it should be properly, it lets that packet back through without having to write a rule for return traffic, because it created state when you send it out. So then it just goes back through. So if any other packets try to like spoof or get into the connection and pretend to be something they're not, they will not match the existing state of that connection and just be dropped just as if it was a per packet firewall. So that's the cool thing about stateful firewalls and why they're more secure. Hardware-based firewalls are kind of a combination here. What they do is they combine software and network firewall functions. and they put those in a purpose-built computer called an appliance. So these are things like Cisco firewalls, Cisco hardware firewalls, Palo Alto firewalls, Checkpoint firewalls, Sophos firewalls. The Juniper has firewalls. There's lots of different firewalls, but the difference is is purpose built by a company. They've thought about the hardware. They've thought about they built the hardware around the software. They've thought about the software and tweaked it for that hardware. And it's a good way to buy a firewall that you know is going to be reliable in your network and is going to have, as much hassle-free operation as possible. So you can build custom network firewalls, but this is important to know both. That the appliance is usually made by a company and you buy them as a pre-made machine with hardware made for the software on top of it. Okay? Now, some appliances also utilize the ASICs, just like how switches did. And it's very fast for things of like network-based things like IDS and IPS, systems, packet forwarding, and more functions. But it is, remember that small little miniature computer, it makes a decision like, is this packet going to port 80 and this destination and from this source? It makes that quick. Now, snap your fingers, super quick. That's the whole point of an ASIC. But some are made with that. That's what you are paying for when you look at hardware firewalls and see the huge price tags on those devices. A lot of the time, it's very specialized equipment like that. So, UTM and NGFW based, these are Unified Threat Management firewalls, UTMs, and NGFW, the next generation firewall systems. Now, both of these use concepts like a network firewall does, being as, per packet, per stateful. It's looking at layer 4 information, layer 3 information, the port numbers and IP addresses. But it does something very important. These types of firewalls can also look at layer 7. This is the application protocol, so the data like from a web page from Firefox, let's say, it can peer into that data and make even finer restrictions based upon that. So it looks at things like HTTPS connections or DNS requests, and it inspects every aspect. So both of these types can also complete a connection on behalf of the requesting client. And when they do it, it's called a proxy. So it's essentially making a connection on behalf. So it's like, let's see, you got to mail a letter and you can't do it. So you ask someone else to do it for you and they go and do it. That's what a proxy is in a network. There's other types of proxies, but essentially this is a web proxy built into these devices. And it just makes connections for you. That's all it does. So this proxy step is important for filtering traffic, but it can also be bad because it allows that firewall on the network to see every aspect of whatever the client is doing, the client's connection. And some of them actually use man-in-the-middle attacks where you can actually set up the encryption on behalf of the person connecting and they don't know it. So those kinds of proxies, while they're needed in some cases to really get a fine-grained handle on traffic flows in your network and restrict functions of websites and things, laws govern the use of those. You cannot just use those without thinking about it first, knowing what your laws are. It's a very serious thing because that breaks the user's privacy rights on the network. So, I mean, you can think of something like a hospital. If that happened in a hospital and someone was connecting to a patient portal, no, that is not a good place to be and using that. So, I mean, yes, if you do it legally, okay. That's one thing, but just be careful when you're, looking more into this stuff. So, we also have other types of firewalls, and these are WAF-based firewalls, WAF. These are web application firewalls. These actually protect full applications on web servers. So these protect things like online banking, things like accounts online that you log into, like social media. They protect database type systems that are taking in data from web clients. But what they actually, their purpose is to stop attacks and exploits, such as XSS attacks and CSRF, cross-site request forgeries and code injections, where you could trick a website into giving a string of information out of a SQL database, things of that nature. But what the other one is cross-site scripting, by the way, if you want to look those up. But it's all types of attacks that can attack a web browser that is talking to a web server. And essentially, it's preventing attackers from tricking badly written code into revealing sensitive information. So it's kind of a stopgap if there is a mistake in the code. And it's a way to prevent something like data leaks and, denial of service attacks and things of that nature from happening. But they can also prevent unwanted actions, like the replay of a legitimate user's actions. And this would go in the middle, like with a man in the middle attack and something like this. But think of this. If I make a purchase online, like, whatever, I go eBay, Amazon, whatever you have from wherever you're watching this, if you can make an online purchase, they can replay that potentially and maybe change things that are important in it. Like maybe where that item gets shipped to, or maybe how many of that item was bought, and maybe the payment method of that item you used. So these are very important to prevent attacks like this. Not only that, but actually thinking about code before you're writing it too really helps as well. But it doesn't just do online purchase protection, obviously, it does account settings change protection. So if I change like my email address on a certain account I have, and I change that, but then it gets intercepted or something and replayed the legitimate action, and then someone, like it's two-factor authentication, let's say, and someone gets in there and changes it to be the attacker's email, so then when they try to log in, they get the code without having to have the permission of the real owner. That is a problem that could be, this could be done with an attack such as this. This is what we're trying to prevent. So this is why these types of firewalls are important too, on top of software and network based. But it also protects things like the graphical user interfaces of server devices, so like network firewalls and server products, from having authorized changes being replayed by an unauthorized attacker. You can think on a plethora of them. You can go from Smoothwall, IPFire to Cisco's offering, Cisco Threat Power is what it's called, forgot for a second. Things like that. Anything like with a web interface, you want to protect changes from being replayed. Because they can be replayed and then they can be edited and make, things you don't want to have happen, a reality in your network. So that's what these help with, the long and short of it. And these are a layer of security, and they're combined with network and software firewalls and also DMZs, and together that creates multiple layers of security in your network. So along with protecting web applications, we also need to protect and detect attacks and prevent them in our networks. This is where intrusion prevention and detection comes in. And what IDS is and IPS, it uses just deep packet analysis, and it correlates sessions in your network together to protect networks, servers, and clients. So the whole idea is it's looking for abnormalities in your traffic that are maybe like a known attack, things like a known signature of a SQL injection vulnerability or a known signature of an SMTP server attack, things like that. And these are constantly being updated. So this rule set for for this is not a static one. Signatures are added, and you write these rules sort of like a firewall rule in things like Snort and Saracata to have this detection. But regardless of any future systems that may come out, because I mean, I think those will stick around, but there could be different ones when you're watching this, the idea is the same. The idea is completely the same because it's still the same concept of what we're doing with the software, but I bet you the software is going to be faster in the future when you watch this. So hey, that's good though too. But an intrusion detection system creates alerts when it sees packets or processes them, and they have to match detection rules. So like an attack, it would say, hey, I see this packet. I know from my signature rules this is part of a SQL attack. So I'm going to fire out an alert and maybe send the administrator an alert in his email and know, hey, something's going on. All right? It doesn't block it, though. It doesn't block it. An IPS system, though, performs the functions of an IDS, so it creates an alert, so it can send an email, but it also creates a dynamic firewall rule that blocks packets and sessions from reaching their intended targets, such as web servers. So it actually will stop the ongoing probe or attack from that source address. It dynamically takes the values, makes a rule out of them, and then it becomes a rule set configuration on your firewall automatically. All right, so both systems only take action when data matches the rule set. They have. Everything else is denied, just like a network firewall or software firewall. It's got to match a rule set. It's just we're doing it for a different reason with IDS and IPS systems. So either system, you can deploy them independently on a client, on a server, or a router. Anywhere you can think of in your network that will be able to run this software can utilize it. And functions of these systems can also be put into ASICs in some cases. I mean, not all cases, obviously, because some things just can't be done with ASICs yet. But I mean, the technology is improving every day, so I would not be surprised if in another 5 years we're seeing even more ASIC technology. I mean, Fortinet's another one that has ASICs that go really fast with threat doing this, the IDS and IPS, very fast with an ASIC as well. So port scanning. Port scanning is simply when a remote host makes a connection to every port on your computer, all right, on another host, even if no programs are listening. It does this to try, remember, to get those reset acknowledgments to come back or the port unreachable messages to gather information of what operating system you're running and what server software you may have. This is the reconnaissance part of an attack. And this is what all those IDS systems are trying to prevent and detect us, notify us about. But it helps us gather information and to break into the host, such as the OS information and server program. And this goes into white hat pen testing. I want to point that out. There is a good part of hacking called white hat hacking. Look it up. Look up pen testers. That is a good opportunity as well to get educated in. Using exploits to, improve security of networks and systems. It's a little bit off topic for this, but it goes hand in hand with networking, so this is a good base for those of you that want to look that up too. But anyway, an IPS and IDS system can detect and block the port scans just like before, and other network-based exploits. And why I set the drop policy, why I prefer drop in my firewalls, and why I think you should too, is because it prevents the OS from informing a remote host a socket is closed, and it gives you almost no helpful information. Almost no helpful information. You still get some helpful information. But that's why we use drop, so we don't send any signal that anything was dropped. Okay, now we're going to talk about virtual private networks. And the whole idea of having a VPN is the goal is to have an IPv4 or IPv6 network that two or more of them that are separate. We want them to communicate with each other privately. So a VPN utilizes existing networks over the internet, most times at least, to connect two separate broadcast domains, or IP subnets, either v4 or v6, together. So to achieve this, what happens is a virtual tunnel network. It's made by the VPN software, all right? And this tunnel network is placed in the routing table, and it overrides the normal routes in your routing table, whether that's on your PC, if you configure it on your computer, or whether that's on your router, because you can configure VPN software on your router to be a client or a server on either of those scenarios. But the interesting thing about it is the tunnel network uses the real network as a transport network. So even though we're making a second network that's virtual, it uses the real network to communicate over. So one IP on the virtual network to reach another IP on that virtual network with the VPN, it uses the real network underneath. But the clients connected to the VPN don't know that. It's transparent to them. So this allows, again, separate IP networks to logically become part of the same broadcast domain. Obviously, we're not reaching a very long UTP cable over there, not only because they only go 100 meters in length, but it wouldn't be possible to physically connect them. So we have to utilize existing infrastructure, and that's what VPNs help us take advantage of, to make them appear to be on the same broadcast domain. So what this does is allows access to network resources that we wouldn't be able to connect to otherwise if we just connected to the WAN directly. So this can be in companies where you have resources on the LAN in the office building, but when you go home, you can't get to those resources over the WAN. So connecting over the internet back to your office, you would use a VPN to bypass that and be able to be let in securely and still access those resources remotely. That's one use of a VPN. The original use is business oriented, but this has moved into privacy services and other things of that nature nowadays, and just tinkering in your network and other stuff. But what happens is the VPN provides us privacy of our application protocols, so our layer 7 payloads, by using encryption. And it makes plain text into ciphertext. So if it's man in the middle anywhere or intercepted, you can't read it. But VPNs can also act as a proxy. And again, it makes a connection on behalf of us. There's SSH proxies as well as VPN proxies, and there's also web proxies, as we spoke about earlier, but they all do the same thing. They just make a connection on our behalf, and it seems like we're coming from the IP address of the proxy server instead of our normal IP address. So that works. That concept is the same with version 4 of IP or version 6 of IP. It changes that source IP address that's connecting to the resource you want to access. VPNs can also be used in networks as a WAN connection. So you can buy and subscribe to a VPN server on the internet, and you're able to route all of your LANs traffic through the VPN by making it a WAN connection. And in that, there is two types, though. There's site-to-site. Site-to-site is when you run VPN client and server software on both routers for two separate networks. All right? And we're going to have a slide of it so you can actually visualize this. But the other one is a client-to-site, and this is the example where we'd go home from the office, we would connect back into the office over our VPN client software to the office's VPN server, and then get access that way. That is a client to site, and our site is the office, and then the client is just at home. With a site to site, it's two networks connecting together. With client to site, it's one specific PC on one network connecting to another. So this is what it looks like here. Excuse me. We have our real IP here, 3331/24 of our VPN server, and this is the VPN's tunnel network, 10.10.101.1/24. And it's a good idea. You can go through and practice your subnetting with these slides as well. I'm sure you can figure it out by now, and if you can't, just keep at it. But The virtual tunnel network, this is the one that the VPN creates for us. The real IP is the IP addresses we already have, whether that's with our ISP or just assigned some other way. And what happens with like client to server is PC1 here on the 1110/24 network has a real IP of 1114/24. But when he connects and makes a connection and he follows the green line through his router to the VPN server through another router, he then gets a tunnel IP once he authenticates to the VPN server and connects. And he has 10.10.101.3/24. Now, when the packets hit the VPN server and then leave down the other red line to go to any other resource on the internet, the source of them is now 3331 in the /24 network. So effectively, we've already have a proxy function on top of having the tunnel IP that the VPN provides. Now, the cool thing is, this means we can do one of two things. We can use the real IP, we can use the tunnel IP to connect into this other office over here. If they had VPN software and they were connecting to the same VPN, we could then tunnel into that office through this VPN's tunnel network and access things like this server here, S1. We could access it by 1037.101.11/16. That's a private address range we wouldn't be able to access on the WAN normally. But because we are agreeing and setting up the VPN tunnel between our two networks, we can access each other's resources over the tunnel network. What you do is export that private network behind the VPN in your LAN out to the VPN configuration. When clients connect, they don't just get the tunnel network, they get copies of networks they will connect to, along with DNS servers and gateways. So the VPN adds a cool layer on top of things like DHCP, because then we can change even more the DNS and gateway values in the VPN tunnel network itself. It's really cool. You can have split VPN tunneling where some of the traffic uses the VPN and some of the other traffic uses the real IP and the normal network, the transport network. Another way that this can be done, though, is once we're both connected, PC1 and PC2 can have tunnel IPs on that same network that the VPN server is providing, and they can communicate with each other logically as a point-to-point topology. You remember our topologies? That's the cool thing. So just with a VPN, you can create your own private point-to-point topology over an existing network, an existing web of networks such as the internet. So that is the great thing that VPNs provide. There's one more thing too that VPNs can provide, and I will say you can also access PC2 by that tunnel IP. You could also export this private LAN IP here. Well, that's not private, it's public in the example, but if it was private, you could export it and access it as well over the VPN. But another interesting thing is you can pretend R2 is a headquarters router and they run a VPN server here. You could have R3, which could be a branch office in a mall, let's say. I don't know. Let's say Starbucks. Why not? Let's have Starbucks, their branch office connect back into this VPN here in the HQ. This one connect back in the other branch office. Maybe this is in California. This is in New York. And this one is in Colorado, kind of somewhat in the middle of those two. And what we can do is map those together and send like point of sale data to Starbucks, their central database, so they can maybe run analytics on how much of a certain coffee they're selling. Things like that. But VPNs afford a lot of customizability in a network, and they can connect separate networks together. That's what you got to remember. There, it can be used as a WAN. They got the different types. And the last thing I want to leave you with VPNs is if we do a site-to-site configuration, R1 would have client and server software, something like OpenVPN or IP protocol. V4 and 6 have extensions built in called IPsec. That's IP security extensions, and that provides a type of VPN as well. There's SSL VPNs, there's IPsec VPNs, other things like that. But this would run there, and tunnel into R3, and vice versa if you want R3's resources to access R1. Then you can, all the resources behind R3 could be exported over the VPN tunnels network to R1 and vice versa, and that's an example of site to site. So then you can route all of the networks behind R1 through the VPN connection, and then you can route all the networks behind R3 in the VPN connection. So that's 3 different ways to use a VPN. Client to site, you have your hub and spoke, where the hubs are like the branch offices. They connect to a central office and their VPN server to get data. And of course, client to site, where you have one client connecting back to the HQ, the office. So that is VPNs. And with that, I will see you in the next section. All right, welcome to section 13. So now we're going to talk about the fact that LANs need WANs. So this is all going to be about how we connect to other LANs, and essentially some of the concepts that will tie in things like public and private IPv4 addresses and things of that nature. So what we have here is, in order for our LAN to get information or data on the internet, it uses an ISP's network. That's Internet Service Provider. So the ISP's network is what we call a WAN, or a wide area network. So this is their infrastructure, in other words. Now, the ISP builds and maintains their network's infrastructure, and what they have is a lot of cabling, routers, firewalls, switches, modems, and servers all together to create their LAN, essentially. Even though we call it a WAN, as a customer of an ISP, you are basically in their LAN. They just have a very huge and complex LAN. But the concept is the same, you see. So they still manage IP subnets the same way as you do. They still do routing and security and all of these things, and DNS and managing those services. But the difference is they know how to get to other parts of the entire internet. We don't. As if we're home users and we're just in our LANs, all we know is how to use them to get to the rest of the internet. We're not responsible for all of the connections needed and routers and equipment to get us there. The ISP is responsible for that, and that's what you're paying for. You're paying for access to their infrastructure. So these two, the LAN and WAN, the demarcation or demarc with this is the term that refers to the responsibility for each network's equipment. So on my end of the LAN, I deal with things like my Wi-Fi router, like my OpenBSD firewall, my switch, my DNS server I have, my DHCP server I have, and yes, I have mine separate. But you can do that. But essentially, that is your equipment, okay? And the end that you control is your cabling, your routers, your firewalls, your access points, your servers, everything in your building, or if you are managing a network for a bigger institution like a university or a hospital or a dentist office or something like that, this is where you, as the administrator, that's your responsibility. That's what you're getting paid to do, to keep that equipment online. So that's what happens with something like that. But if you work for an ISP, you are managing the other side of the demarc. So just kind of giving you basically a perspective on what it really means and what each position in certain places is managing. So the end you control, again, as we said, is everything in your building. And the equipment you manage is referred to as a CPE, and that is customer premise equipment. This is, again, anything you own, or in the case of doing consulting or something like that, as an administrator, the equipment you are managing on behalf of the company you're working for that bought it. So don't think because you work for a company it's your equipment. It's not. In that case, you are managing it for them. All right? It's still your CPE, though, for purposes of our discussion here. So, what is our access methods for WAN? At least as of 2020, we have dial-up, a T1. There's many other types of T1s. They basically mean more bandwidth because we bundle them together. DSL, that's digital subscriber line. There's also ADSL and VDSL, different variants of that. One thing with DSL you have to know, there is symmetric and asymmetric. Symmetric is the same speeds up and down for sending data and receiving data over the WAN. Asymmetric rather is usually a higher download speed for receiving data over the WAN and a lower speed for sending data to the WAN. All right? So a cable connection, this uses DOCSIS, which is Data Over Cable Service Interface Specification. That is actually with how we said way back about the cable modem. So for your TVs. And traditionally, it's faster downstream. So for receiving data from the WAN, but slower upstream because with a cable TV network, you were always just traditionally sending images of a broadcast of a television show or the news or whatever. So you didn't have to receive much other than a control message that said, hey, I'm going to turn the TV and change the channel, and then it would tune into another frequency. Even that, though, they basically send all the frequencies at once down at your TV, and you just select. But I'm getting off topic. Anyway, satellite is another good one. It uses the, up in space, a satellite orbiting in space that you send a signal to. It's, options there. You can pretty much have it installed anywhere. That's the good news about that. Cellular, we have first generation, second, third, fourth, and now 5G coming out now. But cellular is good, but you have to be in range of a cell tower, so do keep that in mind. And the further you are away from the cell tower, just like Wi-Fi, by the way, it'll be familiar to you, the lower the decibels of the received signal, the lower bandwidth you have because you have less frequency available to encode the bits over. But you also have fiber, and with fiber we use things like optical network units and PONs, which are passive optical network units. But it's a lot of the modem, again, is converting the UDP, the electrical signal from our cable, to light to send it over the WAN. But these are some of the access methods. And another thing with any WAN, with IPv4 and to some extent in IPv6, I will say that there is some NAT being used here. What happens is with IPv4, we only get one public IP address from our ISP unless you pay for more or pay for a static one, by the way. There's a difference there. In business connections, you use a static address because you want to map that to a domain name with DNS and you don't want that to change. But you need a way to use the address for all of your LANs devices, even in a home network that doesn't host servers. So this is where NAT comes in, and that's Network Address Translation. And we have two types. We have SNAT, which is source NAT, and we have DNAT, which is destination NAT. If you do certification study, you will see SNAT referred to as static NAT. That's not what I mean in this context. I only mean the source IP address field in an IP header and the destination address field in an IP header is all I'm referring to. So with SNAT, we take the source NAT here. A device like a router in our network changes the layer 3 source IP address of a packet as it's passing through. So it changes that and then routes the packet out. All right. So it changes all of our LANs devices to one IP address. But the router also changes the layer 4 source port number. And this is because you have multiple computers, and those computers are doing multiple different connections out to the internet from your LAN. But we have to change the port number because they're all mapping to the same IP. So the only way to make sure they're separate and can be identified is with the port number to be changed. The source port has to be changed. And this is PAT when we do this, port address translation. So the only IP address, though, from this concept that the WAN sees is the router's public IP address. That's it. They only see one public IP. All right? Now, all devices, again, in the LAN appear to be coming from the router's IP address because of source NAT. This is why we need this, because if we don't change the source of the packet before we route it over the WAN to our ISP, they will drop that packet. It's part of their policies, because you're not supposed to see that range of IPv4 addresses being routed on the internet. But again, every time we change a source IP address and port number, the router that does the NAT makes a note of it, and that note is put in the NAT translation table. And it's a table, kind of like a routing table, that just keeps track of the mappings so we can reverse it. So then when the router receives a response from the WAN, it uses that NAT translation table to reverse the changes. And then this process will come into effect DNAT. This is destination NAT, and this changes the final destination IP address. So when we change that source address, it goes from a private to the one public IP address on our router's WAN interface. This is the same thing in your Wi-Fi router. If you look at that yellow port or that blue port, whatever brand you have, there's one distinct color that's your WAN port when you plug it in, and that's the address. The IP address that's public is assigned to that port. That is what your Wi-Fi router is doing, changing the source address from your LAN IP addresses to one address on that WAN port. All right? So some modems are also combos, so you won't see ports like that. It takes you got to be careful, because those combine all these functions in one: the switching, the router, and the modem, and your ISP controls it. So that kind of makes the D mark a little more confusing. That just depends on your ISP, but that's a side topic. But keep it in mind, if your equipment looks different than what I've shown you here, that's why, because you probably have a router modem combo. Same thing about networking applies to it, though, so don't freak out. Same thing. This is exactly the same with those pieces of equipment as well. But what happens as well, we have the relationship with SourceNet and DNAT. But what happens if a packet comes in that we didn't change the source of yet? Well, then, if we're running a public server on our LAN, what we can do is we make the servers in the LAN, and they will appear to be coming from the router's IP address. So what happens is a packet comes in with the destination IP address of the router and a port number of a service that the router is providing, so the server behind the router is providing, and that would be like port 80. What we would do is change the destination and put it in our NAT translation table, but this is also where you would put the mapping, just like before, but you kind of put a rule for NAT that's always on. This is where static NAT also can mean SNAT. This is where you say, this port number and protocol, I want that to go to this destination on my LAN, this private IP address only. The translation table is still populated, but that rule makes sure the translation will take place all the time. This is separate from SourceNet, and you can run both of them at the same time. So what happens is a client's request comes from the WAN, and then it's asking for a service like port 80 on a server on your LAN. And then the destination IP address gets replaced with the server's private LAN address. And when you do this, it gets to the services on the server on your LAN, and this is called port forwarding. So that's how that operates. But a good thing to remember is, if this is where the firewalling and the resets and the admin prohibited messages, this is some of that too. Because sometimes when people do port scans, they're looking for services you're actually doing port forwarding for. So this kind of goes into the topic of making sure your server is secured and you have proper security in place too. So don't take port forwarding lightly, by the without thinking about it first, there is repercussions because you're letting unknown clients on the internet connect to devices inside your LAN. It's not always a good thing. You really have to know what you're doing. You can do it without knowing what you're doing, but you're opening yourself up for lots of problems like malware and potential data theft, and even things much worse than that if they take over your computers on your LAN and things. And then they could send back out to the internet and do really bad things you don't want associated with your internet connection. But that can happen if you're not careful. So you do have to be careful with this. Now, in the next section, we're going to talk about enterprise networks, and we're going to kind of bring it big picture. All the things we talked about, we're basically going to upgrade them, okay? And talk about them in a little bit bigger scale and a few more topics with that. But it'll just basically add on to what you already know from the course, so it'll make a lot of sense to you. I will see you in section 14. Welcome to section 14. So now we're going to talk about enterprise networks. And what we're essentially doing with this section is we're going to take the topics we've discussed through all of the previous sections, and we're going to apply them to enterprise networks. So essentially, the underlying concepts we talked about are the same for any computer network that we've talked about, but in enterprise networks, there's additional protocols they use for certain things and different types of technologies they have, and we're going to basically bolt that on to our existing knowledge base. All right, so it is going to be pretty cool. So we're going to take it now from basic home network, basically what we talked about, and expand on it. So some of these things you'll be able to implement in your own network as, experiments and a lab network and things of that nature. Feel free to do that. That's a great way to learn. But we're basically just going to make the distinction and cover a few enterprise topics. All right, enough to get you familiar. So, what are enterprise networks? Well, when we say that term, it essentially refers to any type of network, whether it's an ISP, a data center, hospital, a doctor or dentist office, a school, factories, retail storefronts, malls, and many more than that. So it's not only location, but the types of protocols you need to use. Some networks need different protocols than other networks. And some that are larger need different protocols than smaller ones, and vice versa. But the main difference, again, is the size, the mixture of devices and systems, and what protocols that network is using. That's the main difference. It is basically a sum of those factors. It doesn't mean every large network is using these protocols. It doesn't mean every small network isn't using these protocols. It all depends on the needs of the network. These are just what is considered enterprise-grade network functions that are beyond a basic home network for the most part. So enterprise networks include many devices, and a lot of these are going to be familiar from what we've talked about. They, of course, include firewalls, both software firewalls and network firewalls, and of course, that hardware firewall type appliance. A lot of them use like Palo Alto, Cisco, Juniper, those kinds of firewall solutions, and sometimes even custom. But other than that, we need routers because we have the same needs in the enterprise. We need modems because even enterprises still need ISPs and they need WAN connections. So we got that modem to connect us in there. Servers, because in enterprises you're hosting lots of different services, either on-prem or in the cloud, or something we'll talk about a little later called a co-location. But again, we have those Ethernet switches. Now, an important distinction, these are not like the unmanaged variety we talked about. These are called fully managed switches. You will see these in enterprise. And what a fully managed switch means is that it has more features, such as things like VLANs, port security is another one they have, and other things like STP customization, and other things like that. There's many other features on switches. They have things like span for remote monitoring. So I'm sorry, things like span and rspan. There's other protocols that bolt on to these devices if they are enterprise grade. So this is like way back when we talked about enterprise grade switch. When you think about enterprise network, think of those devices, not like Wi-Fi routers. So in addition, though, we have those access points. We have something called an access point controller. This is a server on the network that goes out and automatically gives the access points all their 802.11 information. So on a big scale, this will configure SSIDs, security settings. This is where you use EAP, so you'd use like a Radius or a TACX server in the back end to authenticate wireless clients. And it's more involved than just like WPA PSK in a home network or even small business. But that's what controllers do. We know what IDS and IPS systems are for. SNMP, that's Simple Network Management Protocol. That's for monitoring devices and getting information from them. And of course, traffic monitoring systems like SolarWinds and systems that aggregate things like net flow information from Cisco routers and switches, and information like JFlow from Juniper devices, and Fortinet has their Forti Analyzer. There's many other. They all essentially do the concept of traffic monitoring, and they're basically packet analyzers and SNMP basically collectors. So for those types of systems. Now again, security cameras are a need in enterprise. VoIP phones, that's voice over IP, essentially carries your voice in data packets over a network, and that's a whole area of study in networks in itself. Then you have POS systems, the point of sale. These are in restaurants, retail locations. Essentially, they do things like process credit card information and things of that nature. Digital signs. So with POS systems, you can see why VPNs could be important for securing that transaction. Back to like the HQ office and things of that nature. The digital signage, RFID card readers for physical access, like to get into the door of a building. Server racks, because remember, that enterprise equipment is organized in something called RUs, rack units, and those rack units actually bolt into a rack with screws. They screw into the rack. So you have patch panels that handle UTP and fiber cable. Some can also handle that RG cable. This is a way to manage the runs of the cable in the walls of the building. They patch in to the back of the patch panel, and then you use another patch cord, it's called. It's another piece of UTP cable to connect from the patch panel into whatever equipment in the rack. So that's something you would see in enterprise. UPS systems, not the United States Postal Service, at least in the U.S., but that is for uninterruptible power supplies. So if your power goes out in your company, you don't want your servers just dropping offline or your clients, because you could lose data. So these give you a chance to either survive the brownout of power or power cut, or shut off the systems as an administrator to avoid data loss. So power generators are if it's longer term. These keep the power up and running for the entire building. And again, this is a bigger scale we're talking about, but even small businesses could invest in a power generator. Okay, another important term in enterprise networks is something called autonomous systems. So this can be shortened to the term AS. And what the reason we have this is because enterprises have to maintain anywhere from one network to even more than 100,000 IP subnets, whether v4 or v6. And that's really the scale, because the reason you can get so many networks is like data centers. You need lots of subnets for all that equipment because you have many servers, but also ISPs. Because remember how I said ISPs are really big, complex LANs, essentially from their perspective. They have a lot of networks to manage. And even branch offices connecting to headquarters can have several networks to manage. So when you get over a certain size, what is easier to manage than each network individually is actually breaking it up into an autonomous system. And what this does is it's very similar to the demarcation point, but this time it defines who has responsibility for those networks. So for instance, ISPs have their own autonomous system number. And all of the networks, including the customer, etc., are inside of that autonomous system. Data centers have, like data center providers, have their own autonomous systems. Google has their own autonomous system. Many companies have autonomous system numbers, and it is a way to logically say, hey, this company manages all of these subnets. This concept is the same for whatever IP protocol, v4, v6, and basically it just defines who has responsibility for them. Who to call when, something's going wrong from one of those networks for whatever reason. It could be a security incident, it could be a DOS attack, whatever you have going on. But much like port numbers, remember, autonomous systems are identified by a number. We have 2-byte ones and we have 4-byte ones, and that is ASN, the autonomous system number, if you see that in literature. But anyway, 2 bytes allow for 2 to the 16th power of addresses, so 65,535. And 4 byte allow for the 4,294,967,296. Lots of routing domains there. But the total range is from 0 to 4.2 billion plus, and that is the entire range that can be assigned. That's the number of unique routing domains. And remember, that's not subnets. That is just a number that identifies a huge group of subnets. So this is just administratively, so don't freak out about it. There is a protocol here that we're going to talk about that utilizes these numbers, but essentially, you won't normally have to worry about this unless you are using the protocol that uses them, or you're just very curious. It's great to be curious, so stay curious about this stuff, though, too. But anyway, 4-byte ASNs are the standard as of 2009, so, long time. 4 bytes are the standard, 2 bytes did exist, but we needed more, just like IPv4 to the IPv6 transition ran out of unique ones. So, with autonomous systems and networks in general, we have IGPs and EGPs. These are interior gateway routing protocols and exterior gateway routing protocols. So that is what we're dealing with. But what happens is all of the routers with all of the networks in their routing tables, they need to know how to reach each other. Because not one router can't hold all of the networks that it knows about, especially not for the internet and all of the different organizations' networks that make up the internet. So this is what helps us manage it and share the information for routing on the internet to take place. So we have IGPs, and that's interior gateway protocols, and then the EGPs, which are exterior gateway protocols. What an IGP does is sends routing table information from one router in one OS to another router in that same AS. So if it was Autonomous System 10, Autonomous System 10 would be speaking with an IGP to another router in Autonomous System 10 as well. I will say, sometimes, depending on your IGP configuration, that other router in Autonomous System 10 may know about different subnets that the other router doesn't, and that is the whole point of sharing routes, the routing table information, because how we said routing tables can be filled with static routes, and that was static routing. This is dynamic routing. But an EGP, on the other hand, sends information as an AS path. And this is actually from a router in one autonomous system to another autonomous system. So this is like if router A that is in autonomous system 10 sends to router B in autonomous system 20. This could be different data centers together. This could be different ISPs. This could be your enterprise's network to two different ISPs you're peering with. It could be many different things. But that is the concept of it. And EGPs are what ISPs and bigger enterprises use to run the internet essentially. This is what provides failover in the internet and dynamic rerouting when networks break. So we can also have multiple routes to get to the same final destination, and this routing protocols will put a different route. Like if you have A and B and A breaks, the routing protocol can make a decision and say this A route broke, or maybe it's got lower bandwidth. Whatever the signal is for it to make the decision, it puts B in the routing table, starts sending packets over that path. But that's the idea of what these protocols do. So again, these are called dynamic routing protocols. And these, both of the types, IGPs and EGPs, just refer to several routing protocols. The IGP group is RIP version 1, that's Routing Information Protocol version 1, RIP v2, which is Routing Information Protocol version 2, OSPF, which is Open Shortest Path First. There's also OSPF v2 for IPv6. There is Intermediate System to Intermediate System, IS-IS. That's how it's said. And you also have EIGRP, that's Enhanced Interior Gateway Routing Protocol. That one is not, that's more in Cisco's devices, but it is, as of 2020 and before that, I think 2016 is actually when this happened, they started to open it up to other vendors. But I'm only going to go into depth about RIP and OSPF and BGP in this course. The other routing protocols you may encounter work very similar. So the EGP group is, we're going to start with an old one that you're not going to see anymore, EGP, it was literally called that, and then BGP. EGP is literally called the Exterior Gateway Protocol, and this was the first protocol, one of the first, I believe at least, that sent information between autonomous systems, in between two different ones. It's not used anymore, and it's very rare to see. The newer one we use is called BGP, Border Gateway Protocol. And this is the protocol that sends between autonomous systems. And version 4 is the version we're using now. That is the most modern version, and everything but EIGRP will run on enterprise routers, or if you build your own, there is software on different operating systems to utilize these protocols. So research that if that interests you, because it's very cool. But regardless of all of that, the purpose of all of the routing protocols is just to let routers tell each other about networks in their routing tables. That's it. It says, hey, I've got network A, B, and C. And then this router's like, okay, I have, D and F in my routing table, for instance, that they can, be not directly connected to, remember? So they're what the router that's running the routing protocol is, he's advertising his directly connected networks. And in effect, when he advertises those out to other routers, whether in his own autonomous system or another one, he is able to give a route into the other router dynamically, so then that router can reach indirectly connected networks. How we talked about, we have direct connected networks, directly connected, and indirectly connected. Routing protocols bridge that the gap, and they also help with converging and the routing and everything like that. And it dynamically puts that in as well. So if they fail, the routes go away, by the way. Alright, so this is our first IGP type protocol. This is RIP, that's Routing Information Protocol. Now, RIP uses the Bellman-Ford algorithm. But basically, the algorithm is just the steps that the code of RIP has in it, and that is what allows it to. That's its step-by-step process for finding and exchanging routes with other routers. Okay, that's all that really means. Yes, there is very fine details about it. If you want to read more about it, but essentially, all you need to know as like an administrator is that it uses the Bellman-Ford algorithm and basic things like what I'm showing you here. So this is known as a distance vector. And the vector is a path and a direction. And a distance in this case is hop count. So all we care about with RIP is how many networks away that subnet is and which direction or interface we use to reach it. That's all we care about. So RIP v1 is a class-full routing protocol, and essentially it won't advertise the subnet mask. And in addition, you cannot use CIDR with it. You can't use classless interdomain routing. It's classful. You can only configure your networks as either a 255.0.0.0 subnet mask, a 255.255.0.0 subnet mask, or a 255.255.255.0 subnet mask. You cannot have anything outside of the default classful boundary. You can still have different subnets, but they have to fall on 8 network bits, 16 network bits, or 24 network bits. Okay, that's what classful is. And that's why it's important to know the class of address and IPv4 you're dealing with as well, and the default classful boundary. This is where it kind of ties in even further. But RIP v2 improves this, and it is a classless, so we don't have to just use those fixed masks. We can use any combination to better utilize addresses in our subnets and everything, okay? So you can use a CIDR in RIP v2, and it will advertise the subnet mask information. So, because they try to, remember summary addresses, RIP automatically will try to summarize an advertisement, but that's why you have certain commands, and I'm not getting into all that because that's more about implementation. But with a distance vector, all you need to know is that every router in an autonomous system that's using this is only seeing a small piece of the entire network from other routers' perspectives. So if we have router, let's say 1, 2, and 3, 4. 1 wants to reach 4. Well, he only can hear about the networks connected to 4 by hearing information through 3 and through 2. So the problem is it's only as accurate as its neighbor. So if 2 somehow corrupts the routing update from RIP or hears about a network that's not reachable anymore, you have a problem updating your routing table and you'll start to use outdated routes and things. This is a drawback with a distance vector protocol, but it makes it lighter weight as well because it's simpler to run. But this is what they do, though. They're just exchanging it hop by hop with your neighbors. You tell your neighbor, I know about this, I know about these 3 networks. Oh, you know about these 3? Okay. And then 3 would tell 2 again, I know about these 4. And then 2 would send those other 4 from 3 to 1, and vice versa. It gets complex, but that's the idea of what it does. Again, though, it uses UDP port, UDP connection on port 520 before sending routing table information. So, not really before, but that's what the port it uses. It sends it destined to that port. Okay, just like we talked about with application protocols, it's the same thing. So this uses hop count as a metric. That is how preferred the route is. And the hop count is how many hops away that network is to reach. RIP will always prefer the lowest hop count. When preferring a route, if you have more than one route, it will use the lowest hop count for that destination. But this is what load balancing does, though. We have paths A and B, can load balance around those two. We can also add a password before exchanging routing information. This is important because any router that runs RIP in a network can inject routes in any other router that will listen to the advertisements. So if you have bad routes or a rogue router, that can mess up your routing tables in your network. And that will cause all kinds of routing issues, even sometimes malicious routing issues. So you got to be careful. You may want to configure passwords if you're using RIP. RIP-V, you can't advertise a network that's more than 16 hops away, by the way. So that means it's unreachable, essentially, and it will not put that route in the routing table, is what that means. RIP-V1, addressing-wise, uses the layer 3 broadcast. So 255, 255, 255, 255. It sends it everywhere in a broadcast domain. So even PCs will get it, access points will get it, switches will forward the frame, all of these things. And that's why it can actually be considered somewhat insecure as well. RIP-V2 improves things. We use 224.009 for sending updates. That means, remember multicast groups, how we have to join or subscribe to the group? We have to go ahead and listen for packets destined to that address, and if they are destined to it, we will listen to that advertisement. That's what the range of multicast is for. It's used by different protocols like routing protocols. RIP-NG uses FFO2::9, which is the IPv6 version of RIP. RIP Next Generation is what it's called. You can also use unicast to send routing updates directly to your neighbor as well. That's the more secure method because you may have routers, again, like I said, that you don't trust joining that multicast group and hearing the advertisements. Packet Analyzer can also hear the advertisements, by the way. But yeah, that's a little bit about RIP. OSPF is very similar. It uses the Dijkstra algorithm this time, and essentially it finds the shortest path to every network it's been told about. And this is called a link state protocol this time. And it's classless and classful. We know what that means now. But link state means that every router in the autonomous system sees the entire network from its own perspective. Its own perspective. That's different than a distance vector. This is good, but it's also more resource intensive. What happens is they essentially take their routing table and put it in a database, and all the routers that are running OSPF exchange the LSDB, the link state database. They exchange it with each other, and they fill their databases with everyone else's database packets, and they assemble essentially a big map of the network. Once the one individual router gets the map, they look at every subnet in that database, and they try to find the shortest path to reach that subnet. And they do this for every single subnet. So you can imagine, if you have 100,000 subnets, this is very intensive on the router. It runs this, and then once it finds the shortest path for that individual subnet, it puts that shortest path in the routing table. So this means, though, if OSPF fails, this process of exchanging database information and calculating shortest path to every subnet has to happen again. So that's the difference, though, with a link state versus a distance vector. But OSPF uses IPv4 and IPv6 directly instead of TCP or UDP. OSPF packets, they mark themselves with an IP protocol number 89. That's another field in the IP header for v4 and v6 protocol. And 89 just says, hey, it's an OSPF packet. It uses bandwidth as its metric for a route, so the higher bandwidth paths will always be preferred. And there's more detail on that, but I'm not going to go into that in this slide. It's really cool, though. So this can also load balance multiple paths. We can, again, add that password for security. And our addressing wise for this is 224.0.0.5 and 224.0.0.6. Now, 5, if you're in Ethernet and you're using OSPF, one broadcast domain essentially. 224.0.0.5 is for what's called the designated router, and 224.0.0.6 is for the backup designated router, the BDR. That's important to know about OSPF. OSPF version 2 for IPv6 is FFO2::5 and FFO2::6. and this is for, again, backup designated router and designated router. We can also use unicast to send these updates, so we can go ahead and just send directly to our neighbor. Now, BGP, Border Gateway Protocol, this is our path vector variety. It's dealing with the direction, but that direction is a path of autonomous systems this time. So it uses path attributes as its metric instead of bandwidth or hop count, like RIP-RO SPF, but it uses this metric for an entire path when calculating where to send packets. We're not dealing with just subnet per subnet routes anymore. We're dealing with entire autonomous system paths that have these subnets inside of them, inside of those autonomous systems. This is what the internet is using as a whole. BGP, again, is classless and classful when you configure it. It uses unicast to send the routing updates. Important, not only do you have to put in the networks you want to advertise one by one, it does not automatically pick them out. The other routing protocols don't either. You have to put in network statements for them. But this, you have to say what routes you want to advertise, the networks, the directly connected. And you also have to say what neighbor you want to advertise them to and what autonomous system that neighbor is in. But guess what? The neighbor has to too. They have to agree to peer with you. This is not as easy as RIP and OSPF. It's not just configure it and it advertises to any routers in its broadcast domain. This is different. You have to have trust here. So this establishes a TCP connection on port 179, and this is before the three-way handshake happens, and then they exchange routing table information. But with that, though, we can load balance with the protocol. We can add a password. That's very important in this. But it does require a level of trust between peering, enterprises peering, such as to competing ISPs, because if you misconfigure BGP or any routing protocol for that matter, you can delete routes in your neighboring routers by accident or on purpose, maliciously, as like a network attack. So you got to be careful and you got to be thoughtful, because you can accidentally delete routes, and you can take down big swaths of the internet that way. Now, that's why when you're working in a bigger enterprise, you have to understand how this works. It's different than just peering with a provider. If you're peering between providers, you have to make sure those routes stay up. Otherwise, you're going to break a lot of customers' access to the internet. But essentially, though, that is BGP. Alright, so now we're going to talk about VLANs, or Virtual Local Area Networks. The whole point of using VLANs is when we have a bigger scale of the amount of networks we want to have. So if we have, the idea is we need to have more networks than it's feasible to have equipment for. Whether that's an interface on a router, or a switch, or UDP cable for those switches and devices, or power needs to power the devices. Anything like that where we're hitting limits on any kind of scalability like that is when we use VLANs. So the whole point is, remember how enterprises manage from 1 to 100,000 networks and or broadcast domains, those IP subnets, again, either in V4 or V6. It's important to know that this stuff works on either IP protocol because it's independent of the protocol it's carrying. What happens is, in a flat network like we've been talking about, each broadcast domain is made by using one router, one switch, and its cabling. You can have multiple switches and cabling and access points and everything, but it's still only one subnet or IP network. All right, it's back to that one group of MAC addresses. That's all we're dealing with in a flat network. And we need another router to make another broadcast domain and everything else. In a network that uses VLANs, on the other hand, broadcast domains, or our IP networks, can essentially use the same equipment. And the reason they can do this is, the effect it causes is that we can have multiple switches, access points, cables in our network, and as long as they're in the same VLAN, regardless of their physical location, they will act as if they're in the same network. This is very similar to VPNs, and in fact, VLANs are a type of virtual private network. But essentially, as long as they're in the same VLAN, they will be able to communicate with each other. Now, each VLAN or network is made separate from others using a number that is the VLAN ID, and that ranges from 1 to 4094. And this number is the amount of IDs you can use on the equipment for your subnets. Now, there is a way to go past 4094, and that is with VXLANs, and this scales past that limit. But VXLANs uses the concept of a VLAN, but it's encapsulated inside of an IP packet at layer 3. And that packet actually routes it over an IP network, and it is destined then to a remote endpoint and a certain port number. But in this way, then we have upwards of 65,000 possible VLANs. Now, this is only done in very large networks. I'm talking like data center networks and ISP networks. Most commonly in most enterprises, 4,094 VLANs is quite a bit to go around, but now if you need more than that, that's where VXLANs come into play. But how this is all done is with a trunking protocol. This is what tags frames. This is what puts the ID in them, and that is called 802.1q, and all it does is add VLAN IDs onto existing Ethernet frames. And the only time the ID is added or removed, it's added when it goes out of a trunk port, either on a router, an access point, or a switch. And trunk ports simply carry multiple VLANs. So it's also called a tagged port in other vendors' literature, but Cisco uses trunked. You can call them tagged and untagged ports in implementation, though. But that's what they do, though, when it's going out of a trunk or tagged port. You add the VLAN ID. When it's coming into one, you take that VLAN ID off of the frame. So, by using the IDs, we're creating separate IP networks, but they can all use one set of physical equipment. So it's multiple IP networks because of the VLANs, and each IP network is assigned a corresponding VLAN on top of it, but it uses one set of physical equipment. That's the great thing. This makes it simple to add and remove devices from that VLAN, apply different security policies like network firewalling rules, and troubleshoot cable and power issues. Now, one more thing I want to talk about before we move on is about autonomous system numbers again, to bring that back around. If you're still having trouble with that, I forgot to mention this. If you look up IXP's Internet Exchange Points, you'll be able to see how autonomous systems kind of come together in data centers and everything to be routed between each other, and you'll see how BGP fits in with autonomous systems. And also that another way to see this is with route lookup servers. And route lookup servers show you routes and routers on the internet. Those are a very cool thing to do. Looking glasses, they're called. Lastly, as well, with all those routing protocols in different VLANs, you can do something called redistribution, and you could put information from like RIP into something like OSPF, or redistribute BGP routes into OSPF inside of your. So you could redistribute routes outside of an autonomous system, coming to BGP, and then put them into OSPF, so the routers running OSPF inside the AS can route out to other networks by knowing that route. That would be an example, but those are three things I wanted to touch on that will tie in autonomous systems. But with that is our VLANs. All right, now on to DMZs. So DMZ is the demilitarized zone. And what this type of LAN or network is for is for when enterprises self-host, and they self-host things like their internal and external resources. And essentially, these resources reside on servers they maintain. So these are things like mail servers, websites, DNS servers, databases, point of sale, bug trackers, payroll. Internal company communications can be on servers they maintain, trouble ticket systems, and many more types of services. The idea, though, is that the DMZ is a highly secure network that we only use these resources on. So what we're trying to do is segment the servers that are providing these services and resources off from the rest of our LAN. So the reason being is if we have public access to a server, like a web server on our DMZ, if that server is compromised, we cannot get information. We cannot break into the rest of the LAN and use it for things like pivot points, and we can't in some cases leak information back out to the internet from the DMZ. So it's to segment it off, basically. So sometimes a DMZ cannot logically or physically reach other parts of the enterprise. So you can do this at your home too, as a lab setup or whatever. Or you could segment your IoT devices off on the DMZ, things like that. But it's not really that it's a DMZ, it is just another IP network. It's another LAN on your router. It could be a VLAN, it could be another port on it, and have its own switch for that broadcast domain. But it's another segment, and you can apply firewall rules on your network firewall to stop packets from the DMZ getting to the LAN, and vice versa. So with the resources of a DMZ, they can be directly connected to the public network, so you can have a public IP address on them or an IPv6 global unicast address on them and have them be accessed directly. Secondly, though, you can also place them behind a network firewall. And that in that case, you have to use destination NAT and firewall rules to allow public access to the server. In IPv6, there's not as much of a concern of destination NAT per se, but you still have to allow the traffic to pass with firewall rules. So nowadays, though, many enterprises use the cloud's technology in place of hosting their own DMZ, and they're doing this for the same purpose instead of maintaining their own infrastructure. The idea stands, though, the resources are still segmented off from their enterprise, in this case in a cloud provider's data center instead of on their own physical premise, but the idea is the same. So, multiple WANs. This is also called dual WAN. We've dealt now with DMZs where we have our own resources segmented, but sometimes we actually want multiple ways to access the internet. So this is multiple WANs, basically. And the purpose of having them is avoiding a single point of failure in the WAN. Okay? So you can avoid the single point of failure by having a backup path. And this is where BGP sometimes comes into play, because we could have each WAN with a separate ISP if you have that opportunity, wherever you get your services from. Depends a lot on your location, if you can even physically get another ISP to put cable in, depending on where you're at. But you can use BGP to peer with the autonomous system of each provider and they advertise their routes into your router, and then you advertise, so sometimes your routes into them, but it's not as necessary, because they don't need to know your internal routes just for you to get out to the internet with them. But you can load balance between them. You can send 50% of your traffic on link A and then another 50% on link B. See, that's another reason to have dual WAN. Not just for failover, but for active, not just an active standby WAN. But you can just use a combination of any WAN access method to do this, such as cable and 4G, cable and DSL, fiber and satellite, any of the types we talked about. But the thing is, IGPs and EGPs are used with multiple WANs to allow routing failover, because if you're switching your WAN connection to another WAN, your router has to start using different routes in its routing table to get the packets out the correct WAN. Otherwise, if that WAN A fails and your router is still using it, your packets won't be routed anywhere. They just won't be able to get out. So that's why routing protocols help. You can also do something with static routing called a floating static route, where that is a route that would only come up on certain occasions, like if your link A interface went down for some reason, or is less preferable, you change metrics to make the router use that backup route pointing to link B. That's gateway failover. But that's how you would do that. Okay, so just like we have multiple WANs to avoid a single point of failure on our WAN, we need something called FHRPs, first hop redundancy protocols, to avoid a single point of failure with our router or our default gateway in our LANs as well. So regardless of what network we're dealing with, it could be a home network, it could be an enterprise, you need reliable uptime and connectivity, especially nowadays. So that's fundamental to what it does for us. And what FHRPs help with is avoiding a single point of failure in the LAN part of the network with our gateway or router. Now, routers use protocols such as HSRP, VRRP, GLBP, and CARP to avoid this. Now, CARP is the Hot Standby Router Protocol. That's a Cisco proprietary. VRRP is the Virtual Router Redundancy Protocol. This is an open standard. Many vendors use this. GLBP is the Gateway Load Balancing Protocol. It's a great one, but it's Cisco proprietary, and HSRP is actually more used now than GLBP. CARP is the Common Address Redundancy Protocol. It's an open standard protocol used across Linux, Cisco, and the BSDs. It's a very good redundancy protocol. But the main reason we're doing this is to avoid that router going down, or at least seemingly not going down, basically. But our network firewalls that keep state, so stateful network firewalls, also can avoid single points of failure. And they do this by being configured as an HA pair. This is high availability. And that means whether it's a firewall, a network firewall from a company, or just a router we've made, or a router itself. Because here's the thing. There is a difference. There are just dedicated enterprise routers that only go up to layer 3, like Cisco's ISR G2s or the older ISRs, or like FortiGates or Juniper J-series routers. Those are dedicated routers, but firewalls have different things they have to sync as well, like their state tables, as well as their configuration. So different vendors, and depending if it's a router or a network firewall, use different methods. But what we're doing is avoiding a LAN failure, okay? That's all we're avoiding. Now, we avoid LAN failures in switches by using STP, the Spanning Tree Protocol. And with that, you would just connect more than one links, like two of the same link between two switches, making a redundant path. And STP blocks one of those paths so you can have redundancy if it fails. One, it prevents a loop because we don't have a loop prevention mechanism in Ethernet. But secondly, if that link fails, it switches over to the other link. And if you have a web of switches, this provides path redundancy. Okay, so this provides redundancy in your switch network as well. It's just less complex. I mean, it is complex, but it has less moving parts to worry about with STP and switches as opposed to our FHRPs and even our high availability on our firewalls. So the idea of it, FHRPs is kind of like VLANs. VLANs used an ID. FHRPs use a virtual IP address. This can be on a router or a layer 3 switch, and when you do it on a layer 3 switch, you get it on a switch virtual interface. And the idea is this virtual IP has a virtual MAC address that's associated with it. The format of that MAC depends on the protocol you are using. They all have special values. And each managed IP from an FHRP is the virtual IP. It belongs to a group, which is a number inside of whatever protocol you're using that the routers have to agree on. And that tells them what other routers should help manage the virtual IP. Okay? Now, the router or layer 3 switch that's active in the group is the only one who can send packets or receive them using the virtual IP's MAC address pair, also called the VIP or the virtual IP address. Only one of them is active at a time. When that's the case, you have an active standby FHRP configuration. When they are both load balancing at the same time active, you have an active configuration. So you can have different types of configs for this. But with a active standby, if the active router in the group fails, the backup router takes over, managing the VIP, and then everyone on the LAN starts to send packets to the VIP IP address. And remember the ARP cache in the NDP table? The NDP table? What happens is this MAC address mapping takes the virtual MAC and IP. The IP looks the same to a client. The virtual MAC looks like any other MAC address. It uses those protocols with ARP or NDP to resolve the gateway's MAC address just like any other IP on the LAN in the broadcast domain. So then it just sends naturally and transparently to that gateway as normal. The clients are not aware that this is a virtual IP that is floating between groups of routers. So that's the cool thing about FHRPs. But the whole thing is you need more than one router to do this. And it does get expensive depending on how many you need and what you want to do with them. So this is another thing like VLANs. VLANs are a way to, consolidate your network and make it more secure, whereas FHRPs are actually a way to add more redundancy, but you have to spend more because you need more equipment to do this. Especially when you use like high availability, you need identical machines, so you have to buy more than one of the same model. Or if you build them, build identical machines. All right, so now we're going to talk about the cloud. So we're going to grab an umbrella because it's cloudy today. So the concept of cloud networking or cloud computing has been around since the mid-2000s. Now, this is actually similar to way back when we had mainframes and the only way to interact with them was with punch cards. You'd have with terminals and punch cards and other things like that, you would actually send your request of what you wanted to do to one mainframe from just a terminal that you just used as an input to the mainframe, and it would send you a result back in a few days, etc. But that was our first way of having a computer, way back when computers were first being invented. And they took up entire rooms, and I'm not talking a supercomputer. I'm talking about a computer that's actually underpowered compared to today's computers. So this idea is coming back. Nowadays we're using like our smartphones. Our smartphones are very basic computers that don't have very much power. And we're actually getting all of the power and features through things that are in the cloud. And the cloud is just data centers that ISPs help us connect to. And they have very powerful hardware in there, very powerful servers that do things for us. They do the it's like a punch card. We send the request from our smartphone's app. It does a bunch of calculation, sends us a result. Our smartphone only had to send a request to tell the cloud's resources to do something. That's essentially what we're dealing with today. Not all of the time, but this is a big part of today's internet is the cloud. It's very popular. So it's been around mid-2000s. AWS, I believe, was the first provider of cloud technologies, but there's many more today. There's DigitalOcean, there's Azure, there's lots of them. But it's called the cloud because it abstracts all the complexity of the network infrastructure, server, and storage technologies that allow it to operate. So this is all usually, if it's meant to be interacted with by a user, it is a straightforward user interface like a website for it. But many resources can be cloud-based. There's email, there's productivity software, there's websites, apps, servers, network devices, network firewalls, and hardware resources. So this is actually all it is virtualization for the most part. So you can do this with like VMware Player or VirtualBox on your computer and make your own quote unquote cloud. You know, the same idea of virtualization at least. But things like Gmail are here, Hotmail, MSN, things like that. Because before the cloud, you actually, hosted your own email server. Now we can just use the email resources from the cloud on somebody else's email server like Google's. Things like that. You can still host your own email server, but that'll be a sidebar. But it is a cool thing to do. But anyway, 80 to 90% of the time, this is a lot more cost effective and secure versus self hosting in your own network or on premise. But there are drawbacks too to this, but not for the most part, it is better than because you don't have to maintain the hardware and everything. So in the long run, it's actually cheaper. So you have two types of this cloud. We have public and private. The public cloud is like a huge pool of hardware resources anyone can use. All right? The private cloud is a pool of hardware resources that's restricted to certain companies' data and their infrastructure. So what they can do is recreate their entire infrastructure in the cloud, along with their network firewalls and their configurations and all of these things. So you can basically replicate your entire LAN in the cloud now. And that's a whole, you have things like cloud engineering where you're entirely trying to keep a cloud network running in a data center, not on premise. So this is used nowadays though, and it's more popular than it was like in 2006. So a data center colocation is kind of in between this, and it's a hybrid option. And this is where we purchase our own hardware, and then we store it in server racks in a data center that we rent space from. So there is a drawback, though, to this. When your hardware fails, you need to physically travel there and repair it yourself. And of course, you cannot just walk in there by yourself. There's other companies hosting data there and their servers. You have to be escorted, things of that nature. So it is involved. But there's a benefit. Any power or WAN connectivity issue or failover are taken care of by the data center itself. As far as you getting access to your server from your LAN wherever you are, and your customers getting access if it's your company's resources that's being hosted there. And anything though to do with power or connectivity of your racks equipment is still your responsibility. Meaning, if you didn't configure the IP address on the interface correctly, and you have like the wrong netmask or prefix length in IPv6, and you're missing the default gateway out of the data center, you have to fix that. You'd have to physically go there, go into like serial console if it's got a serial console, or if it's got a VGA keyboard monitor, and go in there and fix it yourself. So there's drawbacks to this, but you get more flexibility with hardware and things of that nature. So there is disadvantages to the cloud, though, in my opinion. You have number one, which is ownership and control of the data, meaning it's going to probably be secure in the data center, but you cannot be 100% in control of how it's secured, like full disk encryption on your server and things of that nature. So you have less control in that respect. Security and flexibility, because with the cloud, you are stuck with what they give you, basically, with images and stuff to install. Hardware and flexibility, of course, with a cloud. A colocation is not this. That's why a colocation was better in between. You have flexibility of all these things. with a colocation, or if you self-host on premise. But the other thing, though, is OS inflexibility, again, because you only have so many choices. Server software inflexibility. Some of them only let you run Apache, some only support Nginx, some may support Windows, things like that. Physical security of the data and hardware, of course, they're very good at that, but, if you want to be 100% sure, do it yourself. That's my opinion. But retention of your data, if you don't pay the service fee for it, or you have other system failures, like something insane happens and their RAID fails or something, and your redundant array of inexpensive disks. So you have failures that can happen where if you don't have a backup drive, it will mess up all the data and it's gone forever. Well, that happens too. It can happen. It's unlikely, but it's something to think about. Where if you host yourself, you can think about all of those things right down to the fine details of it, and buy the drives and everything. But last thing, WAN outages. If everything is cloud-based, if all your resources are in the cloud, productivity, email, everything, if the internet goes out, you're done. You can't get no work done. You're not going to be very productive, and it's going to be a bad day. So that's the drawback of the cloud for you. And like with the DMZ, if your WAN goes out, your DMZ to your LAN clients is still accessible. So if you have internal time track software or something, you could still get to that. So that is something to think about. Some drawbacks of the cloud. So here are some supplemental resources for the course. RFCs, they're great for understanding future technologies, practicing your subnetting, verifying your subnetting, and some more about some internet and networking concepts, as well as some internet history. Those are always some good reads for you if you want to go further beyond this course. And finally, though, we made the internet. So I'd like to congratulate you for making it through the course. I know it was a lot of information that I threw at you. I hope it was understandable in a very easy to digest manner. That was my goal. And I hope that now you know maybe how to fix your end of the DMARC. But for this point, I encourage you to pursue deeper knowledge and certifications and things. Obviously, don't let certifications consume you. I'm going to say that. I am a Cisco certified individual myself. I have my CCNA. It is very valuable. I recommend it, but I don't think those are the absolute end-all be-all for, everything as far as tech. And I'm not just talking about jobs. I'm talking about actually learning knowledge about tech. So when you get in certification, you kind of get so locked in. I need to know this for the certification exam. When in reality, there's a lot more outside of that as well. They are good though. Pursue them if you will. I would encourage you. They're really worth it. But with all of that, I wish everyone that watched this the best of luck and success in whatever you do in your life. I really do. So I hope you travel down your own route, and I hope that you understand networking and the internet a lot better now. And I hope this was a good starting point for you, and you grow from here. So if you do, let me know about it. That would be awesome. Thank you for viewing, and thank you for watching, and have a very nice day.